Okay, I think we're good to go. I'm going to get started. So my name is Tom Burbacher. I'm the director of the Community Engagement Corps for the UW Superfund program, Superfund Research Program. So I want to welcome everyone to the 2021 Northwest Toxics Communities Coalition Summit, co-sponsored by the NWTCC and the University of Washington's Superfund Research Program. Before we get started with the speakers, I'd want to give thanks to a few people who've made this webinar possible. Can we move the slides, please? Okay. First, there's the board of directors for the Northwest Toxics Communities Coalition who's worked very hard with our folks to get this webinar organized. Patty Martin is the current director of the board. And you'll be hearing from her in a couple of minutes. Darlene Shanfeld, John Shaw, Barbara Quinn, Doris Swiller, and Barbara Miller are all currently on the board of directors for the Northwest Toxics Communities Coalition. So thank them for all their hard work. I'd also like to thank the folks in my coalition here, BJ Cummings, who manages the Community Engagement Corps for the Superfund program, and Lisa Hayward, who manages the Research Translation Corps for the program. Also like to thank our featured speakers, Doctors David Carpenter, Shanna Swan, and Diane Rohlman, as well as Briana, Rivera, and Anna Jarabek. Thank you for agreeing to speak at the summit. We really appreciate it. And I'd also like to thank the funders of our Superfund Research Program for many years, the National Institutes of Environmental Health Sciences. And I'll say a little bit more about the NIEHS and our Superfund program in a bit, just to give you a little bit of information about that. And before we begin, I want to give thanks to our Indigenous hosts and want to acknowledge that this webinar is being broadcast from the traditional lands of the Duwamish, Suquamish, and Muckleshoot tribes within the Coast Salish territories of the Pacific Northwest. So before we started, in case you don't know much about the Superfund program, I want to tell you a little bit about it. First with the Superfund program at the UW. If you want to take a look and get more information about the program, the URL is on the bottom there. So we have a nice website that gives an overview of all the different projects that are involved in the program, as well as a lot of our community engagement activities. So for those of you who would like to see what we do in Region 10, that's our focus, Region 10 of EPA, that's a good place to go to find information. I also want to let you know a little bit about the national program, the National Environmental Institutes of Environmental Health Sciences program. So you go to the next, there you go. We're just one of, I think, 23, 25 different programs around the country. And as you can see, these different programs work in almost all of EPA's regions, from Region 1 to Region 10. So I just want to let you know that, if you're in a different region and listening now and you're part of a community group, there's probably a Superfund program nearby that you could contact if you have issues that you would like to discuss with them. So it's a very broad program. It's a national program. And a lot of people are doing good work in a lot of different places around the country. So with that, I'm going to turn over the webinar to Patty. And I think Patty's going to tell you a bit about the NWTCC.
So again, to welcome you to the 12th Annual Toxics Communities Coalition Summit. My name is Patty Martin. I serve as the chair of the Northwest Toxics Communities Coalition, and I have the pleasure of working with organizations and individuals throughout Oregon, Idaho, Washington, and Alaska, which, as Tom mentioned, encompasses Region 10 EPA. The individuals and organizations are committed to protecting their communities from the dangers of hazardous waste sites, and the board of the Northwest Toxic Communities Coalition is emblematic of that dedication and should be commended for their ongoing efforts in their communities and to the coalition. Chemical mixtures and synergistic effects was chosen by the board for this year's summit because little is known about how chemicals in our environment interact with each other and their impact on human health. The expert speakers that we've assembled for today's summit will shed some light on what's known and what is left to be discovered. So I'd like to thank them all in advance for sharing the research with us. As Tom mentioned, the Northwest Toxics Communities Coalition is supported by the University of Washington Superfund Research Program through a grant from the National Institutes of Environmental Health Sciences. The summit's made possible through that support, and and on behalf of the coalition, I would like to express our gratitude to the Superfund Research Program and to the NIEHS for their continued support. Lisa Hayward with the University of Washington Superfund Research Program is now going to go over how to use the Zoom. So Lisa.
Hi, everyone. I'm trying to get my video to start, and every time I try to hit the little icon, oh, here we go. Okay, hi, I'm Lisa Hayward. I work with Tom Burbacher and BJ Cummings in the University of Washington Superfund Research Program. I want to mention a few technical details before we get started with today's talks. First, we're participating in a Zoom webinar rather than a Zoom meeting, and the functionality is a little different. So there are two options for asking questions. One, you can enter questions into the Q&A field located in the menu bar at the bottom of your screen. A moderator will then ask your question of the presenter after their talk. Or two, you can raise your hand if you would like to be unmuted by a host to ask your question directly. The raise hand option may be in the menu bar at the bottom or at the bottom of the sidebar on the right, depending on your computer. So we'll save all questions until the end of each talk. We would like to reserve the chat for the host to post resources and links, so please do not type your questions in the chat. Finally, you cannot rename yourself in webinars, so we ask that you provide your name and affiliation when you ask your question. Thank you for joining us today. I'll now pass things back over to Patty Martin, who will introduce our first speaker, and I'm just going to show the agenda on the screen here while I do that. Patty, you can go on and talk. I'm not seeing the agenda.
Okay, all right, thank you. So Dr. David Carpenter is our first speaker this morning. He's a public health physician who received his MD degree from Harvard Medical School. He chose a career of research in public health rather than clinical practice. He is currently professor of environmental health sciences at the University at Albany, where in 2001, he worked to establish the Institute for Health and the Environment. In 2011, the Institute was designated as a collaborating center of the World Health Organization in environmental health. The third redesignation was just received in July of 2019. Dr. Carpenter's research is focused on the study of environmental causes of human disease. He has ongoing collaborative studies on air pollution and health in several countries and studies health effects of electromagnetic field exposure. He has more than 400 peer-reviewed publications and has edited 6 books. Please welcome Dr. Carpenter.
I think you have to allow me to open my video.
Oh, okay. Again. There we can, oh, we saw you briefly.
Briefly.
Yeah.
There we are. Well, thank you very much. Let me just go directly into my slideshow. It's a pleasure to talk with you again. I was physically at one of these meetings a couple of years ago, and I only am sorry I'm not physically there again today. But it's still a pleasure to be part of the Superfund program. I headed the Superfund program in New York for a long time, although we don't have it any longer. So this whole session is on chemical mixtures, and that's what I want to talk about. Let me start with a very old slide. This is a chromatogram of wet diapers from my son, Zachary, and my PCB analytical chemist son, Patrick. Zachary was breastfed because I'm a public health person and I know how valuable and important breastfeeding is. Patrick's father didn't want his wife to breastfeed because he was concerned about all of the hazardous chemicals that are in breast milk. So we did this very crude chromatogram, the idea being that if Patrick's father was right, Zachary would have a lot more chemicals in a wet diaper than Patrick does. These are two infants born about 3 days apart at 1 year of age. And what is striking is how many chemicals are in urine of 1-year-old children. If you think about it, what is a 1-year-old, what's their exposure? Well, there's some personal care products that are put on their bodies. There's either breast milk or formula milk, and there's some ground up vegetables, but their ability to get around and be exposed is pretty limited. So the issue is how many chemicals are in the human body? Well, there's no good answer to that. The EPA says there's some more than 80,000 chemicals approved for use in the US. And in 1987, which is a long time ago, there was a report of 298 identified chemicals plus 700 unidentified peaks in a human body, almost 1,000 different chemicals. The World Counts is an organization that follows chemical exposures. 64.5 billion tons of chemicals produced each year, 152,000 different man-made chemicals on the market, 9,000 in personal care products, including products that are used on infants and babies. And it's widely believed that each person has at least 700 different chemicals in their body right now. And of those, 400 and some of them are almost certainly carcinogens. Well, what I've chosen to do today is basically summarize briefly 3 different studies that I've been involved in. The first will look at mixtures of metals on cognitive function. The second will look at mixtures of persistent organic chemicals. And then the third will look at mixtures of chemicals that are not so persistent, but those that are found in everyday products. So let me start with studies of chemicals in cognitive function in older adults. This is the work of a wonderful PhD student of mine, Nozomi Sasaki, and this will be part of her dissertation. The issue is that we know that in children, there are a number of chemicals that cause reduced IQ and shortened attention span, and that this can lead to lifelong impairment. The best studied chemicals are lead, methyl mercury. There's some information about arsenic, cadmium, environmental tobacco smoke, PCBs, polychlorinated biphenyls, some additional evidence for some other persistent organics, although they're often difficult to separate out because they all migrate with PCBs and dioxins and chlorinated pesticides. But what Nozomi has done is to use NHANES data to examine the effects of exposure to metals and omega-3 fatty acids as they affect cognitive function in older adults. So NHANES has this information on adults age 60 years and over, and they're given 3 different cognitive tests that are immediate recall. These tests are to test for immediate recall, delayed recall, and working memory. So NHANES collected blood and urine samples from metal analysis from these people and have the people self-report their levels of fish consumption. And that's the data we've used to relate to cognitive function. Now, this is a busy table, but I needed to show it, and I'll just sort of describe it. So what you see now, this is for the immediate recall, the CRAD immediate recall test. You see that immediate recall is better in younger people than older people. Now, I've often wondered if this next thing was correct or not, but it implies that women have better memories than men do. I think sometimes my wife shows that she never forgets. But in any case, if you have diabetes, your memory function is poorer. If you're depressed, your memory function is poorer. Memory is better in better educated people than in non-educated people. We did not find any significant effect of smoking. And I was actually a little pleased to see that moderate alcohol consumption those people had better memory than those people that didn't drink at all. But clearly excessive alcohol consumption is counterproductive. Now, these are the results we found for these 3 tests. So the CRAD immediate recall, the CRAD delayed recall, and the digit symbol substitution, which is a test for working memory. We found striking deficits in all 3 tests in relation to blood levels of cadmium and lead. And all of these were quite statistically significant. Now, lead exposure in cognitive function in children has been studied since Needleman's original study in the 1970s. And since that time, that's been confirmed in studies around the world. There's been less attention to cadmium, but cadmium is important. And there are some studies in children, but this result indicates that cadmium is just about as dangerous in older age as in lead. And it's interesting that others have shown that environmental tobacco smoke causes reductions in cognitive function in children. We suspect that that is an effect of cadmium because the tobacco plant concentrates cadmium, and cigarette smoking is one of the major risk factors for cadmium exposure in adults. We did not find any effect of manganese, but we found a striking beneficial effect of selenium. And this was quite a surprise to us, and I'll talk much more about that later on. But you see how dramatically immediate recall, delayed recall, and working memory, all 3 were significantly improved in relation to the serum levels of cadmium. Well, I mentioned earlier that methylmercury has long been known to cause decrements in cognitive function in children. It's been studied around the world. We were quite surprised to see no effect of either total mercury, inorganic mercury, or methyl mercury on cognitive function. Now, it's methyl mercury that's best known to impair memory. In general, inorganic mercury doesn't cross the blood-brain barrier, but you see that total mercury, which actually is primarily methyl mercury, but none of these were significant. And again, I'll come back to that a little bit later. Some metals and metabolites were only measured in urine. And arsenic is known to be an inhibitor of cognitive function. And the metabolites of arsenic were associated with decrements of some of these cognitive tests, as were urinary lead, cadmium, and tungsten. Now, tungsten also was a surprise. There's very little information about tungsten, and I'm not going to address that any further. But we found no significant association with the organoarsenic compounds, and that's expected. Organoarsenics are not metabolized in the human body. So the inorganic arsenic is very toxic, but the organoarsenics are usually just excreted without any harmful effect. There was also no significant effects of barium, cobalt, cesium, molybdenum, manganese, antimony, tin, strontium, thallium, and uranium in the NHANES data. Okay, so we did the linear regression results for the multiple blood indicators, log transformed on immediate recall, adjusted for the social demographic characteristics as indicated at the bottom. And again, what we find is that lead and cadmium, at least in the 70 and older group, were significantly associated with decrements in immediate recall, but selenium was very positively associated with improvement in immediate recall. And further, the amount of improvement was greater in older people. Again, no effect whatsoever of methyl mercury. These are results of modeled efforts to try to determine the percentage of people in the lowest 10%, lowest 25%, on up through the highest 90% of reports on this CRAD immediate recall test. What you will see is that the selenium concentration is highest in the people with the highest immediate recall. And that's true at both age groups. However, the lead and cadmium are at the highest concentration in those people with the lowest 10 or 25% scores on this immediate recall. So this is evidence that, again, that selenium is improving immediate recall, whereas lead and cadmium are harming it. And that that association is true at both age groups. So let's talk about the effects of selenium. Well, selenium is an essential metal, and it's a cofactor for a number of enzymes. That includes the enzyme that converts thyroxine to T3, which is triiodothyronine, which is the active component of thyroid hormones, but a whole variety of others. But selenium is known to be toxic and actually can be fatal at very high concentrations. So you need some, but you don't want too much. So we were very surprised to see how strong this beneficial effect was. And when we started to search, we found there was old literature dating from way back in the 1970s that showed that selenium complexes with other toxic metals to create an insoluble complex that is then excreted. So it isn't just that selenium is good for you, it's that selenium binds to lead, to cadmium, and in the old literature, clearly strong evidence that it binds to methyl mercury and therefore reduces the toxicity of lead, cadmium, and methyl mercury and other toxic metals, including silver and gold and a whole variety of metals. I've never heard of this before, and I suspect that many of you haven't. It seems to have been sort of lost, but very well documented in older literature. Our results are so striking that I really do think in the medical community, there should be a reconsideration of the use of supplemental selenium to improve mild cognitive impairment in older adults. There's also strong evidence that many older people are selenium deficient. That may be because of diet or changes with age of absorption of selenium and things like that. But our results certainly suggest that selenium is beneficial. I'm not aware of any efforts to counteract childhood lead poisoning by selenium. Clearly, selenium at very high concentrations is toxic, but in controlled administration under the care of appropriate physicians, it seems to me that this is something that should be seriously considered. Well, what about the fish consumption? Now, we know that methylmercury exposure is primarily from eating fish. And most people recognize fish as being healthy food, and they contain omega-3 fatty acids. Omega-3 fatty acids are a polyunsaturated fatty acid that our bodies cannot make. And therefore, we have to get our omega-3s from our diet. The major source of the longer chain omega-3 fatty acids is fish consumption. And therefore, fish can also be sources of metal consumption, but we wondered whether the omega-3 fatty acids in the fish were actually a beneficial effect. And what we found is yes, very clearly. So NHANES doesn't have direct measurements of omega-3 fatty acids, but they have self-report of how many fish meals per month individuals ate. And this shows in both males and females that the more fish meals people report eating, the higher their score on the immediate recall test. Well, what about the correlation between reported fish consumption and metal exposures? Well, there are negative correlations with cadmium, copper, no significant things with lead and manganese, but there is some association with selenium. So one does get some selenium from fish consumption. But if you look at the mercury compounds, you see that very strong, the methyl mercury, the total mercury, very much a function of fish consumption. And then for arsenic, the organoarsenics, again, we know they're in fish, strong association there, but they're not metabolized in the human body. So fish consumption gives you some selenium. It certainly gives you a lot of mercury and the organic arsenics that are not terribly important. So the conclusions from this study, which is the first of the three that I'm going to present, is that lead and cadmium have very significant negative effects on cognition in older adults, just as they do in children. But that selenium is effective in counteracting the negative effects of lead and cadmium. While some selenium comes from fish, we know that there are many other sources. Vegetables, meats all have some selenium. The amount varies greatly in different geographic regions based on the selenium content of soils, but most selenium in most people comes from other dietary sources rather than fish. But in this study, fish consumption had a significant beneficial effect, even though eating fish is the major source of methylmercury. So while we don't have direct measurements of omega-3 fatty acids, we suspect that they are also important for cognitive function, at least in older adults. And there's some other literature that argues that that is the case. All right, let me move on to the second study. This is a study that was funded by the Pew Charitable Trust several years ago, but it's very relevant to the issue of mixtures, and so I'm presenting it. It also is relevant to our discussion of omega-3 fatty acids, because salmon have they're a fatty fish. They have very high omega-3 fatty acids. And what the Pew Charitable Trust asked us to do was to compare farmed salmon with wild Alaskan and British Columbia salmon in terms of their concentrations of chemicals. Now, I should say right from the start that we measured metals in both farmed and wild salmon. We did not find any significant difference between the farmed and the wild salmon, and we did not find concentrations of metals that were harmful, although I must say I was initially surprised at the organoarsenics because I hadn't realized that they're not metabolized in the human body. Well, so what we did, we purchased farm salmon from 51 farms in 8 farming regions, and that included Washington State, although the main salmon farming is in more colder regions. So Western Canada has more than Washington State does. But these regions are basically Northern Europe, East Coast, West Coast of the US, and Canada, and Chile, which is a major farm salmon country. And then we purchased wild salmon from Alaska and British Columbia. Now, farm salmon are almost only the Atlantic salmon, whereas, and that is true whether they're farmed in the Pacific. The Atlantic Ocean has almost no commercial salmon fishery any longer because they've been all depleted. But the wild salmon in the Pacific are chum, coho, chinook, pink, and sockeye. And we purchased those from suppliers in Alaska and Western Canada. And then we had students of mine on all over the world go into supermarkets in North American and European cities and purchase salmon fillets, almost all from farmed salmon. We made composites of these fillets and tested them for 14 organic contaminants, 9 metals, and the omega-3 and omega-6 fatty acids. And then we also purchased some of the food that the farm salmon are fed. I'm not going to present that evidence, but let it be noted that the food that the farm salmon are fed is the source of their contamination. These are our results. Notice that this is a log scale. The green bars are the wild salmon. The red bars are the average of the farm salmon from all of the sites around the world. What we have here are chlorinated pesticides and PCBs and dioxins. All of these are complex organic molecules with multiple chlorines around them. Now, notice that for dioxins and PCBs, the content of the chemicals of the PCBs and dioxins is an order of magnitude greater in the farm salmon than it was in the wild salmon. That also is true for all of the chlorinated pesticides, with the exception of lindane, where there was not a statistically significant difference. Well, this slide just simply shows the distribution from different countries or different cities. So the red bars are the farm salmon from different countries. What you see is that those from Northern Europe tend to be larger for these 4 different chemicals. So it's PCBs at the top, dioxins, toxaphene and dieldrin being complex chlorinated pesticides. So Northern Europe has a longer history than North America or South America, and it's a little more contaminated. I should say that what these farm salmon are fed is a concentrate of trash fish collected locally. It's got about 35% lipid and the other is fish protein. So the least contaminated salmon were those from Chile and from Washington State. And Chile is understandable. It's less developed. Probably some of the food that the Washington State salmon were fed also came from Chile. But then you look at the supermarkets fillets from different cities. And as you would expect, those from Northern Europe have higher levels that match the levels in the farm salmon. And then cities in the south of the US have lower levels, more like those from Chile. The green bars are the wild salmon from the different places that we obtained them, and they have significantly lower levels for all four of these chemicals. Now, if you look in any one fish at the distribution of all of these chemicals that I've shown you, what you find is if a fish is high in one chemical, it's high in every chemical. Now, this is really very important because in general, when analyses of food is done by FDA or EPA or whomever, they measure one chemical and provided advisories on the basis of the concentration in that chemical. But in this situation, if you eat a fish that's high in PCBs, it's also high in dioxin and in DDT and in Mirex and in dieldrin and in toxaphene. And that is significant across the board. So you're eating a chemical mixture. Even if the concentrations are low, you're eating a chemical mixture because every fish had measurable content of all of those 14 chemicals that we were monitoring. All right, so we used EPA, well, this slide simply shows how EPA and the International Agency for Research on Cancer, the WHO, rank these chemicals in terms of whether they cause cancer or not. Most of EPA's ratings is that they're probably carcinogenic. Now, EPA has long had the position that if a chemical causes cancer, there is going to be a linear dose response curve. And therefore, you can identify a cancer slope factor so that if you measure a concentration of chemicals, you can extrapolate back to zero, but there is no concentration that does not increase the risk of cancer. Now, IRAC it's much easier to test for carcinogenicity in animals than it is in people because we're all exposed to chemical mixtures. So it's rare that you find a population exposed only to one chemical for a long period of time where you can prove that it's a carcinogen. But what you see is for most of these things, dieldrin and endrin being exceptions, there's sufficient evidence that they cause cancer in animals. And in humans, it's possible. The only stronger associations are with dioxin and with PCBs. And this is actually an older slide. IRAC now rates PCBs as sufficient proven human carcinogens. So now EPA has developed a series of equations that allow you to calculate how many fish meals per month you can eat if you know the concentration of the chemicals. So for a single chemical, the allowable maximal fish concentration is a function of the acceptable cancer risk, and EPA chose 1 in 100,000, which is less than the 1 in a million that is the gold standard. And it's a function of body weight, the cancer slope factor, the concentration of the contaminant in the fish, and the meal size. Then they have another equation that will do the same thing for multiple carcinogens in the fish meal. Well, we've applied that the formula on the upper right to the concentrations of these chemicals for which there is a cancer slope factor in salmon. And this is just an example of the how EPA makes these calculations. This is for PCBs. The cancer associations are listed on the right, and for all non-cancer endpoints, EPA has the assumption that there's a reference dose below which there's no adverse health effect. So note that the cancer health endpoints are more stringent than EPA. It provides advisories for sports fish consumption. Now, FDA and EPA don't agree at all. The FDA standard for shipping fish in interstate commerce is 2 parts per million. Notice that the EPA standard is slightly less than 0.1 part per million. So FDA is allowing fish to be transported and served to people with much higher concentrations than what EPA will allow. This is what we get if we look at the cancer risk assessment using that second formula from EPA. For salmon from Scotland, the Faroe Islands, and Norway, you can safely eat 1 meal of farmed salmon every 5 months without increasing your risk of cancer. For Eastern Canada, Maine, and Western Canada, you can eat 2 meals every 5 months. For Chile and Washington State, you can eat either 4 or 5 meals a month without increasing your risk of cancer. The green bars again are the wild Pacific salmon. They vary. Some of the bigger ones still provide recommendations that you don't eat more than 1 meal a month. The chum and the pink salmon, these are the ones that are not common. They're the canned salmon. They're not often used for steaks. And for those, you can eat 5 meals a month. And you see that the supermarket samples, is Seattle there? I don't think it is. Oh, yes, it is. That would be 3 meals a month, 3 meals every 5 months for farmed salmon purchased in a store in Seattle. So this is pretty stringent. Now, I should say one thing. As I said, the food this farmed salmon were fed is the cause of the contamination. Well, this study was done some years ago, and there has been a change. We've depleted the oceans of these trash fish that were the major food source when this study was done. And so the industry is now reducing the amount of fish oil, fish meal, and substituting soy oil and soy meal. Well, plants don't accumulate these organic chemicals, but they also don't have omega-3 fatty acids. And therefore, what's happened over time is that farmed salmon are both less dangerous and less healthy than they were when this study was done. Now, the other question, well, what about other health effects? And this just lists the various health effects that are known to occur for these chemicals. And it's not just cancer. Many of them suppress the immune system. They have neurological effects. They're phytotoxic. They have reproductive effects, effects on the musculoskeletal system, the liver, kidney, cardiovascular system, and blood, and our endocrine disruptive chemicals. So we do have a publication where we tried to look at the relative benefit of the omega-3 fatty acids against these things, and we found that basically they the dangers from the contaminants in the highly contaminated farm salmon grossly exceeded the benefits from the omega-3 fatty acids. So let me talk a little more about the omega-3 fatty acids because they are essential. We can't synthesize them. You get shorter chain from some oils and nuts and some green leafy vegetables, but the longer chain omega-3s are made by aquatic algae and they're bioconcentrated in seafood. They're essential components of nerve cell membranes, and they're concentrated in the brain and the photoreceptors of the eye, and they are thought to regulate membrane fluidity throughout the body. So there's some evidence that omega-3s are protective after a heart attack, and that's thought to be because of this effect on membrane fluidity. There's some evidence that if an infant is born prematurely and is not breastfed, that their cognitive function is improved by omega-3s in formula. There's some reports of psychiatric and memory disorders in adults being improved by omega-3s. I found that evidence not very strong. I think our evidence may be even strong. There's really no evidence that omega-3s have any effect on diabetes and glucose tolerance. But omega-3s are anti-inflammatory, and that's thought to be a very valuable effect of them. The big point is omega-3s do not protect against cancer. So this issue of do omega-3s protect against heart arrhythmias, that's not clear any longer. And so the point here is that eating uncontaminated salmon is healthy, but contaminated salmon or any other contaminated fish is going to counteract the beneficial effects. This simply shows the amount of omega-3 fatty acids. Again, green is wild, red is farmed from countries, and yellow is purchased in supermarket. The farm fish, they're fat. They don't exercise very much. They have high levels of omega-3 fatty acids. The omega-6 fatty acids, we all get too much of those. They're present in all animal fats. But there's a lot of omega-3 fatty acids in salmon. Yet, in our analysis, they did not compensate for the organochlorine contaminants that were found in salmon. So our conclusion is that farm salmon have very high levels of organochlorine compounds, much higher than wild salmon. That source is the food. It's worse in Northern Europe than North America, and least contaminated from South America. The beneficial effects of the omega-3 fatty acids have to be balanced against the risk of cancer from the contaminants. And use of the EPA risk assessment methodologies for PCBs, pesticides, and dioxins show that farm salmon from all regions provoke highly restrictive fish consumption advisories. Okay, let me move quickly to my third talk. This is on endocrine disruption. The endocrine system is important for all kinds of physiologic functions. Endocrine system includes the sex hormones, thyroid hormone, vitamin D, insulin, parathyroid hormones, and many others. And endocrine disruption is when exogenous chemicals interfere with the normal function of the hormones. They can do it in a variety of ways. They can mimic the natural hormone and activate receptors. They can antagonize the natural hormone. They can alter rates of synthesis or metabolism of the natural hormone. And they can induce genes that alter many different aspects of the hormonal function and action. Now, hormone receptors are effectively nuclear receptors. And this is an important concept because nuclear receptors are receptors that are actually in the cytoplasm or even on the DNA. And when they're activated, they induce genes. And this is why, for example, at puberty, estrogens or androgens in girls or boys cause many, many changes in every organ system, in physical structure and so forth. So, and then there are many other of these nuclear receptors. The aryl hydrocarbon receptor, for example, is often known as the dioxin receptor, and dioxins and some PCBs activate that. There are these other receptors, including vitamin D. Vitamin D is not a vitamin, it's a hormone. And all of these act in very impressive ways. This is just one example of the number of genes that can be activated by one nuclear receptor, the AHR at the red at the top. And then there are other nuclear receptors I'm not going to talk about today, but you see that activating that one receptor is known to change the expression of at least 300 different genes. Now, when a gene is activated, it makes more of the protein that's its product. When it's suppressed or downregulated, it makes less. So when you disrupt endocrine systems, you can change many things, not just one physiologic function. So let me tell you about the Halifax project. This was a meeting that was held in Halifax, Nova Scotia in 2013. It was supported by NIEHS, and I wrote that grant to get the support for this meeting. The question was here, if we look at mixtures of chemicals, most of whom are identified as endocrine disruptors, but are not identified as being carcinogenic, can that mixture cause cancer even if it's not known that the individual chemicals cause cancer? And we look particularly at those chemicals that have estrogenic activity. This was done by a series of committees, working groups, that wrote manuscripts in advance of our meeting, and they were focused on the hallmarks of cancer, coming from publications, Hanrahan and particularly. And these are different factors that we know that are characteristic of cancer. I won't read them, you can read them there. But the hypothesis was that any true carcinogen is going to basically do all of these things. So the question we had, well, you have this mixture of chemicals that are not known to be cancer because they don't do all of these things. But what if one of those chemicals does one thing, like inducing angiogenesis? That means inducing blood vessels to grow into a cancer. And a different chemical does resisting cell death. And then others do all of these things. Can the whole mixture be carcinogenic? So I already said when we talked about salmon that EPA has always considered carcinogens to have a linear dose response curve, while non-cancer effects have a threshold. Well, we know that that's simply not true for a lot of chemicals, especially those that affect the endocrine system, because the dose response curve is not linear, and they're low concentration effects, and sometimes low concentrations of a chemical are more toxic than higher concentrations. So these were the kinds of chemicals that were of particular interest. So our team, we looked at 89 different chemicals. And when we looked at those standard things like genetic instability, resistant cell death, angiogenesis, we found that there are a lot of chemicals that would meet some of those criteria for cancer. And so many of these non-carcinogenic chemicals had the potential to act on functional targets for cancer. But we found for some of the others that there just wasn't enough information to really consider. And so of the 89 chemicals known to be endocrine disruptors, we found that 59% of them didn't have linear dose response curves. And most of these had these low dose effects. And only 13 of the 89 were found to have a linear dose response threshold. But there were many of the chemicals that we looked at that for which there just wasn't enough information. So, I mean, I can't tell you all 89 chemicals, but these included things like the bisphenols, phthalates, a lot of the chemicals that are in personal care products and so forth. But these were the chemicals we're all exposed to every day. Now, the conclusion from the Halifax project was that our analysis suggests that the cumulative effect of individual non-carcinogenic chemicals acting on different pathways and a variety of related systems, organs, tissues, and cells could plausibly conspire to produce carcinogenic synergies. So in some ways, this is not satisfactory in the sense we couldn't confirm our hypothesis because there simply wasn't enough information. Well, we could confirm that if you have a certain mixture of these chemicals, each of which is not a carcinogen by itself, they meet all the criteria for being carcinogenic. So to conclude my talk, we're all exposed to chemical mixtures. And the problem is that most of our knowledge of how chemicals act comes from studies of single chemicals one at a time. We know that chemicals can have additive effects. They can be less than additive. They can be antagonistic. They can be synergistic, which means more than additive. But even the work done on chemical mixtures usually deals with a limited number of chemicals. And I think all three of these studies show that metals have complex interactions. Persistent organics have complex interactions. And certainly these lower chlorinated endocrine disruptive chemicals, many of them being volatile or semi-volatile, have very different interactions. And so I think that there's really a lack of adequate understanding of chemical mixtures. And the fact that each of us has a different mixture in our body because we all are exposed somewhat differently, it's very difficult to do the kind of study that one would like to do to truly identify how chemicals are interacting in the body. But I hope that these three different kinds of studies that I've been personally involved in give you some sense of the ways in which we need to explore and try to understand how chemicals interact. Thank you for your attention.
Great, thank you, Dr. Carpenter. That was fascinating. And I know we have some questions in the Q&A, and attendees, you can just continue to add those, or you can raise your hand and I'll call on you and unmute you so you can ask directly. So the first question is from Elaine Faustman. She says, David, wonderful presentation. Do you have any insights on what we should expect with the emerging pollutants such as the perfluorinated compounds? Will they have the same patterns as you showed earlier for the various chemicals such as PCB clustering together and correlation of seeing all contaminants at the same time? Also, any comments or suggestions by some guidance to eat younger fish to decrease the overall exposures to these compounds?
Well, two good questions. Let me deal with the last one first, because young fish haven't had a time to accumulate a lot of contaminants. The older the fish, the more carnivorous the fish, the more contaminated they're going to be. It's probably true in humans as well. The more carnivorous we are, the more contaminants we get, although you can get a lot of those chlorinated pesticides off your broccoli as well. So if you're going to eat fish, choose smaller fish, choose vegetarian fish, and you will reduce your exposure. Now, of course, they are also going to have lower levels of omega-3 fatty acids. All right, let's talk about the perfluorinated compounds, because that's also a wonderful question and a major concern. We've sort of gone through phases here. We first knew a lot about dioxin. We studied dioxin, then we started studying PCBs, then we started studying the brominated flame retardants. Now we're looking at the perfluorinated compounds. All of these chemicals have in common that they have halogen items, chlorines, bromines, or fluorines. That makes them very persistent in the environment, persistent in our body. The perfluorinated compounds haven't really come on our radar until relatively recently. We know that they are carcinogenic. They increase the risk of kidney cancer, bladder cancer, testicular cancer at minimum, probably other cancers as well. We know they interfere with hormones. They have effects particularly well documented on thyroid hormone function. There is increasing evidence that they may have cognitive adverse effects, and they certainly have effects on metabolism. Now, they activate the peroxisome proliferator series of nuclear receptors, and different species have different amounts of these nuclear receptors, so that in rodents, they cause a wasting syndrome that isn't common in humans, but they do almost everything that PCBs do, that brominated flame retardants do. And yet they're not exactly the same. Now, furthermore, there's some huge number of different perfluorinated compounds. And what we're finding, again, another one of my students working on at this using NHANES data finds that you can look at different perfluorinated compounds, and one group will have this series of adverse health effects. Another group will have a totally different. So we've already seen this with dioxins, with PCBs, with brominated flame retardants. They're themselves a mixture of different molecules depending on how many halogen items they have on their rings and where they are. And they don't all do the same thing. So it's a very complex world that we're living in. And we need to get much more information on the perfluorinated compounds than we have now, but they're not a good thing. They're very persistent. We all have them in our body, and they're doing nasty things to us.
Okay, Elaine says, thanks so much. Again, wonderful presentation and covering very complex issues in a direct and informative manner. And we have a question from Paulina Lopez. Are the consequences the same, airborne versus consumption in humans? Thank you for the great information. Our Moss study showed the presence of arsenic in the air. What is the difference of breathing versus consuming?
Well, breathing is a much more important route of exposure for all these chemicals than has been previously appreciated. Now, the question was specifically about arsenic. Metals bind to particulates. Arsenic isn't a volatile compound in the way that mercury is, but it can be bound to particulates, and we breathe in particulates. The same is true for lead, for cadmium, for other metals. They get into our lung. If they get past the cilia and the upper part of the respiratory tract, they deposit. The metals come off of the particulates, they get absorbed in the blood, and then that's a route of exposure that's as bad as for anything else. Speaking of inhalation of these perfluorinated compounds needs very close attention because they are semi-volatile. A lot of my work recently has been with inhalation of PCBs. We've long-term, I think I talked about this when I spoke to you people a couple of years ago. We have strong evidence that PCB exposure increases the risk of diabetes in our Native American population, the Mohawks that live along the St. Lawrence River. In addition, PCB exposure increases the risk of menstrual irregularities and even at high concentration, failure to ovulate. But for both of these diseases, it's the lower chlorinated, more volatile PCBs that have that effect, not the more highly chlorinated compounds that you find in fish or food. In contrast, the PCB exposures also increase serum lipids, but it's not the lower chlorinated compounds that do that. It's the higher chlorinated compounds that are found primarily in the food supply. So again, it's this issue that inhalation of a chemical can cause a profile of diseases that you don't get from ingestion. And all of these organochlorine, organobromine, organofluoride chemicals are semi-volatile. So if you're breathing if you're in a place where they're in the air, you breathe them 24/7. And well, the concentration may not be super high, but they can accumulate in your body over time because of inhalation.
Thank you, David. The next question is from someone we can't identify because it looks like a bunch of attendees are identified as BJ Cummings. So just a quirk of Zoom. But it says, Dr. Carpenter, I missed a point where Pacific Ocean offshore caught salmon from the Pacific Northwest more or less contaminated than where salmon collected from one Puget Sound or from two fish farmed in Puget Sound. Oh, it says RCH is the question.
The farm salmon were much more contaminated no matter where the farming was done. And that is a function of the food that they were fed. Now, we didn't specifically monitor salmon from Puget Sound. I know there's other evidence that shows that they are very highly contaminated. So the wild fish that were part of our study were exclusively from salmon farms, not salmon farms, but salmon fisheries, mostly in Alaska, a few in northern British Columbia. The only Washington state salmon we monitored in that study were from farmed salmon off the coast of Washington state.
Okay, thanks. Another question from BJ Cummings, who isn't BJ Cummings. What is the difference between less than additive and antagonistic interactions of toxic chemicals?
Would you repeat that question, please?
Sure. What is the difference between less than additive and antagonistic interactions of toxic chemicals?
Well, I think this is a question about how the chemicals are acting. So, for example, if you have two chemicals that bind to the same site, they may compete. So if they're present at low concentration, they may be totally additive, but if they're at higher concentration, they may be less than additive because all of those sites are already filled. Now, that's somewhat different from antagonistic. So if a chemical binds to a receptor site and prevents the other chemical from actually ever getting there, that would be a pure antagonism. The net effect, of course, of the two mechanisms is pretty much the same.
Great, thank you. We have a question from Darlene Shanfald. How does the water pollution factor into the contamination of the fish?
Well, the water contamination is responsible for the accumulation of the chemicals in the trash fish that are caught, that then have their oils concentrated and make the salmon food. So I certainly don't minimize the effect of the background contamination of the oceans. We've really contaminated those oceans to a great degree. That's true for the organochlorine chemicals. That's true for methyl mercury by the mercury contamination. But the level of contamination from the wild fish was just not anywhere near what it was for the farm salmon. I hope that answers the question.
Yeah, thank you. Question from Patty Martin. How old is the study with the high PCBs mentioned for European farm-raised fish?
Well, our first results were published in 2004. I think so it's 20 years old. I think our studies, our project started in 2000. There were 6 of us. I won't identify everybody because I'll probably forget someone's name, but 6 of us that had this grant from the Pew Charitable Trust to do this global study of contaminants in farm versus wild salmon. So 20 years, that is reflected in the fact that the food-fed farm salmon now has much more plant protein and fat than it did then. As I said, it makes the farm salmon both less harmful and less beneficial because there are much less omega-3 fatty acids in the salmon.
Okay, great. The question from Lisa Arkin. Could you please talk about the risk of inhaling chlorinated compounds in urban or suburban areas that have been devastated by wildfires in cases where many people are still living in the area, particularly where industrial sites and trailer homes burnt down, as in the Almeda fire in Southern Oregon?
Well, wildfires are a very dangerous thing to human health. No question about that. One of the biggest concerns is that fires cause the formation of dioxins. And dioxins, they've been studied forever. They're super dangerous. They're potent carcinogens. They activate this AH receptor, a nuclear receptor that I showed you. And if you remember that slide that shows all the different genes that are altered on activation of that receptor. The dioxins can be volatile. So early on in the fires, you can breathe them in, but they're going to bind to particulates. And every time the wind blows and the dust rises, you're going to have dioxin containing particulates that are inhaled. When you burn buildings, burning plastic is a particularly potent source of making dioxin. But, there are other organic chlorine chemicals like PCBs in most homes. There are also going to be mercury-containing devices that are going to generate both elemental mercury and inorganic mercury. So this is a concern. Of course, we don't have good mechanisms for dealing with the dust that comes from fires, or for that matter, for the smoke that comes while the fire is going. But it's a major source of exposure.
Thank you. I don't see any other questions. Do people have questions? You can raise your hand or you can type them into the Q&A box.
And if the individual questions have been addressed, then we want to invite all of the panelists to unmute themselves and turn their video back on, because it looks like we've got a little bit of time for a group conversation before we need to break before our next session. That includes upcoming speakers, as well as any of the Northwest Toxic Communities Coalitions and UW SRP folks that are in the room.
Good morning, David. I want to thank you very much for coming. One question I have is that we're dealing with a lot of industrial pollution in the Portland Harbor area. Basically, directly adjacent, we have millions of gallons of petroleum products being stored, transferred daily to the tune of something like 300,000 gallons and more of petroleum products being transferred into trucks and then transported out of town. The sources of the fumes, of course, are from the petroleum itself, and the tank farm operators say that they, of course, filter out and burn off any of those fumes, so they're non-toxic at that point. Do you agree with their view that the combusted petroleum product fumes are non-toxic once they're combusted?
Well, I most certainly do not agree with that view. And I've been involved in very similar issues. We have oil trains going actually through my backyard to the port of Albany, where they're being loaded on tankers to go down the Hudson River. And I've been very involved in a public housing project where primarily minority people live and are very concerned about this issue. Whether it's the pure product or the combusted fumes, they contain carcinogens, especially benzene, ethylbenzene. We've got strong evidence that just living near to a fuel-fired power plant increases the risk of leukemia and other diseases of the blood supply. You can monitor these things. We've also been involved in studies around fracking wells, fracking sites, find that emissions exceed federal standards, sometimes by 10,000-fold. And they're episodic emissions, but they're very high with compounds like benzene, formaldehyde, that are known human carcinogens. There are other studies that I haven't been personally involved in, but show that that neurotoxicity, headaches, brain fog, and in extreme cases, even almost an encephalopathy from inhaling low chlorinated volatile organic compounds that are found in both oil, natural gas, and after combustion of these compounds. So they're not non-toxic in any stretch of the imagination.
Thank you.
I just want to ask a question that came in the Q&A. It says, our major landfill here in King County, Washington is 80 years old, 850 feet deep with a 1,000-acre footprint. Millions of gallons per week of untreated landfill leachate flow into the receiving waters of the Cedar River, a major salmon habitat. Please consider including salmon from the Cedar River in your next study as a positive control. Thank you.
That's a good suggestion. If we ever have funding to do another salmon study, we'll remember the Cedar River.
Okay, one more question just came in. The Oregon DEQ has found detectable levels of dioxin in soils and neighborhoods near a creosote manufacturing facility. The agency has expressed concern and is continuing to test, but they are telling residents that there is nothing to harm humans through exposure to soil and dust. How should residents regard this information and the risk?
That information is a blatant lie. There is great concern and every reason to be concerned about that. I used to work for the New York State Health Department. Now I fight with them. I understand the dilemma that health agencies have, because there's some things that to do a cleanup is almost unrealistic. It's impossible, both from financial concerns and from the fact that there's some level of contamination almost everywhere. So that's a creosote plant. We have concerns locally around fuel-fired power plants, around hazardous waste sites. We've done a number of studies here in New York showing that if you live near a federal or state Superfund site, your risk of being hospitalized for a whole variety of different diseases, hypertension, asthma, diabetes, heart disease, your risk is greater than if you don't live near a contaminated site. Now, of course, we cannot provide housing for everybody in the world that's removed from sources of contamination. But I think it's just not correct, and it's to have any agency say that you don't need to be concerned about health effects when there's evidence of a compound like dioxin being present in that environment.
Thank you.
Anything else within our presenter and co-host group for questions or discussion? Okay, anything else from the audience? And I think we're going to take a little
David,
break. Oh,
I
sorry.
have an additional question. Excuse me. We are looking at situations now where we're measuring CO2 contamination levels from diesel trucks. That's just the tip of the iceberg as far as I'm concerned, but is this a good indicator? Basically, I'm in Oregon. Other states say, well, we don't want those old dirty trucks on the road, so get them off the road. Well, they just turn around and sell them to the guys in the next state because they can buy them for half price and drive them away and create huge clouds of whatever. But is CO2 a good, basically, measuring point for other contaminations that may be coming along with those old dirty burners that are also burning more than just diesel crankcase oil, for instance, and so forth like that?
Well, CO2 is going to be formed whatever you're burning. So it isn't just diesel. I think the more critical component of diesel exhaust are the ultrafine particulates, because diesel causes more of these ultrafine particulates that go deep in the respiratory system than do regular gasoline engines. But you're going to get CO2 from gasoline engines as well. Now, there clearly are great variations in the efficiency of combustion. And that's one of the reasons why the old cars and trucks, they don't get as many miles per gallon, because the combustion is less efficient. Therefore, they're going to generate both more CO2 and more of these ultrafine particulates. But, this is really, I think, why all of us are applauding the initiative from the Biden administration to get us away from burning fossil fuels, because it's going to not only increase the risk of climate change, but it generates particulates that are hazardous to our health in many ways, both respiratory disease and especially cardiovascular disease.
Thank you.
And it looks like we have an attendee with their hand raised. So maybe you can introduce yourself and ask your question.
Hi, this is Laura Feldman from the Portland Harbor Superfund site. I'm with the Willamette River Advocacy Group. Good to see you again, Dr. Carpenter. I remember seeing you a couple of years ago. And this is maybe less a question and just an update, a concern. So working on the cleanup, and then with an advisory group with other volunteers, I just want to report that EPA will not acknowledge that PCBs oxidize and become airborne and that we breathe them in. They won't go there. And I keep bringing it up, and it almost feels ridiculous at this point. They'll always hem and haw and say, well, we don't know. Well, we're going to look into that. And they just won't go there. And I'm just telling you this. I feel so hopeless about this. this reality. And I keep bringing it up like an old song, just for what it's worth. Thank you.
Well, I understand your frustration because I feel that as well. Now, there certainly are some people at EPA that actually read the literature and see the strength of the evidence for inhalation being an important source of exposure. I don't know what it's going to take to get EPA to acknowledge that. Now, there are lots of problems if they once acknowledge how important inhalation is as a route of exposure, because we have all of this evidence, a lot of it coming out of old schools, but it's really true in old buildings in general, that there is PCB containing caulk around all the windows and doors. There are PCB containing light ballasts in old fluorescent lights that are often leaking. And we're finding that PCBs that, in addition to being carcinogens, are neurotoxicants and reduce IQ and learning ability and attention span. They're in the air in these schools, in these older buildings. And often the amount of PCBs in that window caulking exceeds the amount that EPA has set at a standard where they have to be removed. The issue is that EPA doesn't say if you think they're there, you must test it. If you don't test it, you don't know that it exceeds 50 parts per million and therefore is officially hazardous waste and has to be removed. So that it's a major issue. I'm actually involved in a legal case for a school there in Washington State, where there are high levels of PCBs in window caulking and people have gotten ill because of that. It's a major problem, and EPA has simply got to acknowledge what the science evidence shows.
Thank you.
Great, thank you. Now someone is asking in the Q&A, which school? If you can.
Sky Valley.
What was that?
Sky Valley.
Oh, okay, thank you. Another question, can you comment on measures of synergism between EDCs and particulates?
Oh, ask me that again, please.
Can you comment on measures of synergism between EDCs and particulates?
I don't really know of any specific evidence where people have looked for endocrine disruptive chemicals in relation to particulates. Now, many EDCs are found on particulates, but particulates often contain a whole variety of things that are not usually rated as being endocrine disruptive. So I'm afraid I can't really comment intelligently on that to answer that question.
Okay, another question. Did you find differences in contamination levels in salmon organs versus the filet meat? That's from Richard Honor.
Well, the contamination is in the fat, not in the meat. And, that's actually a difference with the PCBs, the brominated flame retardants, as compared to the perfluorinated compounds, because the perfluorinated compounds are not lipophilic, but the PCBs, the dioxins, the chlorinated pesticides are. So that's why they're so high in salmon, because salmon is a fatty fish. Those red and white stripes, the white stripes are fat. And therefore, the more fatty the fish, the more likely there is to be higher levels of contamination.
Great, thank you. That's all the questions in the Q&A and with people raising their hand.
Okay. So if that is truly it, we can prepare to go to break. Our next speakers are going to be up at 10:50 sharp. which gives us about 15 minutes. And for those folks who, while we're on break, there'll be a break slide up, but for those folks who somehow got logged in with my name, I've renamed you Anonymous. And if you want to stick around during the break, we can try to get you correctly named. You may be able to do it yourself. If you click next to your name, you may have a rename option. And if you don't, I'm happy to stick around and help you with that during the break. So the whole schedule, Lisa just put up on screen. You'll see that we're coming back at 10:50 with Dr. Diana Rohlman and Briana Rivera from the Oregon State University Superfund Research Program. And we will see the rest of you back here then. Grab a second cup of coffee, take a bio break, and we'll see you shortly. Thank you. Those of you listed as anonymous, it looks like you're being successful in renaming yourself. Please go ahead and do that. If you're having trouble, go ahead. Oh, I see one of you has raised your hand. Two of you have raised your hand. Okay, one moment here. Okay, there's an anonymous person who I have permitted talking. Do you want to tell me your name and I will rename you?
Laura Feldman.
Okay, Laura, I think I've already renamed you.
Okay, thank you.
Go ahead and take your hand down. There's another anonymous person with their hand up who I have allowed to speak up. You want to tell me your name? Hello? Okay, I'm going to go to someone else.
There we go.
Okay.
Okay. Hey, BJ, it's Heather.
Oh, great. Hi, Heather.
Is there any reason we can't have everybody showing and get everybody upgraded to panel? Is there too many people, or what is the?
Yeah, this is a webinar, not a meeting.
Oh, okay. Well, how do we know who all's here? Maybe you could shoot that out to us or something.
Yeah, I don't think that's visible to all of the attendees in webinar.
No, it's not. No.
Yeah, so that's how Newt's decided to broadcast this event for a variety of security and other reasons. But yeah, thank you for letting me know. I've got you now identified properly. Welcome, Heather.
Hello.
Let's see. There we go. Who is this?
Hello, this is Fran Solomon. Can you hear me?
I can. I'm going to rename you. Thank you, Fran.
Thank you. Do you need a spelling of my last name?
I don't think so. I know you, but tell me if I've got it wrong and I will.
Is this BJ?
It is. Hello.
Oh, hi. It's nice. Hello, it's nice to see you. I'm glad to see you with the UW Superfund program. That's great.
Thank you. I'm glad to be here. Is it SOLOMAN, Fran?
It's MON.
MON. Great. Thank you.
Thank you so much.
Of course. Thank you. Glad you're here.
Me too. First talk was very informative, and I look forward to the others. Thanks for renaming me.
Hey, BJ.
Yeah.
So is it, it may be because I'm a panelist. I can see all the attendees. There's two different groups you can click on, one panelist and one attendees.
That's correct. I'm
Attendees can't
Naming
see
the
it.
anonymous attendees right now.
But the attendees can't see the list.
That's correct.
Okay. And can they ask their own questions?
Yes, they just need to raise their hand and then we can unmute them. We've been doing that. Lisa was doing that.
Well, I think Lisa asked most of the questions. Is that because folks didn't want to ask them themselves, or is
Right,
that
they put those in the Q&A box.
okay? We should probably encourage people to ask their own. if
We'll
they
ask
can.
Lisa to do that. Great,
Okay.
thanks. Okay, I have one more anonymous guest to rename. Do you want to identify yourself? Hello? If you're still listed as anonymous, you can let me just, you should be unmuted. You're able to unmute yourself at this point and tell me your name. Okay, you probably have stepped away, so I'm going to go ahead and mute you again. And we're back. John, you're up.
All right. First of all, I'd like to acknowledge Lisa Arkin being in the audience from Beyond Toxics and James Rasmussen being here from the Duwamish River Network. I'm introducing Diana Rohlman and Briana Rivera this afternoon. Their title is going to be Current Approaches to Characterizing Chemical Mixtures. Ms. Rivera is a fourth-year doctoral candidate in the Department of Environmental and Molecular Toxicology at Oregon State University. She is currently working in the labs of Doctors Kim Anderson and Susan Tilton. Her research focuses on identifying and characterizing chemical mixtures. Briana investigates sources of environmental contaminants and their potential impacts on human and animal health through sampling of air and water both. She develops methods to form representative mixtures from environmental exposure data and investigates potential health effects associated with exposure to these mixtures. Dr. Diana Rohlman is the Assistant Research Professor at Oregon State University in the College of Public Health and Human Sciences. She directs the Community Engagement Core of the Pacific Northwest Center for Translational Environmental Health Research and co-leads the Research Translation Core of the Superfund Research Program. Her research focuses on using environmental health literacy to help communities better understand and respond to environmental health hazards such as disasters and proximity to Superfund sites. As a public health toxicologist, she works with interdisciplinary teams to tackle large-scale problems such as chemical exposures from disasters, such as hurricanes and forest fires, or impact of air pollution on asthma using community-engaged methodologies. Dr. Rohlman holds a PhD in toxicology from Oregon State University and also conducted a postdoctoral training there in the College of Public Health and Human Sciences. She received her bachelor's in science from Marietta College in Ohio. Welcome, Briana and Dr. Rohlman.
Thank you so much. And so I start every talk with the apology in advance. I have a snoring elderly dog in the background. So if you hear snoring, it's just that my dog is not very impressed by my career choices. So my apologies in advance. So Briana and I are going to be talking to you today about some of the research that our center does. So I'm going to do kind of a brief introduction, sort of situating our center and the work that we do. And then Briana is going to give you a deep dive into the work that she's doing with pH mixtures. So again, thank you so much for the invitation to speak today. We're really looking forward to this. Next slide, Bri, please. Thank you. So as John said in his introduction, thank you. Both Briana and I are part of the Oregon State University Superfund Research Program. So we are down in Corvallis, Oregon. Every single research center we have has very long titles, so I apologize in advance. What this image is showing, we asked the graphic designer to sort of visualize the opportunities for collaboration that we have across the United States. And so like the University of Washington, you can see their Superfund Center on this map as well as us. We have a lot of these centers across the US, and this map is showing them organized by EPA region. What's really impressive about these centers, so we're all funded by the National Institutes of Environmental Health Sciences, it gives us the opportunity to collaborate with other centers to address large-scale problems as they relate to Superfund sites and toxic waste sites. So we're able to share our research and learn the research of others, which I think I just wanted to highlight that as one of the strengths of our program and how that's influenced some of the work that we've done. So next slide. So with that, recognizing that there's at least 18 of these centers, each center sort of has its own flavor of toxic chemicals that they choose to work with. And so we selected polycyclic aromatic hydrocarbons, or PAHs. And the goal of our center is to detect these chemicals in the environment, to figure out how we can clean them up from the environment, or also figure out what are they doing to the environment and to human health. So in order to answer those questions or to even start addressing them, we've brought together a group of scientists from fairly different backgrounds. So we're a group of toxicologists, biologists, chemists, public health researchers, and data scientists. And we're all trying to tackle these problems and bring to bear our different scientific expertises on that. So next slide. So while I said that we focus on polycyclic aromatic hydrocarbons, that is true. I want to acknowledge that we do realize we are exposed to more than just one chemical or one type of chemical. So on the right of this slide, you're seeing an infographic that we adapted from the National Institutes of Environmental Health Sciences. And this is just showing some of the different contaminants in our environment that people might be exposed to at any given time. So this can be chemicals in vehicle exhaust, this can be heavy metals, chemicals in cigarette smoke, pesticides, flame retardants, and then of course, polycyclic aromatic hydrocarbons. So I bring this up because traditionally in toxicology, we have tested a single chemical at a time. We've said like, all right, chemical A, we're gonna test that. We're gonna see what it does. Now we're gonna go to chemical B. The issue is that's not reality. We know that we're exposed to more than one chemical at a time, and there's these mixtures. But when you start trying to look at someone's exposure to multiple chemicals across multiple chemical classes, that gets really complicated. And I think Briana is going to talk about the complications that arise when we're just looking at mixtures of PAHs. So in this talk today, and for what our center's been doing, we've really been looking specifically at mixtures of PAHs alone, with the idea being that if we can figure out how PAHs in a mixture are interacting, we can figure those methods out and then ultimately start applying them to more complicated mixtures of multiple chemical classes. And I'll let Briana talk a bit more about that perhaps towards the end of her talk. So you might be wondering why we focus on polycyclic aromatic hydrocarbons, other than the fact that they're just fun to say. From a scientific standpoint, we know that they are found in over 40% of Superfund sites. Now, I know that might not sound super impressive right away. The last time this was characterized was 1995, and there's unfortunately been more sites added, and unfortunately, many more advances in our ability to detect chemicals. So also note that PAHs are not routinely tested for at every single Superfund site. So it is very likely that we're seeing these chemicals at many more Superfund sites and toxic waste sites. We also know they're ubiquitous in the environment, meaning that you can pretty much find PAHs anywhere you go. And that's not necessarily a bad thing. As a toxicologist, we're always interested in how much is going to be there. But I want to talk a little bit about how they're actually formed. So the scientific definition is formed from incomplete combustion. The easier way to think about it is anytime you're burning organic material. So a wildfire where trees are burning, that is going to produce PAHs. Volcanoes can produce PAHs, but also industrial pollution or car exhaust where you're burning gasoline will produce these chemicals. And then finally, we're starting to learn quite a bit more about the health effects that these chemicals can cause. And it can be across quite a range of endpoints. So the most infamous PAH, in my opinion, is benzoate-pyrene, which we know is a carcinogen. So that tends to be the health outcome that is focused on the most with PAHs, but there's several other health outcomes that we also tend to look at. So next slide, please. I always like to put this slide up because it's a reminder, I think to me mostly, that while we do focus on PAHs largely at Superfund sites and toxic waste sites, we're also interested in characterizing PAHs from just sort of the everyday life activities. And so this is showing just different areas in everyday life that PAHs might be created. So in small oil spills from smoking cigarettes, even grilling food. If you're a fan of charbroiling your meat and getting it nice and blackened, that nice blackened area actually has quite a few PAHs in it. So looking at what are some of these maybe smaller scale exposures, but that are happening much more routinely is something that we're also very interested in characterizing. So with that, I've been talking about polycyclic aromatic hydrocarbons, but I wanted to give you a little bit more background on them. So this is a snippet of an infographic that we developed a few years ago. And I wanted to sort of situate more some of the different variables that go into making mixtures complicated. So as I said, they're formed from incomplete combustion or just the burning of organic materials. Like all chemicals, their toxicity does typically depend on how a person is exposed. So if you breathe it in, if you eat it, drink it, or if you touch it, how much you're exposed to, and then the type of pH that you're exposed to. And today, and I'll let Briana correct me on this, but I believe she's going to be talking mostly about the type of pH that we're finding in mixtures. So there's a couple of reasons why we're very interested in the type of pH. Not all pHs are equal in terms of toxicity. And it also comes down to the question. So we could test any mixture, right? We could say like, we're going to contaminated site B, we've taken a sample, we've tested it, and it's toxic. And that's useful information, but that's really only half of the test that we need to do. Because if we know something is toxic, usually the next question is, okay, well, how do we clean it up? Or how do we tell people to reduce their exposures? And in order to get that information, we need to figure out which chemicals are actually causing the toxicity, or which chemicals are interacting in such a way as to cause toxicity. So again, to give you an example of these different toxicities, I think most people are probably familiar with naphthalene. It smells like mothballs, largely because it actually used to be used in mothballs. Well, so that chemical in very high doses is associated with dizziness, nausea, headaches, that sort of thing. So definitely not good health outcomes, but very different from the toxicity of benzoate pyrene, which is carcinogenic. So that is one of the reasons why we do, or why I harp on the importance of looking at the type of pHs that's there. That is how we can figure out how to clean up contaminated sites or protect human health. So with this next slide, I believe perfect, repop that up. We affectionately call this the ball of yarn. It looks pretty messy, and that's actually kind of the point. So to orient you to what we're looking at here, every single dot that you're seeing on the screen actually represents a pH. So at this point, we had a screen for 62 different pHs. And these are environmental samplers that we've put into this image from various different studies. And what you're seeing here is how many times we found each pH in the environment and how often it appeared with another pH. So when you see those really thick lines connecting two dots, that means we very frequently find these two pHs together. Down in the bottom right, you can see one pH has really thin lines, so we're not seeing it as often, and we're not seeing it with these other pHs. The bottom line of this image, though, is I'm visualizing what a mixture can look like. So mixtures are complicated and they're really messy. And so we're very grateful that Briana has decided to take on this struggle of characterizing these and figuring out what's the best way to try and untangle this massive ball of yarn so that we can get useful information from it. So for my last slide, before I turn it over to Briana, I want to just give you a little bit of background on where our center is currently in terms of what we can study. So we're currently able to look for 65 pHs, and this can be in the air, in the water, in the soil. 65 might not sound like a great deal when I tell you that there's hundreds of pHs, but traditionally it's been around 20 pHs that were analyzed. So we've been able to pretty significantly expand the suite of chemical analytes that we're able to look at. We're also able to look at pHs that haven't been studied as much. But once we find out that they're in our environment, we can say, well, if they're there, let's learn about them. Let's learn if this is something we should be concerned about or not. There's also been work in our center done, and I don't think Briana's going to talk about this today, but we can take some questions towards the end, or if we can't answer them, I can always send out information later. But we've been able to do some work on source identification. So are these pHs that are more likely coming from natural sources like wildfires, or are they more likely coming from industrial sources? And that, again, gets back to the type of pH that we're seeing that can help inform that analysis. So with that background on what our center studies and the rationale for selecting pH mixtures as our sort of analysis point, I'm going to turn it over to Briana, who is sort of the expert in this section. Thank you.
Thanks, Diana. Thank you very much for that really lovely introduction on pHs and our Superfund program, as well as some of the complexities of studying mixtures. So as Diana had alluded to, for the remainder of this talk, I'm going to focus on pH mixture safety assessment. having difficulty advancing my slides. Okay. So for this talk, I'm going to start by giving you all some background, talking about how pH mixtures are currently assessed. I'll then discuss an alternative approach to mixture safety assessment by describing some work that we've been doing with an approach called representative mixtures. And I'll be covering some previous work that we've been doing with this within our SRP program. And then I'll conclude this talk by discussing some ongoing work that we've been doing with representative mixtures. So first, I just wanted to really orient you to some of the impacts of this work. And one of the main impacts that we're trying to achieve is to provide regulators with a more feasible way to conduct mixture safety assessment. So current approaches to mixture safety assessment typically involve considering one chemical at a time. They also only take into account one type of chemical interaction. And due to this type of approach and these assumptions, sometimes the risk of exposure to these mixtures can be underestimated, and sometimes they can even be overestimated. And so there are some additional approaches that are currently being used where a researcher or an individual will go and collect an environmental sample from a contaminated site, and then they'll bring that sample back to the laboratory and evaluate it for toxicity. This type of approach is useful due to the fact that it does take into account all types of chemicals that may be present at the site, as well as potential mixture interactions that may be occurring. However, one of the main limitations of this is that you're not able to easily parse out which chemicals within this mixture may be driving toxicity or may be of most harm. And so really, in order to have an actionable remediation plan, you need to know, or regulators need to know, what types of chemicals are in the sample that are of most concern and need to be reduced or removed. And so our objectives are to investigate new approaches to mixture safety assessment. Not only are we trying to investigate these new ways, but we also want to try and provide a framework where this type of approach that I'm going to be talking about today may be useful for more complex mixtures. So as Diana had talked about earlier, our program is largely focused on PAHs, or polycyclic aromatic hydrocarbons. And so this approach is more focused on PAHs, but we're hoping that this approach can be applied more broadly to chemicals that have multiple different types of chemical classes within the mixture. And so with this approach, we also intend to prioritize chemicals of most concern in a mixture. And this will allow us to inform regulators on what types of chemicals within this complex mixture are the ones that need to be addressed and removed at a remediated site, or at a contaminated site, sorry. And so what is the current process for pH safety assessment? Well, it first starts off with identifying a contaminated site. In this instance, we have a factory that appears to be contaminating a waterway. And then after the contaminated site is identified, environmental sampling occurs. And so this primarily is to identify what types of chemicals are at the site, as well as the concentrations that are present. So then the sample will be taken back to the laboratory, and it'll be characterized, meaning that they'll identify what types of chemicals are found in this sample. So typically with this type of approach, the regulators have some kind of idea of what chemicals might be present at this site. And so they do something which is called a targeted screening, meaning that they'll look for a specific chemical class. And while this is very useful, there are sometimes, with this type of approach, it is possible that they may be missing some types of chemicals that are present at the site, but are missed due to this targeted method. And so after they identify what types of chemicals are present, they collect toxicity information for each of these chemicals. And so this is largely found on publicly available databases from either state or federal agencies. And another limitation of this, with this type of approach, is that there isn't currently toxicity information available for all chemicals. And so you can only use in your safety assessment chemical toxicity information for which you have, or when chemical toxicity information is available. And so after this information is collected, the overall mixture safety assessment occurs. And so the way that this is traditionally done for PAHs is using this assumption of additivity. And so if you had tuned in on into David Carpenter's talk, he kind of touched on this a little bit about what the assumption of additivity is. But in case you are just tuning in now, so essentially what you do is you take the toxicity of each individual chemical and you sum them together. And then the sum toxicity is predictive of what the toxicity of the whole mixture would be. However, this assumes that PAHs only interact with each other in an additive way. And so only accounting for this one type of mixture interaction isn't necessarily appropriate. At this point, we do know a lot about PAHs and that they don't interact in just one way. And so this current approach often under or overestimates mixture toxicity. So next, I'm going to go into the different types of mixture interactions. And so as I talked about in the last slide, the first and general kind of rule of thumb is that PAHs respond in an additive manner, meaning that in this graphic that I have here, the response of chemical A, which we're seeing is around 2, and then we have the response of chemical B, which is around 4. And then when you would put them together into a mixture, you would expect the overall response to be around 6. And so the next approach is something called synergy, or more than additive, which many of you may be familiar with since this is one of the focuses of the summit. And so this approach, again, you would have the response of chemical, or this type of interaction. So again, you would have the response of chemical A, which is around 2, and the response of chemical B, which is 4. But in this case, the overall response when they're combined is around 15. And so what's happening here is these chemicals, when they're put into a mixture together, they're interacting in a way where they're amplifying. We're seeing an amplified response. And the last type of interaction, which you may be a little bit less familiar with, but Dr. Carpenter had also touched on this, is something called antagonism. And so again, you would see these individual responses, but then when you combine them, they're actually inhibiting each other. And so in this case, we would see 2 + 4 = 1, for instance. So now that I've touched on the current approaches to safety assessment and some of the types of mixture interactions, I just want to really orient you and give you some more information on the different types of approaches that are available and give you some background on the a type of approach that I'll be focusing on today. So the first type of approach, which I had touched on with the overall view of what's currently done, is that it's called a component-based approach. And so the way that this works is that you use individual chemical toxicities in order to predict the mixture toxicity. And so, as I said before, this assumes additivity, and which means that you're only considering one type of mixture interaction, and that this method can under or overestimate risk. Additionally, this type of approach requires a comprehensive database of toxicity information. So as I said before, if you're lacking toxicity information, then you're not able to take that chemical into account for your overall assessment of mixture toxicity. The next approach is called a whole mixture approach. And so the way that this approach works is you would take a whole environmental sample and then return it to a laboratory and conduct toxicity tests on that sample. And so, as I had to discuss before, this is useful due to the fact that it does take into account potential mixture interactions, as well as the types of chemicals, all types of chemicals that may be present at this site. However, it is expensive due to the use of the whole chemical extract. Additionally, it's hard to parse out the drivers of toxicity with this type of approach. So as I kind of touched on before, it's really what we're trying to get at with this type of with these safety assessments for mixtures is, at this contaminated site, which types of contaminants are we trying to regulate? Which ones are of most concern to our health? That's really the type of information that regulators need. Additionally, with this type of approach, there are an infinite number of ways to form these mixtures, or there's you would get all different types of mixtures depending on when you would sample, and also depending on the different sites. So if we were to conduct this type of approach every single time, it's not necessarily feasible. And so the last approach that I want to touch on is something called representative mixtures. And essentially this serves as a compromise between the component-based and the whole mixture approach. And so the way that this approach works is that you're creating a mixture that is synthetically made, meaning it's created in the laboratory, and you can use that mixture. It's representative of the whole mixture, or the mixture that's found in the environment. Additionally, this type of approach does maintain environmental ratios, meaning that the proportions at which these chemicals are found in the environment is maintained. Additionally, this approach, some of the limitations of this approach are that it only contains your chemicals of interest. So going back to how that safety assessment was conducted, you're using a targeted method. So you're only identifying chemicals that you were looking for in your sample. And that's typically how this type of approach is formed. You can also have different chemical compositions based off of the approach that you use, which I'll touch on more in some of the later slides. And so for the remainder of this talk, I'm just going to be focusing on representative mixtures, some of the work that we have done in the past with representative mixtures within our SRP program, and the ongoing work that I've currently been doing. So how does a safety assessment work for using representative mixtures? Well, it starts off very similarly to a traditional safety assessment, where you have a contaminated site. You go and collect an environmental sample, and then you return that sample to the lab, and you identify what types of chemicals are in that sample. And as I had said, this is more of a targeted method, so you're typically looking for a specific class of chemicals based off of the information that you knew on at this site. And so this mixture is called the mixture of interest, or mixture A. Next, you identify a representative mixture. And so there's two different approaches in which this can be used. The first is that you identify an existing mixture with known toxicity information, meaning that someone had already created a representative mixture and have collected toxicity information on it, and this mixture may be similar in chemical composition as your mixture of interest. The next approach is where you would create your own representative mixture. So you would identify, you would use one of these approaches, which I'll touch on the next slide, and you identify which chemicals you want to put in that mixture that you think sufficiently captured the chemicals in your mixture of interest. And so with either of these approaches, you have to compare the chemical composition of mixture A to mixture B. And then if you do determine that these chemicals are similar enough, or that the chemical composition of these two mixtures is similar enough, then you can use the toxicity information from mixture B to conduct your safety assessment of mixture A. So what are the different types of representative mixtures? The first type is an exposure-based approach. And so what this means is you're identifying which chemicals are at the highest concentrations in your environmental sample. And what I mean, and I had termed this exposure because these chemicals at higher concentrations are the ones that you're most likely to be exposed to. The next type of approach is a toxicity-based approach. And the way that this works is it does vary depending on the metric that you use to determine toxicity. And so this could be based off of how the chemical responds within the body. It could also just be simply based off of the potential to cause harm. For instance, using toxicity values that may be used in traditional risk assessment. And then the last approach is this exposure and toxicity-based approach. And so this is an approach that we're currently exploring, where essentially what it does is it scales this toxicity information based off of chemical concentrations. This has typically been used in ecological risk assessment, but to my knowledge, it has not been used for human health risk assessment, particularly for trying to prioritize components that may be driving toxicity to form representative mixtures. And so next, I'm going to move on to some of the previous work within our SRP program on pH representative mixtures. And so the first time that our center had started to kind of tackle this question regarding how we can simplify complex mixtures and form representative mixtures for more feasible toxicity testing was through this project, which we called, which I'll be referring to as the SuperMix project. And the way that this project worked is we had conducted sampling at Portland Harbor Superfund site. Specifically, we did sampling in the water. And due to the knowledge that we had of this site, we decided to focus on PAHs. And so these samples were evaluated for 63 PAHs, which was the method that we had at the time. Since then, we have added 2 more PAHs. And the authors, Mitra Geyer and Jamie Minnick, who were previous grad students in our program, they identified the 10 most abundant PAHs, and so this is seen as the exposure-based approach. And so before I go into the details of this project, I do want to orient you to the graph that I have here on the right. And so what we're seeing across the bottom are biological endpoints. And then this bottom half of the graph is the different types of mixtures. And then the top portion is the individual PAHs. And so really what I'm trying to show you here is which of these chemicals and which of these mixtures had caused a biological effect. And so if you're seeing a white square, that means there was no effect. And if you're seeing a black square, then that means there was an effect. And so the authors of this project had chosen these 10 PAHs that were highly abundant in the water at Portland Harbor Superfund site. And they had created a mixture from this. They called this the SuperMix 10 or the SM10. They then were trying to identify, okay, of these 10 compounds within this mixture, which of these chemicals are driving toxicity? So this can be seen as the toxicity approach. And what they did in order to try and answer that question was they screened these the individual PAHs that were in that SuperMix 10, and they evaluated it for different biological endpoints. After that, they had created 2 submixtures. The first was the 3 components that did cause an effect in zebrafish, which can be seen here. And they called that the SuperMix 3, which can be seen here. The next was the 7 PAHs that did not cause an effect when screened individually. And that was called the SuperMix 7 or the SM7, which can be seen here and here. What's really interesting about these findings is that when screened individually, the SuperMix 7, none of these chemicals had caused effects. But when they were combined into a mixture, there were different types of results seen. And so I want to zoom in on this and really highlight just one kind of biological endpoint example. And so as I said, we're seeing no effect here for individual screening. But then when we combine these inactive components into a mixture, we are seeing a biological effect. And so this can be suggestive of synergy. Additionally, it does get at the point that when you screen these chemicals individually, that individual toxicity information is not necessarily predictive of mixture toxicity. And so some of the main takeaways of this work, this really was our center's first approach to try and identify drivers of toxicity. And so the authors of this project, Mitra Geyer and Jamie Minnick, they started off with this exposure approach where they had chosen those top 10 PAHs, and then they tried to use this toxicity-based approach to identify the drivers of toxicity. However, what were some of the really important findings here is that we identified that individual toxicity information is not always predictive of mixture toxicity. What another highlight of this is that depending on these different types of approaches, you may have different conclusions. So if they had decided just to screen those chemicals individually and not put them into a mixture, they might have had different conclusions regarding some of the potential concerns with the PAHs that were found at that site. And so this information really informed my research to try and explore different types of approaches to form representative mixtures. So next, I'll cover some of the work that I've been doing currently with pH representative mixtures. And so before I delve too far into the project, I really wanted to orient you with some of the questions that we had going into this and some of the objectives. And so with the supermix study, as I said, that was kind of our center's first way to simplify complex mixtures. So we wanted to continue to try and answer this question. So what are the different types of approaches that we can use to take these complex environmental exposures and really try and narrow them down for more feasible toxicity testing? And so in order to get at that question, we intend to explore different approaches to form representative mixtures. And we also have seen in the supermix study that depending on the approach that you use, the composition may be different. So another objective is to try and identify and compare the different types of compositions based off of these different approaches. So the next question that we were trying to answer is, which method best represents the response of our mixture of interest? And so in order to address this, we will create these representative mixtures, and then we will evaluate them for biological endpoints. And then we will compare the response of these representative mixtures to our mixture of interest to identify which of these representative mixtures may most sufficiently represent our mixture, or the response of our mixture of interest. We also intend to evaluate the different types of responses that are seen from these different mixture formations to see if some of these mixtures may be under or overestimating risk depending on the approach. And so for this study, we conducted sampling at a legacy creosote site. Particularly, we decided to do, I had chosen to use air samples. And due to our knowledge of the chemicals that are highly present at creosote sites, we decided to focus on PAHs. And so these samples were evaluated for 65 PAHs. And of those 65, 32 PAHs were identified. So the overall workflow started off with environmental sampling. So we had gone to this legacy creosote site, deployed our samplers, collected the chemicals present in the environment. We returned those samples to the laboratory where they were processed and those chemicals were extracted from the sampler. And then we, once we had gone through that process, they were analyzed on our instrument for PAHs. And then once we were able to identify which PAHs were found in our sampler, we collected toxicity information. And so this was collected through federal and state databases, and also an effort through our SRP program is to identify chemicals, or is to collect toxicity information for individual chemicals that are in our 65 pH method. So we were able to use that zebrafish information as well. And then after that, we formed different representative mixtures and evaluated them for, and tested these mixtures for toxicity in zebrafish or in human lung cells. So next I'll be talking with you about some of the different formations of these simple pH mixtures. So we explored several different approaches, and what we started off with was this real world exposure, which I'll be calling the creosote mixture. And so as I discussed in some of the previous slides, we know that people aren't just exposed to pHs. However, due to our knowledge of the site and due to the objectives of our SOP program, we decided just to focus on pHs. And so we know that there's other chemicals besides pHs here, but we just focused on pHs, and we created a simple mixture based off of pHs that were identified in that sample, which I'll be calling the simple creosote mixture. And then from there, this is what I'm terming our mixture of interest. And so based off of the information that we had on our mixture of interest, we formed different representative mixtures. The first being the exposure mixture, which is similar to the approach that we saw at in the supermix study, where we identified the most abundant chemicals that were found in our mixture of interest, or the simple creosote mixture. The next approach is the toxicity mixture. And so the way that this approach was used is we prioritize components strictly based on available toxicity information. And so we collected toxicity values from federal and state databases. We also incorporated that zebrafish information. And where we didn't have available toxicity values, we had used a predictive model, which was able to give us toxicity values, which generated toxicity values based off of chemicals that had similar structures. And then the last mixture is the exposure toxicity mixture. And the way that this worked is it incorporated both chemical concentrations as well as toxicity information. And so we scaled the toxicity values based off of their chemical concentrations found in the simple creosote mixture. So next, I wanted to discuss some of the composition of these simple pH mixtures. And so don't worry too much about the chemical names here. Really what I'm trying to show is the chemical composition, which can be seen by the sizes of these blocks as well as the colors. Additionally, anything that can be easily seen was in greater than 3% of its respective mixture. And then each of the representative mixtures was composed of 7 pHs, and the simple creosote mixture was, consisted of 32 pHs. So what we can see from the simple creosote mixture is that of these 32 pHs, we can only see 7 of the chemicals. And what that's really getting at is that we found 32 chemicals, 32 pHs in the simple creosote mixture, but there's 7 that are making up a large portion of that mixture. And so what we're trying to, and so in order to try and address the question, is it these 7 chemicals that are at really high concentrations in this mixture that are driving toxicity? We decided to form this exposure mixture, which can be seen here. And so this mixture here is composed of these 7 pHs that were found in the simple creosote mixture. And we can see that the proportions were largely maintained. So in the simple creosote mixture, we're seeing approximately 40% of the simple creosote mixture is composed of naphthalene, and we're seeing that maintained in the exposure mixture. The next approach is the toxicity mixture. And so as I said in the last slide, this approach is largely based off of available toxicity information. And so really this approach is targeting those chemicals that are in the lower 3% of the creosote mixture, or that can be seen down here. And so what we're seeing with this mixture is we're largely seeing naphthalene completely drop out, or any of these chemicals that were found in high abundance. And we're seeing the presence of chemicals such as retine, which is in purple here. We're also seeing that retine is making up a large portion of the composition of this mixture, which means that it was largely prioritized based off of the available toxicity information as being a chemical of potential concern. The last approach is the exposure toxicity approach. And so what we're seeing here, as I said, that we had scaled toxicity information based off of their chemical concentrations. And so we're seeing that a large portion of this chemical is composed of 3 pHs that were found in high abundance, which can be seen in the exposure mixture and the simple creosote mixture. We are seeing, however, that naphthalene was largely dropped out, which means that that wasn't necessarily a chemical that, based off of the available toxicity information that we had, was of potential harm. We're also seeing that there were 4 additional chemicals that were at really low concentrations in this exposure toxicity mixture. So after we created these representative mixtures, we evaluated them for biological effects. And so due to our study design, we have not yet screened the simple creosote mixture, but we do have information on the different representative mixtures. And so, so far we have tested them for one biological endpoint that I have here. And we're seeing for the exposure mixture, what you're seeing in the graph here, what we expect to see is that with increasing dose, you would see the line go up, meaning that as the concentration of this mixture increased, the biological response would also increase. And so for the exposure mixture, we're largely seeing a flat line here, which means that we're not seeing a response at this point with this biological endpoint from exposure to the exposure mixture. The next the next mixture that we've tested was the toxicity mixture. And so here we are seeing, with increasing dose, we're seeing that line go up, meaning that we were seeing a response. This isn't incredibly surprising to us, as we did prioritize this mixture based off of toxicity information. So we did expect it to be to cause a response in our lung cells. And so last but not least, we had the exposure toxicity mixture. And so again, what we're seeing is that with increased dose, we're seeing that response increase. So what's really interesting about, well, one of the things that's interesting about this is when we compare the toxicity mixture to the exposure toxicity mixture, based off of the information that we have available, we're seeing a steeper line, which means that it would cause a lower dose, or you would need a lower dose of the exposure toxicity mixture to cause the same effect in the toxicity mixture. What's also really interesting about this is that, let's go back and look at the exposure toxicity mixture composition. A large portion of this mixture is composed of chemicals that overlapped with the exposure mixture. However, we didn't see a response in the exposure mixture, but we are seeing a pretty significant response in the exposure toxicity mixture. And so this could be an indication that less abundant but more potent chemicals may be driving toxicity. And so it's those chemicals it was those 4 chemicals that were at low concentrations, but were likely maybe more potent or more toxic, that could be driving these responses that we're seeing. And so, so far, these results do show the different types of responses that we can get based off of the different approaches. So if we had just prioritized based off of exposure, we may have been underestimating the type of the type of response that, or the type of potential harm that the composition of these PAHs may be causing. And so some of yeah, we could get different, we can have different conclusions based off of the different types of approaches that we use. So some of the future directions for this project, we intend to also screen for additional biological endpoints using our lung cells. And we also intend to screen these mixtures in zebrafish. Once we collect all of that biological information, we intend to compare the responses of these different mixtures to each other, as well as to the simple creosote mixture, to try and identify which of these representative mixtures best captures the response seen from the mixture of interest. So what are some of the main takeaways from this project? So far, this is the first project to our knowledge that has conducted a comprehensive comparison of different ways to prioritize drivers of toxicity, and also compare these different representative mixtures to the mixture of interest. And so we're trying to provide additional information to advocate for the use of representative mixtures as an alternative for mixture safety assessment. We also see from some of our preliminary data that less abundant chemicals are likely driving toxicity, particularly the responses that we were seeing in the exposure toxicity mixture. And so with that information, we would like to, one of the main takeaways is that chemicals that are both high in abundance and toxicity should be prioritized. I do want to touch on some of the limitations of this work. So as I discussed before, this framework used a targeted approach. We just focused on PAHs. However, our intent is that this could lay the foundation for regulators to potentially adapt this type of approach for more complex mixtures that included multiple chemical classes. Another limitation is that due to our sampling design, we may be missing other environmental chemicals. And this is also related to us using this targeted approach as well. So for instance, our samplers don't take up metals, so we wouldn't be able to incorporate that into our approach. Additionally, similar to how the component-based approach is limited by available toxicity information, this approach is also limited by what type of toxicity data is available. However, a way in which we addressed this was to use predictive models, which were able to predict toxicity values based off of chemicals that had similar structures. And so I see this as being a potential solution for addressing this data gap that we have where we're missing toxicity information. And I see this as being an area that continues to improve. So I also just wanted to touch on some of the future directions for the field of mixtures, particularly with in the context of representative mixtures. So there are thousands of chemicals that exist in commerce, but only a fraction of them have been tested. And so we really need to kind of address this. We need to find different types of approaches that can be used to try and collect additional toxicity information. And individual testing hasn't, based off of some of the data that I've shown you today, isn't incredibly informative for whole mixture safety assessment, particularly in the context of using these component-based approaches, since it only takes into account one type of mixture interaction. And so we've provided representative mixtures as a feasible approach to whole mixture safety assessment. Not only does this account for types of mixture interactions and maintains these different proportions that are representative of whole environmental samples, but it also prioritizes chemicals of most concern, which are informative for actionable remediation plans. And additionally, we need approaches that can be used to extrapolate from one mixture to another, since it's not feasible to try and test every single possible mixture. And so representative mixtures also serve as a potential way to address this. As I touched in the really early slides about different types of representative mixtures, not only can you form your own representative mixture like we did in our projects, but you can find mixtures that are similar enough that can be used to extrapolate from one mixture to another. And so with that, I would just really like to acknowledge my funding sources, the NIHS and the Superfund Research Program. I'd also like to acknowledge my lab members in the Food Safety Environmental Stewardship Program, as well as the Tilton Lab. A special thank you to my advisors, Kim Anderson and Susan Tilton, and a big shout out to Diana, who's been a huge help in helping me distill down my information, the information from my project to communicate it with you guys today, as well as all of the different grad students and staff that have been involved in this project. With that, I'd like to thank you all for your time. I provided my information as well as Diana's information if you have any additional questions or would like to shoot us an email. But we'll also open it up for questions at this time as well. So thank you.
Thank you, Briana and Diana. There are several questions. So we'll start off, was there a reason to ethyl naphthalene was left out of the exposure mixture?
That's a very good question. Yeah, so the reason why that one was left out was actually due to availability of the standard. Sometimes that happens, it's unfortunate. But that particularly those types of chemicals, the ones that are alkylated like that, are sometimes really hard to get at, are hard to obtain, which is also a limitation of this type of approach.
Okay, thank you. Briana, do you find masking of toxicity when the mixtures become too complex, wherein some toxicities are nulled by in situ chemical reactions that deplete the relative toxicity of a key known chemical? And that's from Richard Honor.
So, I mean, that hasn't been a large focus of my work, but due to some of, I have read some studies that have talked about that, where they've investigated really complex mixtures and have added like certain types of carcinogens, and they do see a decrease in response due to in more complex mixtures compared to more simple mixtures.
Great, thank you. Just a comment from Lisa Arkin. She says, fabulous study. Thanks to your team for this important work. Yeah, and then a longer question. Wouldn't it make sense in using a representative mixture approach to use an actual whole mixture approach as a quality control measure against the representative approach assumptions? We found this is an issue at Western Processing, where they did toxicity panels based on sediment mixtures, which showed much higher toxicity than assumed by their assumptions based on levels of indicator chemicals they assumed to be the drivers. Wouldn't this also provide some level of information about whether other chemicals and interactions outside PAHs are causing effects changing endpoint toxicity? For example, interactions between PAHs and toxic metals. Excuse my voice.
Do you want me to take that first, Bri, or?
Yeah, you can go ahead.
So I don't know who asked that, but you've pretty much pinpointed the entire purpose of doing mixtures toxicity. So thank you. The short answer is yes, right? We do want to get to a point where we can plug in an entire whole mixture and figure out the toxicity and figure out which components are leading to toxicity. It kind of goes back to that ball of yarn, though. We are trying to tease out pieces to better understand how do you address interactions between pHs and PCBs, for example. The issue right now is we can't even figure out how PAHs alone are interacting. So the hope is if we can figure out how just PAHs are interacting, then we can start to figure out how PAHs are interacting with PCBs or how they're interacting with flame retardants. I think I should also mention that the work Briana is doing right now is much more in the research stages versus the actual application to current cleaning up of sites. So it's the hope that her work and the work that our center is doing gets at that second part of your question, which, give me a moment, I'm trying to find that. Where you were saying that when that other study was done, they actually did not mimic reality. And so that's what Bria's trying to figure out is, are we ultimately getting to a model that will accurately show what we're seeing in the environment? So I'll stop there, and Briana, if there's something you wanted to add.
Yeah, so there's actually another student in my lab who's doing work very similar to me, but he's looking at it from more of a whole mixture approach. And so he's actually using, he's tested the whole mixture that they've collected at this same site in the water. And he's also formed some representative mixtures and has been comparing responses there as well. So that is another, as Diana said, that is another kind of objective of our work as well, is kind of incorporating these different types of approaches.
Great, thank you. A question from Laura Feldman, trying to figure out how this affects on the ground Superfund cleanup processes. Would it mean that instead of going after high levels of a certain PAH, sampling would target not the most prevalent, but the one most toxic?
Yeah, so that's exactly our intent. You know, based off of some of the work that I've done so far, we're seeing those really prevalent chemicals based off the toxicity information that we have available aren't necessarily of most concern, which I think does kind of go against some of the narrative that people think about. It's like, oh, these are really high concentrations, like should we be concerned about them? But what we're seeing with my work so far is that we should be kind of focusing on those lower concentration chemicals that might be of most concern. Diana, if you want to add anything.
Yeah, I was just going to say this, you know, in toxicology, we always say the dose makes the poison, which is still true, but I think we have to remember that dose is relative, right? Like a drop of cyanide is still terrible for you. And yet, you know, even an over-the-counter painkiller at high enough doses can be toxic. And so I think as a scientific community, we've sort of fallen into that false narrative where we're like, oh yeah, there's a ton of this, so it must be bad for us. And that's not always the best way to approach it. So I think Briana's approach is saying that it could still be a problem if we have a ton of a single chemical, but we also need to pay attention to small amounts of very, very toxic chemicals.
Thank you. Question from Barbara Quinn. How often are you seeing synergistic effects when looking at chemical mixtures? In other words, mixing that results in higher toxicity than the additive method?
Yeah, it's a really good question. To this point, at this point, I haven't done a ton of work with that. We're just kind of considering them from a whole mixture perspective. We haven't screen these individually, but that is actually another project that I'm currently working on, but I just didn't have any data available at this point. But what I have seen is in the literature is that it really depends on the chemical composition. So depending on the types of chemicals that are in the mixture, you may be seeing synergy, but then, and it also really comes down to how they respond in the body. So if they're targeting a similar endpoint, there's certain chemicals that need to be metabolized in order to make them toxic. And so a lot of times if we're seeing similar chemicals that have to go through that same kind of process, then and we might actually see an inhibited response because they're not being metabolized. But if it's chemicals that don't need to be metabolized that to cause a response in our bodies, those actually we might be seeing more of a synergistic effect with.
Okay, great. Another question from Lisa Arkin. What were the biological impacts to lung cells in zebrafish that you were measuring?
Yeah, so the data that I had showed you was focusing on oxidative stress, which is kind of like a precursor to inflammation. In zebrafish, we're looking for a suite of different types of effects, mostly looking at morphology or different type like developmental effects, as well as behavioral effects. And then in lung cells, I'm also going to, which I haven't looked at this point, but I'm also going to look at DNA damage and cell death as well.
I will just add to that, because we are a research laboratory, which is different than a regulatory research laboratory, we're able to look at a much more broad suite of toxicological endpoints, but they don't always directly translate back to human health. So I think the zebrafish is a really great model just to say, like, does this mess up biological systems, right? That's really what we're looking for in the zebrafish. And if yes, we know that's not good, but we can't really always take, like, here's what we saw in a zebrafish, so that means this will happen to humans. It's really just sort of a litmus test for toxicity. So with Briana being able to test these in lung cells, and these are human lung cells, we're getting closer to identifying potential connections that are directly to human health.
Okay, thank you. Lisa Arkin had a second part to the question. Can you discuss how this data could be extrapolated to programs such as Oregon's Cleaner Air Oregon to determine health impacts to nearby residents experiencing exposure? How can we actually characterize hazardous impacts?
Yeah, that's a really great question. With this approach, we're hoping that it'll really prioritize chemicals of most concern. So if there's, for instance, some kind of factory that may be emitting chemicals and there's like a sampling plan that occurs, we could potentially use that approach to identify which chemicals that are emitted by this factory in the air should be the ones that are being regulated. Diana, if you want to add anything onto that.
Well, I think this goes back to one of the very first things you said in your talk, right? That right now, the traditional way to look at mixtures is additive. So we've got chemical A and we've got chemical B, and they both hit the same target in the body. So we'll just add their toxicities together. And what we're starting to see, and this is still in fairly preliminary stages, but we're starting to see that that might not always be the case. That you might have chemical A and chemical B, but they don't add together. Maybe they interact for higher toxicity. Or there was a question about the masking effect, right? Can one chemical actually reduce the toxicity of another chemical? So this, from my perspective, this is a more nuanced way of looking at toxicology, and it's getting at what is actually happening when we have these chemical mixtures, and we can't always just default on 1 + 1 = 2.
Great. At the Willamette Superfund, EPA downgraded the ROD as to the amount of PAHs that needed to be cleaned out of the Superfund based on a previous study saying that the only PAH they included in their study, being the most toxic, was not as toxic as previously thought. However, they did not look at the lower toxic PAHs, nor synergy or chemical mixture interactions. Was this wrong thinking?
So
this is from Doris Weller.
I can address this to begin with. This actually kind of brings up a different topic than what we were talking about today. That particular PAH, it was, I believe, benzoate-pyrene. And so benzoate-pyrene, I mentioned that, it's sort of infamous for being known to cause cancer. I can maybe follow up on this and send some resources afterwards. I think, Lisa, your team is working on this as well, right?
Yeah, we are.
Yeah, so this might be worth sending resources afterwards, but just very briefly, benzoate-pyrene was sort of set as the standard for carcinogenic PAHs. So to put that into a math standpoint, they basically said benzoate-pyrene is at 1, and we're just going to set its toxicity as 1. And then they took 7 or 6 other PAHs and said, we're going to scale them relative to benzoate-pyrene. So that was done mathematically, not necessarily based on what is seen in animals. So I can send some other additional literature. We've put together kind of a fact sheet from the Oregon State Superfund. And then I know Lisa's team has also been working on that, but I am happy to talk maybe at a different time about the comparisons from benzoate-pyrene to these other carcinogenic PAHs. We don't have any information right now about interactions between them. We've focused more on, is it appropriate to mathematically scale all carcinogenic PAHs to benzoate-pyrene, which is a different question than what Briana is talking about.
Okay, and then a follow-up from Paulina Lopez from DRCC. She says the same questions, please, for the Duwamish Superfund site in Seattle about lowering the ROD standards for the cleanup based on BAPs. Thank you.
It would be the same issue that we saw down in Oregon for Duwamish.
Okay, another question from Rory O'Rourke. Have you considered a non-targeted analytical approach similar to stormwater research conducted by the Center for Urban Waters at UW-Tacoma to evaluate chemical mixtures and exposure mixtures?
Yeah, I mean, that's definitely something that I've thought about. Particularly, I've had discussions with my friend who, or my colleague who is doing whole mixture research. Since right now we're only looking at pHs. However, that's just not a objective of our center or of the work that I'm currently doing. But yes, that using untargeted methods is definitely ideal, since you are looking at the whole suite of potential chemicals that could be in a sample.
Okay, and a couple questions in the chat. So from Darlene, grilling, but what about browning, crisping when baking? Is it carcinogenic?
I can take that. Yes, it's actually interesting how much research exists on the grilling of meat. So if you're really curious, I can go into great detail, but typically we see pHs when you're actually burning. So the reason meat gets a bad rap, and I should preface this by saying I'm vegetarian, but the reason meat gets a bad rap is if you're grilling outside, especially if it's a fatty cut of meat, as you're grilling it, fat is dripping down, fat is organic, so it is hitting the flames, burning, and so then you're kind of shooting pHs up onto the meat. Also, as you're charring meat, you're actually burning the meat, and so that is what's forming pHs. Surprisingly, there's not a lot of information about like burning and browning and crisping, but anytime you are burning meat, you're going to be forming that. You're not going to be forming as much, right? So there's recommendations for if you really enjoy grilling or barbecuing or smoking meats, we recommend just trying to sort of space that out. So if you barbecue one night, maybe bake chicken the other night. You can also, if you have a grill, we recommend raising the grill slats. Obviously I don't cook meat. I don't know these things, but raising the thing on which the meat sits above the flames as much as possible. So you're just creating distance so that if fat is burning, is dripping down and burning, it's got more space to dilute. Also, just buying less fatty cuts of meat can be really useful. But yeah, we typically focus more on the grilling, smoking, charbroiling as being sources of pHs. And if you do happen to blacken your meat, you can scrape that bit off, and that's a good way to reduce those pHs.
Great. Question for Briana. Is the overall toxicity of representative mixtures compared to the toxicity of the original / real life mixture to verify its representativeness?
Could you repeat that question?
Sure. Is the overall toxicity of representative mixtures compared to the toxicity of the original / real life mixture to verify its representativeness?
I see. So at this point now, we're comparing the pH representative mixture that I discussed. So we're comparing that simple creosote mixture, which was those pHs that were found in the sample. But at this point, we don't intend to compare it to the real world complex mixture, which is a limitation of our work because there could be potential other chemicals in that real world exposure that could be driving toxicity as well.
Okay, thank you. Another question from Laura Feldman. We were also recently told about sampling results from the Cove that there's a PAH hotspot that is at a level of 2 over the EPA threshold, but not considered to be generally harmful. Can you explain?
Diana?
Okay, sorry, can you read that again?
Sure. We were also recently told about sampling results from the Cove that there's a PAH hotspot that is at a level of 2 over the EPA threshold, but not considered to be generally harmful. Can you explain? Sorry about that background.
That's fine. In all honesty, I would have to probably see the data. So EPA has various different thresholds. So I would need to know if it's like the level at which action should be taken, the level at which additional sampling should be done. There's several different levels. So if you're willing to send me that information, I'm happy to take a look at it. And if I can't answer, I can send to other people in our center to try and get an answer for you.
Okay, excellent. I think, oh no, another one just came in. Oh, it's Laura Feldman saying, okay, well, thanks. Are there other questions? If so, you can raise your hand or you can put them in the Q&A box.
I think there was one from Patty in the panelist chat.
Okay, are you looking at it? Oh, here it is. With the permitting of over 300 locomotive-sized diesel engines for backup power for the data centers located in my community, how concerned should we be about the presence of PAHs from the emissions?
Yeah, that's a good question. I mean, so we know that diesel exhaust is a source of PAHs. We also know it's a source of particulate matter. I honestly, there's no easy math for me to say, like, here's how much is produced by one diesel engine, and so multiply that by 300. Again, I'm a researcher, not a regulatory person. So my answer would be like, it should maybe be sampled, but that might be, my guess is with that, they're going to be regulated. I believe you're in Washington, so there should be air regulations. And so that would be a question that you can ask your regulators there, because that place should be underneath forms of regulation, permitting, so you can actually look up what they say that they're emitting and what's going into the facility. But unfortunately, that's outside my area of specific expertise, even though I can tell you there are going to be PAHs coming from that.
Okay, thanks. Briana, do you believe your methods will translate into analysis of more complex matrices, such as landfill leachates, land disposed sewage sludge leachates, etc., such that you will be able to identify a specific source of any noted toxicity? From Richard.
Yeah, so I mean, that is one of the objectives of this work, is that it can be applied to more complex mixtures. And particularly we haven't confirmed it at this point, but we do believe that the exposure toxicity mixture might be the best approach, where we're able to not only identify drivers of toxicity in these complex mixtures, but also take into account the exposure aspect as well, chemical concentrations. So yeah, we do intend for this potentially to be applied to more complex mixtures with various chemical classes. But that would be something that would also have to be validated before it were to be applied.
Thank you. A question from Elaine Packard. What are the harms from biodiesel?
I would have to push you off to probably a colleague of mine. We don't study diesel in particular. Like I said, I can tell you there's going to be PAHs. I can tell you there's going to be PM 2.5. I know a few people that I work with. So if you want to send me an email, I can try and get more specific examples. Otherwise, it would just be me doing a specific literature search to figure out what specifically is going to be there.
Great. Thank you both. I think we've gotten to the end of the questions. Oh, another one just came in. This is from Lisa Arkin. Hypothetically, do you think that your data would support regulating facilities that incinerate with a different set of health protective regulations than other facilities, such as a trash incinerator or a medical waste incinerator?
I'm maybe going to ask for some clarification on that, because all incineration is going to be producing PAHs. So like we know that even medical waste, you're burning up the plastics, et cetera, will produce PAHs. So I don't know that we would want to regulate industry different than a trash incinerator or a medical waste incinerator, since they'll all be producing PAHs, but I'm not sure that's what Lisa's asking.
Lisa, I just asked you to unmute if you want to ask, if you want to clarify.
Thank you. Great presentation, first of all, really cutting edge research. I was just thinking about how difficult it is for communities to work with our regulatory agencies when we're looking at something like a trash incinerator that takes in medical waste, so burning a lot of plastics and metals and things like that. And these mixtures are in the air, since one can't know at any given moment what's in that trash mixture. So the source of the pollution is a mix, an unknown mix, and then it's creating mixtures in the air that may be because I was thinking about your analogy with, or I'm making an analogy to burning trash, to burning meat, you know, that we're creating by the act of burning things, we're creating even greater toxicity. And as a grassroots organizer working with a community in the air downwind of a medical trash incinerator, I'm just trying to, you know, use your data to stimulate my own mind about, wow, this is a greater risk, and yet it's treated by regulatory agencies as the same as any other risk. Maybe that's just me thinking out loud. Sorry. Thank you.
No, I'm trying to think through it. I mean, I think at the fundamental aspect of our center, the question was, should we assess toxicity of mixtures in an additive way? And so that's what Briana was showing at the very beginning, right? Where she showed, like, if you have chemical A at toxicity of 2 and chemical B at a toxicity of 4, we would say that's a toxicity of 6. And that is how it's been done traditionally. But as we're advancing more in science, we're able to ask these more nuanced questions. I think what our center is saying is that might not be the best way, is that we need to acknowledge these interactions. Sorry, that's the dog in the background. She's tired of me talking. But so if we know that additivity is not the best way, then what is the best way? And so right now we're just focusing on PAHs because the question just becomes incredibly difficult, if not nearly impossible to answer once we start adding in additional chemicals. So we're not ignoring the fact that we know when you burn plastic, you're creating much more than just PAHs. Right now, in many ways, this is just sort of a thought experiment of, can we figure this out with PAHs? If so, now can we start adding in everything else? So I think, Lisa, your question is still a really good one. We're just not at a point where we can start to answer that, because when you don't even know the inputs to like a medical incineration facility, trying to then characterize what's coming out is difficult, to say the least.
Thank you. That's very helpful. This is so stimulating. I really appreciate just all the ways this is getting us clean air advocates to think, you know, about how to do better. Thank you.
Thank you.
Any other questions? I'm seeing some thank yous in the chat. Great presentation. Yes, well, that was stimulating and very interesting. So thank you both for sharing. And we're going to take a little break and then come back. And I don't have the agenda in front of me, but there will be another talk. Yes, we'll return at 12:30 to hear from Annie Jarabek from EPA. So we'll see you soon.
While we're on break, I'm going to try once again. Some of your renamings worked and some did not. Heather Trim, can you please raise your hand if you're in hearing distance? Richard Honor, could you please raise your hand? Okay, I'll try again in a few minutes.
Looks better if you're not on mute. Okay, it's 12:30, so I think we'll get started. Thanks for those of you who remain present. And our next speaker is Annie Jarabek. Annie serves as a Senior Science Advisor in the Center for Public Health and Environmental Assessment within the Environmental Protection Agency's Office of Research and Development. Prior to her current position, she was the Deputy Director of the Human Health Risk Assessment National Research Program and EPA's Office of Research and Development. She was the principal author of the agency's Methods for Derivation of Inhalation Reference Concentrations and Application of Inhalation Dosimetry, and she led the agency's risk assessment for ingested perchlorate. Her current research efforts focus on multi-stage dosimetry modeling, including approaches for both in vivo and in vitro extrapolation of inhalation exposures. Annie is recipient of numerous awards, including a Lifetime Achievement Award from the University of Massachusetts, Risk Practitioner of the Year Award from the Society for Risk Assessment for Risk Analysis, and a Superfund National Notable Achievement Award. Most recently, she received the Lehman Award for Risk Assessment by the Society for Toxicology in 2020. And earlier this year, she was elected to serve a 4-term as Vice President, President-elect, President, and past President for the Society of Toxicology's Women in Toxicology Specialty Session. So welcome, Amy. Are you ready to go?
I am. Thank you, Tom, very much. And I thank the coalition for also affording me this opportunity. BJ, you said I have some feedback. I have no control over that. So how does it sound now?
I think it's okay. It's mild. No worries. Thank you.
And I can't find my presentation. Are you seeing my slides?
Not yet.
Because I'm in presentation mode, so.
Are you share screening?
Yes, I am.
So far, we're not seeing anything.
How about now?
Now we got it.
Can you see it now?
Yes.
Great.
You just have to put it in the full screen mode.
Yep.
You got it.
Great. So again, thank you, everyone. I am Annie Jarabek. So there were some comments made about the regulatory agency for which I serve, and I just want to specify that I'm in research and development and not in any particular program office, but I will try to help you navigate a bit some of the questions that just arose on the last call. And I'm sorry I missed this morning. It was just unavoidable on today's date. But what I'd like to speak to you about is how we are hoping to move mixtures assessment forward with some mechanistic modeling. And I also want to preface this talk by saying that I am a risk assessor. So that is the lens from which I am now approaching this. Even though I used to be at the bench, now I try to apply what people do at the bench to inform our assessments and our regulations. So the topics I'm going to cover today are just a little bit of background. I suspect some of this has already been covered. Definitions and traditional methods, just because Tom asked me to. Talk a little bit about an exciting evolution or an evolving emphasis on environmental justice that I think that you will find of note as well, particularly under this new administration. We're all very excited with the transition. and then dive into what the current constructs are for considering mechanistic data, be they both conceptual as well as computational. I'll go light on the computational, but there are some models represented. I'll give you an example. Tom mentioned that I was the lead for the agency on perchlorate. It has a rich database. That's the one I chose to illustrate. I'll summarize, and I do provide some citations and contact information. At the bottom of this slide is the requisite disclaimer that these views are those of me and do not necessarily represent US EPA policy. So traditional risk assessment, in terms of how it's approached, one needs to appreciate that we are, and this was very much the case under Administrator Pruitt, unless there was enabling legislation dictating that you were going to try to regulate something, you couldn't do it. So we are very much tied to media specific enabling legislation. So by media specific, I mean the Clean Air Act for air, the Resource Conservation and Recovery Act for land management, the CERCLA for also for Superfund sites, the Safe Drinking Water Act, of course, for water. So media specific legislation, and it typically focused on single chemicals. But because this workshop is devoted to mixtures, I know that you appreciate that that's not necessarily what we're being exposed to or what's causing toxicity. I believe this was probably already covered, but the definition of dose additivity in risk assessment is when each chemical behaves as a concentration or dilution of every other chemical in a mixture, and you sort of index what the possibility might be against a reference chemical. And that is the basis of a toxic equivalency factor approach. So you just equate the dose as the sum of the component doses, and you scale it that way. It was just mentioned by the last speakers. And that's shown illustratively on this slide. I would note that those definitions were based on understanding of interactions from empirical data, from observations. So at number 1, chemicals X and Y, shown as separate responses to the left, chemical X and chemical Y. At case 1, you've got antagonism. So somehow they're inhibiting each other. For 2, it can probably response additivity. At 3 case study, it could be either dose additivity or response additivity. The point is that when you just observe things, it's very difficult to understand what's really causing that interaction. And then of course, case 4 is something displaying synergy, where you've got more than just the 2 component addition. So those are typical traditional definitions, and we're hoping to replace those soon. So as oops. More importantly, we know that realistic exposures and resultant risks are not by single chemical. So other definitions to appreciate are aggregate exposure. This is the combined exposure in an individual or a defined population, say at your community, to a specific agent or stressor via different routes, pathways, and sources. Aggregate risk is the risk resulting from all of that exposure to a single aggregate, to a single agent or stressor. And then cumulative risk is what I want to focus on. And cumulative risk is the combined risks from aggregate exposures to multiple chemicals or stressors. So here's a schematic of how we view cumulative risk and how we want to characterize your overall level of vulnerability. So you have a source of toxicants that can come from air, soil, sediments, or ingested substances. So certain media-specific concentrations might be combustor emissions, combustor deposition to water, and then maybe ingestion of fish impacted by drinking, being in that water, or drinking water impacted by that, those emissions. So the air emissions can then end up in your drinking water, for example. Those are all environmental stressors. However, now we appreciate that there are other interactive factors that result in your overall level of vulnerability. For example, you as a person may have biological or genetic traits and sensitivities that predispose you to contract a specific disease, such as breast cancer, or intrinsic traits such as race or your sex, and as well as population demographic indices such as being an asthmatic or a diabetic. So those are physiological background traits that really need to be factored into your overall level of vulnerability. Additionally, there are cultural, dietary, and behavioral factors, such as, is the local fish a staple of diet? Do you smoke or abuse drugs and alcohol? Are your outdoor activities active or couch potato? Where do you get your drinking water source from? And then the other vulnerability factors also include buffers. So there may be aspects that buffer or increase your capacity to withstand some of these stressors. For example, access to healthcare can either be a buffer or it can be a deficiency if you don't have access to healthcare. Crime rates, proximity of homes to pollutant sources, your socioeconomic status, your diet and nutrition, again, access to recreational facilities, access can go either way, and whether or not you have social support networks. So you can see now that it's a much more of a cultural embedment, as well as just what is the physiological background and the environmental stressors. So all three of these, the environmental stressors, the lifestyle conditions, and the physiological background of you yourself or the population of interest defines the overall level of vulnerability. To address that then, cumulative risk assessment has these features. It has a population focus. Vulnerabilities and susceptibilities we try to factor those in, and we also try to engage stakeholders in involvement in defining some of these boundaries. I'll get into this in a little bit later. There are multiple chemical, physical, biological, and psychosocial stressors, as I just noted, as well as some capacities that can serve as buffers. There's multiple exposure routes and pathways. And importantly, human health is now not in isolation, but it's embedded in the environment. So you consider ecosystem services, and really we want to consider what's known as, with the World Health Organization, One Health. So if something is impacting the environmental conditions, more than likely it's also impacting your health. And that's what we mean by One Health, both impacts on the ecosystem as well as humans in that ecosystem. And that's what we're defining as cumulative risk assessment. So looking at cumulative risk assessment as a paradigm, there are integration issues that are different than the traditional hazard identification, dose response assessment, combined with exposure assessment to get your risk characterization, which is shown in the blue. And the biggest difference is that dose response and exposure assessment are very interdependent in the cumulative risk assessment paradigm. So for hazard identification, to start out with, you want to evaluate effects specific to the vulnerable population and effects from the stressor interactions. For dose response, evaluating that, you want to look at the combined doses of multiple stressors, dose response for a sensitive population, whether or not there's any effect modification, again, whether or not you have a capacity to withstand it, or whether, such as a buffer, or whether or not you're going to be more susceptible, and what might the toxicological interactions be. For exposure assessment, you need to evaluate multiple exposure routes and pathways, as well as the social, culture, and economic factors that influence that exposure, and trying to estimate what exposure is to non-chemical stressors. That's very difficult. And then risk characterization, there's uncertainties associated with combining risks and what the qualitative factors might be affecting those risk outcomes. So it's challenging, but we really feel that this is an important paradigm to try to advance. Other definitions and methods, models are mathematical representations of a natural system intended to mimic the behavior of the real system, which allows description of empirical data or observations and predictions about untested states of the system. And this is becoming more and more the norm. Use of models has been facilitated by computer programming of the mathematics and construction of convenient input and output formats. And one of the most important types of models for cumulative risk assessment is the conceptual site model, which is a written description or a visual representation of actual or predictive relationships between humans or ecological entities or both, and the chemicals or other stressors to which they may be exposed. So you can visualize or envision what your conceptual site model might be for a given problem, and then you might also be able to describe it mathematically. I'm going to give you an example of both. In terms of a process, the integrated cumulative risk assessment process is pretty much the same as typical risk assessment. We start with planning and scoping, which includes a technical description of the problem, as well as stakeholder and manager interdisciplinary dialogue to try to figure out what exactly is the problem. That's then known as the problem formulation. In terms of risk assessment, you then analyze and try to characterize the risk. In this case, though, we're also considering the economic, statutory, social, and other analyses to inform the decision. So as you can see, cumulative risk assessment is more comprehensive. I did want to just mention about environmental justice, EPA, which we are now defining as fair treatment and meaningful involvement of all people, regardless of race, color, national origin, or income, with respect to the development, implementation, and enforcement of environmental laws, regulations, and policies. I encourage you to visit this particular website, where you'll find information on grants and resources, the strategic planning to try to advance environmental justice in our regulations, and as well as opportunities for collaborative partnerships on different programs. I am going to focus on strategic research because that's where I sit. Goal 1 in this particular Environmental Justice 2020 Action Agenda is to deepen environmental justice practice within EPA programs to improve the health and environment of overburdened communities. I'm going to be focused on increasing the understanding of the factors that influence environmental health disparities and develop methods and data to assess adverse and cumulative risks. But as you can see, we're also involved in research and development to promote the use of decision support tools for identifying and prioritizing environmental concerns, assessing cumulative impacts and evaluating mitigation options, to develop innovative monitoring tools and addressing special focus areas such as promoting tribal sustainability and well-being, and advancing efforts to mitigate the effects of climate change. I just wanted to point out, and just give you another thing to go look up. EJ Screen is one of those tools that I just mentioned. It's an environmental justice mapping and screening tool that provides EPA with a nationally consistent data set and approach for combining environmental and demographic indicators. I really encourage you to go to the overview, and as well as you can plug in some specific parameters of your own interest to use this tool. So now I'm going to turn more to the meat of the work that I'm doing to modernize assessments. The challenge really hasn't changed. It always has been for risk assessment. Well, how do you best integrate evidence? However, we are in an era of some important transitions, both conceptual and computational. So we are now in an era of big data descriptions. There's a lot of high throughput data, all kinds of information, and it's all being surfaced on the web. And there are ways with systematic review tools to scrape that information. How are we going to put it together? There's now an emphasis on comprehensive source to outcome characterizations. That's going to be my focus today, as well as bringing in new approach methods such as in vitro methods to try to inform some mechanisms. For translation of this information, I'm going to focus and try to convince you that mechanistic modeling and a modular workflow is the best way to try to understand all this, so that you have exposure alignment across the various types of data that you might be trying to integrate, and look at quantitative adverse outcome pathways and integrated assessment and testing approaches, otherwise known as IATAs, to inform this, as well as reporting standards. So this is a schematic of a typical risk assessment. I mentioned scoping and problem formulation previously. That's based on a broad literature search. And you then try to develop protocols for evaluating the information that you might find in your literature search according to something called a PICO statement, which is your population, the exposure, the comparator, and outcome. So for example, you may have an exposed population and an unexposed population to a specific chemical, and the comparator then is whether or not you get the same outcome or adverse effect. And typically this is done in parallel across human data, laboratory animal data, and what is known as mechanistic data. The problem with this parallel approach to identify the evidence, then evaluate the studies, and then integrate the evidence to either do hazard identification or dose response assessment is that it is in parallel. And you have diverse exposure systems across those three types of data. And you have doses at very different levels of biological organization. By that, I mean, some study might be done at a cellular level, or an epidemiological study might look at a population. You've got various types of outcomes. What are the adverse effects that they're saying, these studies are saying that occur? And you also have different modeling approaches for that. Finally, mechanistic data are not considered in this integrated structure. It's sort of an add-on at the end. It's the third data stream. Whereas really what I hope to show is that the mechanistic information can create a framework by which you make sense of both the human and laboratory animal or ecological data together. The challenges for cumulative risk assessment are these. So what is the scope or the conceptual boundary of the community analysis? Is it geographical? Is it based on the demographics of a population? And what are the exposures? What are the routes, the frequencies, and magnitudes of those exposures? And what is the scale, again, as I just mentioned, for the measurements or the observations? It can be geospatial, a local region, or all the way to a national. We've got national ambient air quality standards. What are the temporal considerations? Are we talking about acute operations such as startup and shutdown of a combustor, or are we talking about chronic exposures? And then, as I already mentioned, the biological scale of the effect of the measurement. Are we looking at molecular events? Are we looking at tissue events? Are we looking at population events? Each of those has a very different inference structure that can be drawn to influence your resultant risk assessment. And then your assessment endpoints, exposure measures and metrics are for various receptors. You can have adverse outcome pathways across various species, and hopefully we're getting to the point where we're using something called general ecological assessment endpoints and ecosystem services, again, for that concept of One Health, trying to bring in the ecological endpoints together with humans so that we get a more comprehensive picture of the impact on health. One of the important aspects of this transition to comprehensive source to outcome characterization are these two constructs, the aggregate exposure pathway shown on the upper left and the adverse outcome pathway shown on the bottom. The adverse outcome pathway shown on the lower right was first coined to represent a biological signature of a perturbation in a system. Again, remember, cumulative risk is looking at not only chemical, but other stressors. So a molecular initiating event can be from any stressor that causes a macromolecular interaction that then results in a key event being such as a cellular response that then through another relationship can migrate to an organ tissue or organ response, can migrate then by another key event relationship, the KER, to an organism response, and then to a regulatory relevant population response. The important thing about the adverse outcome pathway was that it was considered a biological signature. It was not chemical specific. Soon after that was first coined by Gary Ankley of EPA in 2010, Justin Teagarden of PNNL and also affiliated with Oregon State, and Cecilia Tan here at EPA coined the aggregate exposure pathway, or AEP, in which you organize data and talk about different components along a pathway in a similar fashion. So you start with the source, say manufacturing. There is a key event relationship that then results in the next key event state. So what is the concentration in the environmental medium, air, water, or soil? That then transitions to external exposure and then to an internal exposure, or such as the amount absorbed or the amount in blood. And then the target site exposure shown on the left-hand side of this middle section of the chain is what then links to the molecular initiating event of the adverse outcome pathway. I would note that dosimetry modeling provides a critical link here between these two frameworks because the target site exposure is very dependent on the chemical absorption, distribution, metabolism, and elimination to create that target tissue exposure. So you really want to try to figure out what are the chemical features that influence what that target site exposure is in order to link your exposure to a potential adverse outcome pathway. So this is now the basis of what we're trying to do to define comprehensive interactions. We're using those two frameworks, the aggregate exposure pathway and the adverse outcome pathway framework, breaking it into components so that we then can explore how are mixtures actually causing these interactions. And so there are 4 categories. First is the interaction in the environment. So you might have an emission source, an interim environmental key event state, such as you saw before, it could be from the source to the media to a specific concentration in an entity and then to the external dose. The next category would be the toxicokinetics. How does an organism, be it human or ecological, handle that chemical in itself to create the target site exposure? Toxicodynamics means what are the response mechanisms to that particular internal dose. So there's that molecular initiating event. Remember, that was the beginning of the adverse outcome pathway. There are several key events for that to then be manifest as an adverse outcome. And then category 4 in terms of potential interactions are at the population and ecosystem level. So this is where especially you can see that interaction between humans and ecosystem services. So these 4 components, based on the AEP and AOP frameworks, can be very useful to help define better what the interaction in a particular mixture might be. Exploring this further, I do this on the next 2 slides where we break down those categories of interactions, again, based on whether it's for category 1 in the environmental exposure process or 2 in the toxicokinetic process. But let's explore this a little bit. So category 1 in terms of an interaction that occurs during environmental exposure processes could include emissions, transport and transformation, and exposure processes. So for example, one subcategory is whether or not chemical X influences the movement of chemical Y between those key event states, or does it change the conversion rate of chemical Y in the environment, or does it create a new conversion, a different key transfer rate involving each of those chemicals. In terms of the toxicokinetic processes, chemical X might interact with chemical Y by influencing the movement of chemical X between the key event states in an organism. It could change the conversion rate of chemical X in an organism, or it could create a new conversion involving the 2 chemicals. Similarly, subcategories of interactions in 3 and 4. Now 3 again is the toxicodynamic. They involve chemicals with molecular initiating events on a common adverse outcome pathway network. So chemical X and Y may have 1 or more common molecular initiating events. They could have different molecular initiating events, but could have 1 or more common intermediate key events. So they might influence that pathway of pathogenesis down to an adverse outcome or they might have different MIEs and different KEs, but both of those could result in the same adverse outcome. And then population or ecosystem mediated interactions, they might have different MIEs for adverse outcomes that occur in different portions of a receptor population, or they could have different adverse outcomes in different species in an ecosystem, but the adverse outcomes lead to a joint effect in the receptor population. So this is just an example of how to explore those 2 frameworks, being the aggregate exposure pathway and the adverse outcome pathway, in a systematic fashion to really start to understand what exactly is the mechanism for the interaction in the mixture that you're curious about. So let me give you an example of toxicokinetic interaction. This is a category 2B. Chemical X modifies the metabolism of chemical Y, decreasing the detoxification of chemical Y, and this would result in a synergistic interaction. So you have release of X on the upper left to a key event state. Then you have the outer exposure surface. Now you're internal to the target site exposure, TSE. And now at the molecular initiating event, you have a decreased key event being the decrease in enzyme activity, influencing this interaction between the release of chemical Y, the outer exposure surface, then that first key event state, you can see that there's a detoxification. If this decrease in enzyme activity from the first chemical X actually influences that detoxification, you're then going to get an increase in the adverse outcome of the two combined. But it's a very mechanistic insight on what might be causing the interaction in this particular mixture. So this translation with mechanistic modeling involves evolving empirical modeling not just from observations of what, to really trying to understand how and why they occur. You've got a qualitative agreement with current biological understanding of the toxicokinetics, the absorption, the distribution, the metabolism and elimination of a particular set of chemicals, as well as how they might be causing toxicity, their pathogenesis processes. And then quantitative agreement with test measures of key events. So if you've got measurements to try to test your conceptual model, that really helps characterize the risk. It can provide insights on important physicochemical properties. It can help translate across these different experimental designs to improve data integration. It addresses differences between test systems, species, and humans to refine the inferences, and you can quantify and explore properties systematically and consistently. So this is now a new mechanistic scaffold. Remember when I said that typically we look at human data and then lab animal data and then mechanistic data? We're now proposing a new approach. Conceptually, it's very similar. You start with source, you look at fate and transport, you look at the toxicokinetics and toxicodynamics and look at the adverse outcomes, and you try to integrate. The objectives, though, with this mechanistic scaffold is to organize the data across the entire system, not just one type of data and then the next, but together. This increases the transparency of the type of data that you have and can also inform data gaps. The mechanistic understanding can clarify the context for the interpretation of the information. It helps us to use exposures to drive the risk assessment, to characterize those key events, quantify the uncertainties in the process models of what you're trying to describe, and facilitates the integration of human ecological endpoints. Importantly, also, the integrated risk assessment increases utility and confidence because you can tailor your specific source to outcome risk characterization, as well as leverage data sources. So for example, if you know how a chemical reacts in the environment, it's likely going to have those same physicochemical properties in your test organism. So you shouldn't have wildly different ways to describe how the chemical interacts with water, for example. So your workflow is to identify your contaminant sources, identify the chemical species, review together both the health effects and ecological effects that you might be able to find in the literature, evaluate the exposure routes, the receptors, and the transport and transformation to then interface the media concentration and receptor behaviors to characterize the ADME, the absorption, distribution, metabolism, elimination, the molecular initiating event, and any adverse outcomes, so that you can then integrate human and ecological data together. And I'll be illustrating that with the case study of perchlorate. So category 3A, when you have a common molecular initiating event, is shown here. We use the AEP and the AOP to construct a continuum for both human health and ecological effects and integrate them. So again, the aggregate exposure pathway is exposure processes. to then describe the target site exposure. You look at sources of contamination, key exposure states, relationships among those key exposure states to define that target site exposure. And then toxicokinetics helps you identify the target site exposure influencing the molecular initiating event that causes the pathway to adverse outcomes. So you have the MIE, the molecular initiating event, various key events of toxicity, the relationships among those key events that helps inform what the adverse outcome might be, and that's called toxicodynamics. So we first developed an adverse outcome pathway for perchlorate. I'm moving toward a cumulative risk assessment of perchlorate with this talk. We first developed the adverse outcome pathway. This is the case study that was published regarding that, where we used the AEP and the AOP to facilitate the integration of human health and ecological endpoints. So this is a 3A case study, and the chemical that we want to talk about is perchlorate. And if you don't know what perchlorate is, it is used in many, many applications. It's an oxidizer. It was originally used to treat certain thyroid conditions. It's applied in agriculture. It is part of most munitions. It also is one of the components of airbags. It is the solid rocket fuel in the shuttle, as well as many other types of launched objects in the military, as well as fireworks. It is an oxidizer. And when it gets into the environment, it's highly soluble because it readily forms salts that then dissolve readily in water. So it has gone pretty much everywhere after exposure, and it lasts for decades. This particular process of degradation I've got shown on the bottom takes decades. So perchlorate is very stable and mobile in the environment. We're concerned about perchlorate exposures because of the impact on thyroid hormones. What I illustrate here is the thyroid gland. So you have a symporter, which is an active transporter of iodide into the thyroid gland, and iodide is used in the thyroid to create your thyroid hormones, T4 and T3, which then circulate in the blood. And thyroid hormone is basically important for any healthy tissue functioning. There is a feedback mechanism. So because it's so important, the thyroid hormones in the blood are monitored by what's known as a hypothalamic pituitary thyroid HPT axis. So the hypothalamus is monitoring what is this serum concentrations in the blood. If they're low, it releases thyroid releasing hormone to tell the pituitary gland to stimulate the thyroid. So that's a positive feedback. There's not enough, you need more, create more positive feedback. Thyroid stimulating hormone then tells the gland to increase production of the thyroid hormone. What happens with perchlorate is that it looks very much, it has the same charge, and in terms of the three-dimensional structure of the compound, looks almost exactly like iodide to that active transporter. So what it does is then inhibits iodide, and you get a decrease in thyroid hormone, both in the gland as well as in the circulating blood. This is a highly conserved adverse outcome pathway because, as I mentioned, thyroid hormone is important for functioning of just about every single tissue. By highly conserved, I mean it is dominant in many species, because you can appreciate that, of course, thyroid hormone is important both for function as well as, in particular, development. So every baby that's born in this country has its heel pricked, and these blood is monitored for these two hormones, T4 and T3, and actually also TSH, to see what the baby's thyroid status is, because we know that it is so involved with neurodevelopment. So the adverse outcome pathway for that inhibition of that transporter, the sodium iodide symporter, or NIS, in the thyroid gland, and subsequent adverse neurodevelopmental outcomes in mammals is shown here. So you've got the NIS inhibition, it decreases serum T4, which then results in a sequence of adverse key events leading to cognitive function being decreased. So we use that particular adverse outcome pathway to assemble dose response data for mechanistic endpoints in multiple species from the published literature and from various models. And we use the AOP framework to organize and integrate the data across species as a way to highlight the data gaps as well, and to evaluate the applicability to cumulative risk analysis. So here we've got the very left-hand box, NIS inhibition, leading to thyroid hormone synthesis and depletion in the thyroid. We get that serum thyroid hormone decrease, and it impacts these species that we could find in a very similar way, where you get decreased fecundity, decreased survival, decreased growth, and developmental and neurotoxicological effects. The species that we tested were mammals, humans, rats, meadow and rabbits. We found data in amphibians, fishes, birds, and invertebrates, all illustrated on this slide. This is a very busy slide, but I just want to point out what the data display looked like. This is the perchlorate anion dose on the y-axis and micrograms per kilogram per day. And you're looking at the different key events moving from the sodium iodide symporter or NIS inhibition to depletion of the thyroid hormone in the thyroid gland itself, reflected then in a thyroid hormone decrease in serum, the upregulation of thyroid stimulating hormone increase because it's trying to compensate for that decrease in the hormones, histological changes in the gland in terms of, is the thyroid then trying to create more cells to try to compensate for that insult? Is there impaired growth, impaired reproduction, or developmental effects or mortality? And these various, I don't want to get into the data a lot, but the various symbols there, if you want to look at it later, are whether or not it's an adverse effect, a low adverse effect level, or a no adverse effect level, or whether we were able to model it with something called benchmark dose response modeling. But you can see that there's a consistent display of data across these various key events. And what is illustrated in black here with the asterisk is the point of departure that the agency developed for the oral reference dose for drinking water for perchlorate. And the reference dose is shown then down here to be protective of all these different effects. And you can see that there's a consistent effect, a consistent relationship across all of these relative being protective by that reference dose. So we were encouraged by that. The key events in humans, just want to point out that we use that same relationship between the point of departure and the reference dose consistently across all of these different major key events, such as the increase in the thyroid stimulating hormone, whether or not there was a histological change or developmental effects. We kept that consistent in this particular construct. And likewise, the rats, I would note, the gray line indicates no observed adverse effect levels in rats, and they fall right in line with humans. I just wanted to illustrate that because you might have heard that, oh, rats are so much more susceptible to thyroid hormone perturbation than humans, when in fact they're very consistent when you look at it on a mechanistic basis. It might be true for tumors, but in terms of these other key events with respect to development, rats are a very good model for humans. So moving now to cumulative risk assessment and how we might use that adverse outcome pathway to evaluate a conceptual site model. This is a conceptual site model that we just developed to look at 3 different species in a particular community that we're defining as one exposed via atmospheric deposition, there's surface water discharge of perchlorate, and there's a groundwater spill as well. And again, I had mentioned that part of the issue with cumulative risk assessment is defining your community. This is how we defined it for this hypothetical case study. So this is the second paper then, where we're coupling the AEP now to the AOP to quantify the integration of human health and ecological endpoints using this construct. So the difference here with the second paper is we actually then did quantitative modeling, and we explored further the left-hand side of this, which is the aggregate exposure pathway. And that's really important in terms of, well, both sides are important to mixtures, but in particular, trying to figure out what your sources are. The aggregate exposure pathway network is very important. So this shows you the full-blown coupled aggregate exposure pathway and adverse outcome pathway conceptual model. On the left in the blue, you start with the chemical. You have your sources. Again, we just hypothetically said it's coming from the atmosphere. There's a water discharge and there's a spill. The exposure media that we then explored was surface water, groundwater, and soil. Your intermediate key event state was what is the concentration in aquatic plants? What's the human consumption? What do irrigated plants get? What do on-site plants get? And then the exposures in the various species were humans, terrestrial mammals, fishes, birds, amphibians, aquatic invertebrates, and terrestrial invertebrates. And then the target site exposure has to do with really trying to figure out what that ADME, the absorption, distribution, metabolism, and elimination is in the mother and the fetus and an individual organism, to then link to that sequence of events, starting with the molecular initiating event and the events leading to these adverse outcomes in the various species. How we did that is something called a network flow model, illustrated on the left. The red circles represent nodes, which are resource pools that can be the individual species or a standing stock or biomass. The edges are the transport and transformation equations. The system must have a boundary, just like the conceptual site model. So the boundary of this particular network was the conceptual site model that I showed you a couple slides earlier, and it must be open. So it has to have flows in and out of it. The directional changes to achieve mass balance of what goes in and what goes out is a thermodynamically conservative approach mathematically. Just shown here, I don't want to get into the math, but to give you a sense of it, here you have your surface water, the atmospheric deposition, and the groundwater. It goes to these three nodes: pond water, groundwater, soil. Pond water then interacts with aquatic plants, obviously, or it can flow out, or it can grow to groundwater. Groundwater can go to grass. Grass can influence concentration in soil, as can groundwater. Shrubs also interact with groundwater, and they can also go to soil. And you can represent those flows, those arrows, in something called a matrix to be able to quantify it mathematically. How you parameterize such a mathematical network is you extract as many rates and stocks as possible from the literature, and you can then infer some of the missing rate data to define those arrows quantitatively from standing stock concentration, and again, that mass balance. So you're creating a system and you're defining the boundaries, and then you can evaluate what the flows in and flows out are based on the starting conditions on the left, which is a concentration in surface water, the atmospheric deposition, or the groundwater. For those who want to see the math, it's here. You use ordinary differential equations called ODEs, and you figure out what comes in and what goes out for a particular compartment in that conceptual site model. And then you construct for each of those flows, as well as the various nodes, and then use a Monte Carlo approach to select a set of parameters. So we ran constants and initial storages from the literature, as I mentioned, with the initial parameterization. We ran the ordinary differential equations to steady state, and we used a uniform sampling distribution to inform that matrix. And we used a sampling distribution of 10,000 to get analyses across the entire set to figure out what the distribution of concentration is in each of the entities. So here you have illustrated, this is just schematically, what a different deposition distribution might be in each of those. So you've got surface water, the groundwater, the soil, the aquatic plants, the grasses, and shrubs. Again, that is representing in the community defined by the boundary shown by the dotted lines, those nodes that are important and what the distribution of the concentration is in each of those. So then you can run hypothetical exposure scenarios. Now this is hypothetical, but what we're trying to do is illustrate this as an approach, a mechanistic modeling approach, to be able to really now define cumulative risk should you have the data or try to do this with an actual case. So what we did was we ran 3 different exposure scenarios: mild, moderate, and high. Mild was that perchlorate is present throughout the ecosystem. That is true of both moderate and high as well. And the concentrations that we started with were lower than were documented in contaminated sites. For the moderate case, we just increased each of those inputs from surface water, the atmospheric deposition, and groundwater 10-fold each. And then for the high scenario, we increased to 100x, 10-fold above the median, the moderate case for groundwater contamination over the moderate scenario. So the concentration results look like these. You get an evident influence of increasing groundwater contamination on vegetation. On the left is the mild scenario, and then moderate, you're starting to see more in grass and shrubs. And then with that groundwater increase, you see a lot more increase in concentration in grass and shrubs. So on the y-axis, you've got the concentration in ppm, and across the bottom is you've got different concentrations for each of those 6 components of your site. It's also important, however, to evaluate the behavior assumptions of the receptors, be they the humans or the ecological entities in your conceptual site. So what we assumed for the human behavior, we assumed that humans are exposed only through drinking of groundwater via a well. The daily water intake was 2 liters. And the person had a body mass of 72.3 kilograms. It was a full-term pregnant woman, was used in the model that we used to calculate what is then the internal dose from that external concentration. The rat and fish behavior assumptions are shown on this slide, that the rat represents a small herbivorous mammal. So they consume grass, they drink surface water. The daily intake is the particular rate, 0.005 grams per kilogram per day. And the body weight is shown there in kilograms. And for fish, we had much less data. So we had to assume that the internal equivalent concentration was the same as the water concentration, or the target site exposure was in fact the concentration in the pond water. And just because of the way the gills operate, that was probably a relatively safe assumption. So the environmental analysis results are shown here. Now, environmental analysis is the type of ecological network analysis. I talked to you briefly about a network analysis just to give you the concept of what was done, but we then use that type of analysis to track where the material came from in each compartment. So here shown on this slide is each of the 3 exposures: mild, moderate, and high. In looking at fish, the small herbivorous mammal, the rat being the representative, or humans, in each of those cases. And you can see with each different one, you get a contribution from surface water being the blue, the atmosphere is the gray, or the groundwater, that's different in each species. And the aggregate exposure pathway can then show how these organisms are affected differently in the same environment, just based on the exposure pathways and their specific behaviors. So you're starting to get a much more accurate characterization now of what a given species might do in the very same environment, being your conceptual site model. So how then did we link the aggregate exposure pathway to the adverse outcome pathway? For humans, we had something called a physiologically based pharmacokinetic model to describe quantitatively the absorption, distribution, metabolism, and elimination, or ADME, in humans. So again, we had the exposure on the left-hand side, we have an external exposure, and we use this model in the purple regime of that target site exposure being the interface between the exposure and then what that exposure might do internally. We used something called a physiologically based pharmacokinetic model to describe the absorption, distribution, metabolism, and elimination to best estimate what that internal target site exposure that would interact with the molecular initiating event might be. We did something similar for the rat because there was an available rat physiologically based pharmacokinetic model to do the linking between the AEP and AOP. And then for fish, as I mentioned, we had to assume that the external exposure was the equivalent to the internal target site exposure. Again, because of high mobility of perchlorate and the high efficiency of the gills, we felt that this was a supported assumption because there were no physiologically based pharmacokinetic models for fish available. The PBBK or physiologically based pharmacokinetic model results for humans and rats are shown here, and you can see that the dosimetry, you've got the percent of that inhibition in the thyroid gland versus the dose of perchlorate on the x-axis. You can see different shapes of the two species, the different shapes of those curves and different dosages causing that NIS inhibition. So about 40% in the human occurs at 30 micrograms per kilogram per day, whereas it's not the same in the rat. So the dosimetry provides quantitative linking between the AEP and AOP, and you can characterize species-specific differences. And these result from a combination of the exposure, the animal behavior, and these specific ADME properties. We then calculated a hazard index, which is often used to characterize mixtures. The equation is shown here, and this is one that I do want to spend some time on. So EI is each exposure source. E is the exposure level. I is whatever, remember we had those three different exposure sources, the atmosphere, et cetera. The acceptable limit of exposure, we use the lowest reported low L for each species. And you combine those, and when this hazard index is above 1, you have a problem with the mixture. When it's below 1, you're not as concerned. The results are shown here. The hazard index is shown on the bottom. For each species, we've got human, fish, and the small herbivorous mammal or the rat. For each of the three, each column represents the exposure scenarios, mild, moderate, and high. And you can see only in the high concentration are humans really considered to be at risk. The fish don't seem to have a problem at really any of the exposure concentrations, and the rat definitely, the small herbivorous animals, because they're eating the grass as well as drinking the water, have a much greater risk of being impacted by perchlorate. So it places exposure predictions in the context of the mechanistic toxicity data, and it shows how organisms with similar mechanisms of toxicity may be affected differently because they have different exposure pathways or perhaps because they have different behaviors. So this can be applied to multiple chemicals. You might imagine that you've got various different anions that are similar to perchlorate. In fact, thiocyanates and nitrates act similarly in the thyroid gland. Those then could be 3 different target site exposures that impact the same MIE from 3 different chemicals in a mixture. And I would also like to point out that different chemicals don't necessarily have the same MIE, but can interact in a network at different places along an adverse outcome pathway. So they can have the same or various MIE, but this construct of looking at what exactly are the key exposure states and what exactly are the key events of an adverse outcome really helps you define what the interaction of your potential mixture might be. So in conclusion, coupling the aggregate exposure pathway and the adverse outcome pathway networks is a very useful tool to organize data for cumulative risk assessment. You can look at it across exposure routes, explore potentially impacted species and multiple chemicals, look at exposure pathways, receptor behaviors, that ADME, absorption, distribution, metabolism, and elimination, and toxicity mechanisms all influence the prediction of an adverse outcome, and these quantitative analyses can refine cumulative risk assessment and inform relative source contributions in support of regulatory decision-making. So to come full circle, again, we have to interact with that enabling legislation. At least you would know how much is coming from air, how much is coming from water, and how much might be coming from land, so that you could then say this amount from this source needs to be a certain amount. And I provide mechanistic references as well as the mixtures and cumulative risk assessment guidance documents for your reading pleasure later. I thank you. And I also want to acknowledge the postdoc David Hines, who did that perchlorate work with me. Unfortunately, he has left the agency, but this is his contact information, and here is mine as well. Thank you so much for your attention.
Thank you, Annie. That was great. I don't see any questions in the Q&A box. So if you have questions, you can enter those. It should be, should find that in the lower menu bar. Or you can raise your hand using the raise hand option, and I can unmute you to ask directly. Any questions, Tom?
Yeah, Annie, this is Tom. That was a lot to figure out here. I wanted to, I guess, ask a question having to do with the risk assessment part of this. And I guess my question would be, how would, if you started to use this approach to come up with new NOELs or LOELs or risk values, do you think that there would be a big difference from the, from what we're using right now in terms of the way that we would be regulating chemicals?
Yes, I probably should have pointed out that with the exception of the evolving emphasis on environmental justice, we don't really do cumulative risk assessment.
Mm-hmm.
We do that individual chemical by individual media approach.
Mm-hmm.
You might do a toxicity equivalent factor approach, but that the legislation is not written in a way to do that. So cumulative risk assessment would really need to be communicated, if you will, across the various programs that are regulating each of the individual media. And the bottom line to your question was that last bit that I mentioned, the relative source contribution. So if you do a cumulative risk assessment and you know this particular exposure in air in this particular system, say it's an impacted community, resulted in this impact, you can then back that out to say you should not allow this chemical or this mixture in air to this extent. So the relative contribution, the relative source contribution is of, say the exposure is 1. If there's a lot of chemical mixture coming from air, your relative source contribution might be 0.8, and the rest would not be too much from groundwater or soil, for example. That's going to be the earliest way cumulative risk assessment can impact how we currently do assessment.
Okay.
But this was a very eye-opening analysis that we did and provided to the Office of Water to say, the way you compute things right now really isn't taking into account comprehensively what might be happening, because it wasn't lost on them. They also have regulation for nitrate, right?
Mm-hmm.
So that mechanism of perchlorate interacting with the thyroid gland, and then our emphasis that, well, not only could perchlorate be doing this, but 2 other things you regulate, nitrate and thiocyanate, might also be doing this to the gland. So, what are you going to do about that? So they're thinking about it.
Yeah, that was going to be my next question. I mean, in terms of the adverse effect pathways, I guess I heard a lot about that in the past related to trying to take into consideration, this would be with the mixtures question, I guess, how different chemicals, if you see that they're basically working on the same adverse effect pathways, then you should be taking into consideration when you're considering risk.
Right. And I think being able to unpack it to that level of interaction, is it in the exposure side only? Is one affecting transport and transformation of another? Or is it actually, as you suggest, influencing a key event in an adverse outcome pathway? That's really important to convey and understand. is sort of the first step to try to get this kind of information into assessments more routinely.
Mhm. And then I don't know if this is an appropriate question or not, but you mentioned about you're looking forward to the new approach that the EPA is taking. Do you see that there's a lot of have you noticed that there's a lot of change going on in the different divisions of EPA given the change in the administration?
Well, I will share with you that I had to answer an email just this morning, and I remind you that it's Saturday, that if I wanted to incorporate cumulative risk assessment into legislation, how would I do it? So they're very much interested in advancing some of this environmental justice in particular. And one way we know that we can start to inform environmental justice is with cumulative risk assessment and something else called hazard impact analysis.
Mm-hmm.
So stay tuned. I don't have any more information than that. They're starting conversations on it.
Thank you.
Yeah, that's exciting. So I see Therese Weller has her hand up. So I'll ask her to speak.
So Annie, what you're saying is that, so if a cumulative risk assessment was done on, so I mentioned in the earlier question that I had about the pHs that were downgraded in the Willamette Superfund site. So the cumulative risk, they wouldn't look at the other PAHs, but they would look at something like, it's also where most of the PAHs are. It's an extremely busy road with lots of diesel and lots of truck traffic. And so there's a lot of PAH influence that is airborne. And also because Oregon has extremely low thresholds for toxicity for diesel. So that accumulative effect would be looked at in that case in the future, that the surrounding anyway, the surrounding influences of perhaps other PAHs would be looked at.
Right. I think the key there, at least what I'm trying to advocate for, is you really need to understand whether or not those other PAHs act the same or differently. And one thing I didn't have time to include in this talk is one of the other ways this type of adverse outcome pathway and what are the key events of how one PAH causes toxicity is then you could look to see, okay, PAH 2, 3, and 4, do they all have the same key events, or do they interact with that adverse outcome pathway at different key events, and how much? And if you could then characterize that, rather than assume that they're all some sort of equivalency factor to a index chemical, benzanthrene, for example, or BAP, you can then get much more specific in terms of how much of the different PAHs should be allowed in a particular media. That's not discussing knowing how to figure out what the different exposures are. Does one, if you've got a higher PAH 2, does that mean 3 and 4 are less, or does that mean 2 is much higher plus 3 and 4 at a typical concentration? So you really need to be able to understand the mechanisms of the interaction in each of those 4 components: the exposure, the toxicokinetics, the responses, their toxicodynamics, and then what's happening at the population. Does that clarify?
I might be misinterpreting Therese's question, but I think it may be going to that there's focus on benzopyrene in sediment. So they decided that they could leave a lot more benzopyrene in sediment without thinking of other sources of benzopyrene in the community.
Okay.
So as well as stressors on the community and other kinds of things. Your approach, I'm assuming, would be different. You would be with this cumulative approach, you would be looking at not only the benzopyrene and sediment, you would be looking at other places, other sources of benzopyrene, as well as, socioeconomic kinds of issues and other kinds of stressors. So that's, I
Thank you,
don't.
Tom. Yes, I get now. I understand what
I'm
you're
not
getting
sure
at.
if that's Teresa's question, but let's make it
Thank
my
you.
question, I guess.
Again, the major issue for integration to use cumulative risk assessment is you have to set the boundary of your system. So is it a community that you're concerned about? And then you can think about, well, how is this community, as Tom just said, is it just the sediment, or are you also getting exposures from elsewhere? And then yes, it would be a different answer than the current one in terms of the risk.
Okay, great. Question from Lisa Arkin. The thyroid outcome you were tracking, is that hypo or hyperthyroid? I suspect hyper.
It's actually hypo. So you get a decrease in the thyroid hormone because perchlorate inhibits iodide uptake, and iodide is part of how we manufacture the thyroid hormones.
Okay, that's interesting. Okay.
And so hypothyroid is one thing, but the lack of thyroid hormone when you're as a fetus or developing organism, that's when you get the neurodevelopmental impacts. So it's a much more adverse outcome, if you will, if you're exposed as a fetus or a neonate to low thyroid.
Okay, good. This is a question from Greg Wingard. How much support is there in the agency for pursuing this approach? And you kind of touched on that.
Right. As I mentioned, the Office of Water definitely paid attention to it. They, probably are going to, within drinking water, there's something also called a relative source contribution. So how much do you assume is coming from drinking water per se, or versus other water sources? They appreciated that could be useful there. In terms of across media, I really think my answer today to the email was that either internally in the agency, or perhaps both legislation as well as a mirroring internal organization in the agency, you need an entity that, I don't know if dictate's the right word, but someone that has to have oversight to say all of the different media need to play well together. Because otherwise it's always 100% or certain assumptions via air, certain assumptions via water, certain assumptions via soil. Probably none of them are realistic and they're not integrated. So what's really needed is to have an integrated approach. If there's any appetite in the agency at all, it's right now. And again, it's under both climate change as well as environmental justice. And I have my fingers crossed that cumulative risk assessment will start to be advanced under both those programs, which is why I mentioned them.
That's great to hear. I have a question from Patty Martin in the chat. Regarding the Monte Carlo analysis, would you know if it would be appropriate to use to determine compliance with NAAQS?
Oh, that's interesting. So that the National Ambient Air Quality Standards are more of a ubiquitous distribution. I suspect that you might defeat the purpose somewhat of establishing those distributions if you use the NAAQS for that. I think there's a much more local interaction that's potential, but again, it really depends on what the boundary of your site model might be. If it's a small community, I don't think the NAAQS is necessarily relevant.
Okay, a question from Richard Honor. Thank you for putting these human environmental issues into FDA terms and terminology, rather than just in the usual terms of EPA environmental considerations. We are in the midst of an important transition that will place environmental toxicity and toxicology concerns directly into human health terms. So I guess that's not a question. So thank you.
I couldn't agree with you more. Thank you.
And also a thank you from Lisa Arkin for answering her question. And then finally, a question from Barbara Quinn. I missed the definition of adverse pathway. Can you define that?
So the pathway starts with a molecular initiating event. So some perturbation, it's meant to be a biological signature of that perturbation. So you get some sort of macromolecular interaction. It then results in literally in math terms, a transition state, so that now let's just talk about the tissue. The tissue then has cells that are perturbed. They're going to be at a different state of operation of homeostasis. They are now somehow manifesting toxicity. There are key events along that pathogenesis. So how does that initial event cause an adverse outcome such as atrophy or tissue necrosis, some other histological event, for example, the observation that we would not argue about whether or not it's adverse. What are the steps to arrive at that necrosis or adverse effect? That's what the pathway is. But it's a biological signature of an initial event. In the case that I illustrated, it was what is the impact of decreasing iodide coming into the thyroid, decreasing the thyroid hormones, which is one of the key events, and then decreasing thyroid hormones in the blood. And then what does that decrease in thyroid hormones in the blood mean to the developing tissue, say of a fetus? So that would be a pathway, an adverse outcome pathway of a perturbed iodide uptake by the gland, by that symporter called the sodium iodide symporter, the NIS.
Okay, that's helpful. Thank you. I don't see any more questions in the Q&A box. Are there questions out there? You can raise your hand or you can enter them in the Q&A.
Great. I think that means we get 10 or 12 minutes before our next speaker rather than just 5. So go get yourself a cup of tea, take a bio break, stretch your legs, and we will be back with Dr. Shanna Swan, author of Countdown from the Icahn School of Medicine at Mt Sinai in New York at 2:05 on the nose. And if you are listed as an anonymous guest in the attendee list and want me to change your name to identify you, please raise your hand and I will do that over the break. Okay, got a hand raised. Who is this? You have to unmute yourself. You have permission.
Yeah, I just did that. This is Greg.
Hey, Greg. Great.
Hey, BJ.
I did this for a few folks earlier and it worked for some and not for others, but let's hope it works now.
Yeah, I noticed I wasn't the only one showing up as anonymous.
Yeah. Okay, I think we got you. Good to see you here. Anyone else listed as anonymous? Heather, yours didn't stick, so if you're still here, I can change you back to Heather. Richard Honor, you can also raise your hand if you want me to correct your name. Okay, not required, just optional. We will see you back here by 2:05.
Look, here we are.
Go ahead, Darlene.
I can go ahead. Can you hear me?
Yep, go ahead.
Okay, great. My name is Darlene Shanfeld. I'm a co-founder of the Northwest Toxics Communities Coalition and a board member. And it's my pleasure and honor to introduce Dr. Shanna Swan. Dr. Swan is one of the world's leading environmental and reproductive epidemiologists. She is a professor of environmental medicine and public health at the Icahn School of Medicine, Department of Environmental Medicine and Public Health at Mt Sinai in New York City. Dr. Swan has worked for over 25 years to understand the threats posed by chemicals to our environment and our health, and, when necessary, to develop new paradigms to assess their risks. Of most concern to Dr. Swan are the chemicals that our bodies can confuse with its own hormones, endocrine disrupting chemicals. At the Icahn School of Medicine, Dr. Swan is working with a wide range of collaborators, including epidemiologists, biostatisticians, toxicologists, geneticists, and systems biologists, to conduct studies and develop methods to evaluate the risks from such chemicals. Methods that are sensitive enough to tease out the often important subtle health effects of complex mixtures. An award-winning scientist, her work examines the impact of environmental exposures, including chemicals such as phthalates and bisphenol A, on men's and women's reproductive health and the neurodevelopment of children. Dr. Swan's recently published book is entitled Countdown. There's another book, Countdown, but her book, it's 2 words, Countdown, not to be confused with the one-word book. Dr. Swan, thank you very much for participating in our summit.
Thank you, Darlene, so much for that introduction. And just want to check that everyone can hear me. Can you hear me?
Yes.
Good, wonderful. Okay, then I will go to my slides and I will go to slideshow. And can you see that now? Hello?
No.
No.
You cannot?
No.
Okay, hold on, let me go back. Oh, you know why? I bet I didn't share my screen. Yeah, okay. Share screen, share.
Yeah.
Now.
Yes.
Now, yes. Beautiful.
Yes.
Okay. Okay, slide show. How's that?
Excellent.
You see that first slide? Yes? Okay, good.
Yes.
Okay, so first of all, before I launch into my talk, I thought I would just tell you a little bit about myself because we have some time, right? And I have never worked with this excellent coalition. And so you don't know me very well and I don't know you. I'm learning a little about you. Now you're going to learn a little about me. So I actually worked in public health at the California Department of Health for 17 years and started a program there called the Reproductive Epidemiology Program, and was originally working on the effects of groundwater contamination by solvents and their effects on reproductive health. And that was a long time ago. But I got involved in the question of endocrine disruptors when I was appointed to the National Academy of Sciences Committee on what was then called hormonally active agents in the environment. And I didn't actually know what endocrine disrupting chemicals were at that time. That was the late 1990s. And the science I'm going to show you here was really what got me into the study of endocrine disruptors. But after I came back from some of those committee meetings and said to the health department that I thought we should have a program to investigate endocrine disruptors, it kind of fell on dead ears. So I decided I had to leave the health department and enter academia to do that work. And so that began the journey that I took from the health department, eventually ending up in Mt Sinai in New York, where I am now. Okay, so what I'm going to talk to you about is not really the book, but the subject matter of the book, which is really how chemicals in our world are threatening male and female reproductive health. So today I'm going to take you through this walk, if you will, through the problem, the causes of the problem, the consequences, and some possible solutions. And so let's start with the problem. So the first thing I want to point out is that these people in Houston, NASA scientists, are aware of a problem. They're intently, observing it and paying attention and figuring out how to fix things. We don't have that same attention yet on the problems that I'm going to describe to you. And I think the first step in the solution is recognizing the problem. So I think what kicked off my book and the current recognition of the problem, which is actually quite widespread now, is this paper that I published in 2017, which went global. And there were many headlines. One of these is not actually quite correct because it's who's killing America's sperm, and maybe it should be what's killing America's sperm, and actually not America's sperm because it's a problem worldwide. But nevertheless, I'm happy to say that this got a lot of attention focused on the problem. But this was not the start of recognition of this problem. So let's go back to 1992. There was a paper published out of Denmark, University of Copenhagen, first author Elizabeth Carlson. And this paper stated there has been a genuine decline in semen quality over the past 50 years. It included this graph. And by the way, the circles, the area of the circles are proportional to the log of the sample size. So basically, bigger circles, bigger sample size. And this was a very dramatic decline in sperm concentration from over 100 million sperm per milliliter to, I think it was 50 something sperm per milliliter, and roughly 1% per year. When this was published, there was a lot of skepticism, and one of the skeptics was me. I was asked by the National Academy of Sciences Committee whether they should consider this in their deliberations, whether this is important evidence of harm to humans from endocrine disrupting chemicals. Well, first of all, the study didn't talk about endocrine disrupting chemicals. It didn't talk about actually causes of this decline, except in the discussion a little bit. But this was problematic for a number of reasons, I thought. And here are some of them. Maybe the way that sperm was counted had changed over the study period. That could introduce a trend, right? Or maybe there was what we call selection bias. Maybe the men that were included were different in the early part of the study period and the late part of the study period, right? So maybe the men at the beginning had entered because they were proud of their sperm count, and the men at the end were concerned about their sperm count. You know, you can make up all kinds of scenarios like that. Maybe the men later on in the study period were more obese or more stressed or older or smoked more or whatever. In other words, there could be confounders and biases explaining this decline. So I decided that this was important enough for the committee and for our scientific community to really try to dig in and address some of those questions. And so I took 6 months when I was given a basically sabbatical to work on this with 2 colleagues from the health department. And what we did was we took the underlying 61 studies and we abstracted from those all of these variables that we could in order to try to explain away the decline. And it was a big job. And when we finished the analysis that included, you know, had these variables controlled for, the surprising thing was that the slope of the line had not changed to the first decimal place. It was stunning. And I published this in 1997. And I not only published it, but I was hooked then that I had to figure this out. If this was real, what was going on? So I did a series of studies. The second one was published in 2000. And in that one, I actually separated North American and European studies and studies from other countries. And as you can see in the middle of these 3 figures, that there's very few studies from other than North American and European countries. And there's also a difference in the slope between North America and Europe. But basically, if you looked at the overall slope, it would be just about the same. Even though the study period is not exactly the same, we actually had more studies and extended the study period. And we still found this very significant decline in sperm count. I did a lot of other things to examine this. For example, setting up a 4-center study to look at semen quality in 4 places in the United States, which I won't go into now. But ultimately in 2014, some colleagues and I got together and said, let's just do this right. Let's now use meta-analysis methods, which are available, which weren't available previously. And let's, you know, just do the ultimate study on sperm decline. So we designed that. We designed the protocol, which we published before we registered it before we conducted the study. We got a very good research librarian. And then we dug in and looked for all the studies that reported sperm counts in English language papers and in peer-reviewed literature. What we did that was different here is we looked at the year of sample collection, which I had done in 2000, but which Carlson had not done. So Carlson used the year of publication, we used the year of sample collection, which actually what reflects the sperm count in that year. And Carlson had identified 61 studies. I had identified, I think, 101 in the 2000 paper. And in this latest 2017 paper, which is the one that had the world headlines, by the way, we had 185. So it was bigger, it was more solid, and it was pretty definitive. But what you see if you focus on these, that there's 1 line, 3 lines, and 4 lines. What are the 4 lines? Let me break that down for you. So if you go into the Levine figure, you see that there's the red line, which is unselected Western men, and I'll define unselected in a minute. And then there's fertile Western men. So red and green, those are the Western men. And then there's the other, which is the unselected and the fertile. There really were very few studies from other countries. And what I'm going to say from now on is going to refer to Western, and actually it's going to refer to unselected Western. So what's the difference? Unselected Western are men who didn't have any knowledge, as far as we knew, of their sperm count. So they should be representative of the general population. The fertile is men who were fathers or married to pregnant women. So they obviously couldn't have as great a decline because they had to have a certain level of sperm to become fertile. So the best information, I think, is the red line. And if you look at the red line in the right-hand graph and the red line in the left-hand graph, you see they're pretty similar, although the years are different. They're going down at about 1% per year, a little greater than that. Okay. So one of the things that people have asked is, what happens if you extend this line? So let's look at this line in detail. Sperm decline in Western countries from unselected men. At the start of the study, 1973, the first year of sample collection, the sperm count was 99 million per milliliter. This is a very good sperm concentration or density. If you look at the end of our study period, which is 2011, it's 47, which is not at all a good sperm concentration. Why is that? Because when this number hits 40 or drops below 40, then we're in the subfertile range, because at that point, it takes longer and longer to conceive a pregnancy. So there's been some very nice studies showing the relationship between the per cycle probability of conception in relation to this number. And it doesn't increase, it doesn't matter much when sperm count is above, say, 50, 60, 70, you don't get pregnant much faster. But when it drops below 40, it takes increasingly long time. So this last year of sample collection was 2011. We are now at 2021. We're 10 years past that. The decline here is something slightly over 1% per year. That means in the 10 years since this paper was published, a sample collected today, we would predict would have a concentration of 37 million per milliliter, which is in the subfertile range. I just want to stress that. Now, we don't know that. We don't have those data. I'm actually in the process of updating this study, but that's something that I'm extremely concerned about. And if you do extend this line, I have to point out it can't ever hit 0, right? Because this is the median sperm count. That would mean that half of the sperm are negative, which obviously they can't be. So this 0 line is what we call an asymptote. We can come arbitrarily close to it, but never hit it. But if we can change things in some ways that I'm going to suggest, maybe this week we can make this curve veer off and follow the blue or the orange lines. So I want to say that sperm count is only one measure of semen quality. So that's the number, and we can also ask about the shape or the morphology. We can also ask about the motion or motility. They should be swimming at a sufficiently straight line, not in circles. They should be advancing. And we don't want two-headed sperm or two-tailed sperm and so on. So when you go for a semen analysis, you'll get those numbers, and you'll also, in many cases, get a measure of the chromosomal integrity of the sample. So in this diagram, what I've outlined is problems in the males, problems in the females, and problems that affect both. And what I'm going to talk about in this whole talk, I'll concentrate on a few of these, but I'd like you to keep in mind that all of these problems are with us, and they are all increasing, almost all of them, when we have the data at the rate of about 1% per year. And that's kind of stunning, I think. And I'll show you a couple of graphs. The males I'm going to talk about in most detail because that's the science I want to show you, but there's very good science in support of problems in the female. And when I say both, I mean that both can have or contribute to fertility, of course. Both can have ambiguous genitalia, hormonal abnormalities, low libido, and so on. So when we talk about problems in reproductive health, we're talking about everybody's problems. And maybe I'll just stop to say that this has not been really recognized historically. And one of the inequities, if you will, is that women have been historically blamed for the failure of a couple to conceive or for having repeated miscarriages. We now know that responsibility is shared pretty much equally between men and women in terms of male causes and female causes, or unknown causes, which kind of they can split. And then miscarriages also can be responsive to chromosomal damage in the male and older fathers and so on. So it's many of these things can't really be separated. And even though miscarriage I put here under the female, that should really probably be in the both, given what we know about causes of miscarriage. Okay, so here's a picture which is meant to convey to you that the 1% effect is driving all of these trends. Of course, I can't show you all of them, but I'm showing you a few of them. So there's the decline in sperm concentration in Western countries, but birth rates, number of children born to a woman or a couple, has also increased at about 1% per year. And these data are from World Bank. And in 1960, the average in the world was 5 children per woman or couple. And in 2018, it was half of that. So that's pretty much 1% per year. And it's interesting that it's going down everywhere. And miscarriage rates, we have less information. I actually have some data that would update this curve, and I need to do that. But if you calculate that rate of increase in miscarriage rate, it is also about 1% per year. So let's talk about causes. So first, I'd like to make a big separation between genetic causes and environmental causes. And these declines or these changes occurring over 2 generations are much too rapid to be solely genetic, although there's undoubtedly some gene-environment interaction going on here. So I'm going to leave aside the role of genetics, and focus on the environment. Okay, so now I'm going to make another big subdivision into chemical exposures and lifestyle factors. And I will talk briefly about lifestyle factors, but that's not primarily what I'm going to be talking about today, although I have studied many of these. So now if we come into chemical exposures, I want to make another subdivision, and I want to divide those into endocrine disrupting chemicals, chemicals that have the ability to interfere with our endogenous hormones, and other. And finally, to say that within endocrine disrupting chemicals, I'm going to focus on the phthalates primarily. I'll say a little bit about the bisphenols, but you know very well in this audience that there are many other categories of endocrine disrupting chemicals, and there's a lot of evidence of reproductive harm associated with those other classes. So I want to just stop and pause for a minute and point out that because these chemicals are not tested before they're put into products that are introduced into our homes and into our bodies, we are taking part in an enormous experiment in which we are the subjects and we are being exposed without our consent. And that is a situation that urgently needs to be changed. Just here are some examples illustrating these classes of chemicals. We have the fluorinated compound illustrated by a Teflon pan, phthalates illustrated by the rubber duckies. Of course, phthalates are anti-androgens. They make plastic soft and flexible. We have the flame retardants illustrated by the cushions, pesticides, and the bisphenols lining tin cans. And I don't show cash register receipts, but they're also in those, of course. And then another illustration of phthalates to emphasize that they are also in personal care products. And the production of plastics, which is where I do most of my work, has been growing at an incredibly fast rate. And just, think about where this started. It started after the Second World War, and it started there I think for a number of reasons, but one of them was that people were very enamored of science and scientists. And we had this whole era of, better living through chemistry. I have ads that say plastic, an important part of your diet, actually. So they were welcomed into our homes. And the fact that they are fossil-based and petrochemical-based means that they rose with the growth of the petrochemical industry. And also that they have an intimate connection to climate change. So now I want to hone in on one particular category of chemicals and one particular reproductive outcome. So let's talk about the development of the reproductive tract. And this is where a lot of my work focuses. So this schematic is just a cartoon, if you will, but it's meant to illustrate that originally the sex organs are undifferentiated. For example, a single ridge in an animal between the same in males and females. When testosterone starts to be produced by the fetal testes, then that undifferentiated sex organ differentiates and becomes male typical, that is for a genetic male, and female typical. So what can interfere with testosterone? So here's some examples. It's the phthalates that are found in these personal care products, in our home products, or even very surprisingly, perhaps, in all kinds of tubes used to process foods, such as this milking machine. So all of these contain either diethyl hexylphthalate, dibutyl phthalate, which have the ability to lower testosterone. What does that mean? Well, here's a nice study by Parks 2000. And what you see on the left is that when the mom is not exposed to any phthalates, the male experiences a surge of testosterone in a narrow window of gestation. But when the mom is exposed to phthalates, and this is DEHP, diethyl hexylphthalate, that surge is depressed. So this is a very nice illustration of how testosterone surge that's needed for differentiation of the genitals is not happening because of exposure to this phthalate. And what that means, as was shown by Paul Foster and Earl Gray in the early 2000s, was that the male is born with genitals that are slightly less masculine than expected for his genetic sex. Some measures of those are that he will have a somewhat smaller penis. The penis can be malformed, for example, hypospadias, which is when the urethral opening is not at the head of the penis, but is on the shaft. His testicles may be undescended, but not completely. And he might have a shorter anogenital distance. It's this measure, anogenital distance, I want to call your attention to. Before I do that, I want to point out that the amount of testosterone change does not have to be great. Okay, we're talking about very, very low doses. And this is surprising, perhaps, but the early studies of intrauterine position, which some of you may be aware of, I think they're really beautiful, beautiful studies, showed that when a male was gestated between two females in a rodent in the uterine horn, that male was less completely masculinized. And when the female was between two males, she received a little bit of testosterone, which made her less female typical in her physical appearance and also in her behavior and her sexual behavior, in her mating and her fertility, and also for the male. So I recommend these studies to you if you're interested in this. You look up intrauterine position effect, fetal position effect, testosterone transfer. They're really, really interesting and point out how much a small amount of testosterone change matters. So the anogenital distance is very, very sensitive to the level of testosterone that is the fetus sees in utero at a particular time. And it's normally 50 to 100% longer in males than females. Data on this has existed for over 100 years, and it's actually been used in toxicity testing for quite a few years now, almost 25 years. But it was not used in human toxicology until I looked for the Phthalate syndrome in humans. So this is just to stress again that the amount of testosterone that can make a difference is a drop in a swimming pool. We're talking about very, very small doses. And this happens in utero at a certain time. So we asked, are the levels of phthalates in the mother related to genital development in humans? So basically I was asking, is there a human phthalate syndrome? Well, fortunately, I had a population of pregnant women for whom we had saved urine during pregnancy. I wasn't sure why I saved it at the time, but it turned out to be extremely useful. And we could bring the babies back and we could measure that anogenital distance, penile width, testicular descent, scrotal size, and ask the question, are the levels of urinary phthalates related to this development of the male genitals? And the answer was yes. So we published in 2005 first this paper saying decrease in anogenital distance among male infants with prenatal phthalate exposure. This was pretty big news when it was published, and actually I think influenced the decision to keep phthalates out of children's toys, although that's a little bit wrong in terms of who's being exposed there. But nevertheless, it did have an impact and it did take phthalates out of a lot of products. Then we got money to replicate this. Each of these studies, by the way, takes about 5 years and costs about $5 million. So this is a big thing to get a replication of this. So the second study was published actually just in 2015 and was done much more precisely, and I'll show you an example of that. And what we really showed, both in this study and many other studies that have now been done on this, that this anogenital distance is a very important marker of fetal androgen exposure. And I'm going to show you it's also a marker of later reproductive function. So here's the question. Is AGD related to sperm count? Well, we couldn't answer that question with our babies because they didn't have sperm count and we didn't have 20 years to wait. So then you have to know that in animals, the evidence is that a short AGD at birth means a short AGD through life, adjusted for body size, of course. So we went to adults and we got, these were young men in Rochester, New York. We got their semen sample. They let us measure their AGD. And what we showed was that the longer the AGD, the higher the sperm count. And then Mike Eisenberg showed that infertile men also had a shorter AGD. So AGD in males tell you what was the androgen level they were exposed to, something about that, and how are they going to function as adults. By the way, it also is a marker of in females who also have testosterone, but less of it. And when they have excess testosterone, they have a longer HED. And we showed that in daughters of PCOS women who have higher levels of androgen. Okay, so now I think you should be convinced that at least one class of endocrine disrupting chemicals is related to sperm count and may be playing a role in that decline that I showed you initially. What I haven't showed you is that the timing of this is really, really important. So it turns out that the critical window for rodent AGD is these just 3 days in what's called the male programming window, days 15.5 to 18.5. And I wanted to look at that in humans, but the problem is for the males, you can dose the mother at certain days, but you can't obviously do that to humans. So we had our studies, of course, are observational. So what we did was we had 3 trimester urine samples, who had samples from the first, second, and third trimester. And what we saw was that the decrease in anogenital distance was only seen in urine from the first trimester. So I believe that with more urine samples, we could pin this down to a smaller window, but this is the closest we were able to do with the data that we had. The other question of timing that I want to point out is that when a change occurs in utero, it causes a permanent change. That change is permanent. When a change occurs in adulthood, it is transient. So here's an example. I use smoking for this because I don't have these data for phthalates. But when the man is smoking around the time of conception, and by the way, male exposure in that window before, while that sperm is being produced, which is 60 to 70 days, the sperm that's going to, conceive that baby, fetus. In that period, if he smokes, his son can have a 40% reduction in semen quality, sperm count. If the mother smokes during pregnancy in the critical time, the first trimester, then her son will have a 40% reduction in his sperm count. But if the man smokes, his reduction is going to be less. And here's the good news, if he stops smoking, it can revert to, he can recover his sperm count. So here's the lesson: prenatal exposure or periconceptional exposure is permanent. Adult exposure causes damage that is transient. And I said I would say something about lifestyle. I've published on all of these factors, but I can't obviously show you all the data, but diet matters, and the evidence is pretty good that the Mediterranean diet, in particular low-fat diet and diet free of processed foods, is going to be good for sperm count. Binge drinking is bad for sperm count. Stress is also damaging to sperm count. Heat, surprisingly, is damaging to sperm count, as is obesity and lack of exercise. All of these things can matter in adulthood, and they can also matter to some extent if they occur in the father around the time of conception or the mother during pregnancy. So let me talk about some consequences. It's pretty surprising to learn that men with low sperm count die earlier. There have been a couple of papers on this, and this paper from Denmark, Tina Jensen, showed that whether or not the man had given birth to a child, he still had a higher probability of death when his sperm count was low. It was more marked when he had never had a child, but you see, below that critical 40, remember I told you 40 million per milliliter was critical. When you go below that, you're increasing your risk of a shorter lifespan. There's also higher risk of heart disease, diabetes, and reproductive cancers. So some people have said that reproductive health should be considered the 6th vital sign, and that I recommend that every man should know his sperm count. And another consequence, I don't have time to go into the non-human species, but there is hardly a species on the planet that has not been exposed to and affected by these chemicals. And we have, I'm sure you're very aware of the damages to these species, the decreases in fertility. And for example, for the alligator, the small penises. I haven't shown you frogs, but we have frogs with ovaries and testes in the same animal, all kinds of disturbances in the reproductive system of these animals. And they didn't ask for this. We polluted them. And finally, I want to say that we're not just exposing ourselves. The pregnant woman is exposing her fetus. And then we have to remember that within that fetus, there are the germ cells of the next generation, the reproductive cells. So the mother's exposure is affecting 3 generations at least. And there's evidence that there are further generations affected. So I just want to say that when we looked at the sperm decline data, we looked to see, this is 40 years basically. We also looked for the last 30 years, the last 20 years, the last 10 years, hoping to see that the slope was going to be leveling off, that it wasn't so steep, but we did not see that. And so I think we have to push ourselves to make changes which will bring us to the orange line or even to the blue line so that we can avert this pretty catastrophic decline that we're in right now and avoid this scenario. So what are some possible solutions? I'll tell you this very nice work from Pat Hunt's lab at the University of Washington is really encouraging, because what she has shown that in mice exposed to estrogen, when the father was directly exposed and the son only indirectly exposed in utero, but the grandson was unexposed and the great-grandson was unexposed to any hormone disruptors, that the great-grandson recovered full reproductive function. So Pat says it takes 3 generations, which is good for rodents who have an intergenerational gap of 2 years. It's not so great for us, but at least we know that this is possible. In order for this to happen, I have some suggestions. The first thing is that we have to stop regrettable substitution. For example, swapping out BPA from our bottles that are labeled BPA free, but putting in instead another bisphenol like bisphenol F or bisphenol S, which do the same thing. And this is going on all the time. And we have to test the chemicals that have been untested, that have been left untested, that were grandfathered in. And so here I have three R's, but they're not the usual 3 R's. I suggest removing hormonally active chemicals. Easier said than done, of course. Removing chemicals that cause harm at low doses, because as I've tried to emphasize, these effects occur at extremely low doses and animals are seldom tested at very low doses. We want to remove chemicals that are environmentally persistent, because certainly for the chemicals that stick around for more than a few hours, we are going to meet them again and again in our water, in our food. And we need to test the chemicals that are previously untested. And we have to replace them with chemicals that do not have endocrine disrupting effects, that are free of low dose adverse effects, that are minimally persistent and are shown to be safe prior to marketing, as is intended under REACH, which requires manufacturers to show that a product is safe before it's put into the market. And we have to regulate at the scenario at which we are exposed. We are exposed to low doses. We are exposed to mixtures. We're exposed to chemicals that are in our environment and persist in our environment, and we are exposed to untested chemicals. We must regulate at human relevant scenarios. So I'm going to stop. I want to thank my funders, NIEHS, US EPA, all the participants in these studies, huge study staff. And finally, I just want to suggest that if you want to read more, you read Countdown. Thank you.
Thank you, Shanna. It was a great talk. Those of you in the audience, you can ask questions by raising your hand and I will unmute you, or by typing in the Q&A box. So I see some questions in the chat from panelists. Let me find those. Okay, so this is from Briana. Very interesting work, Shanna. Did you also consider other factors such as lifestyle that may be contributing to risk of death when investigating links to reproductive health?
Yes, Briana, as I mentioned, I only, passed over the lifestyle factors quickly, but that's something that I've studied as well. And certainly these can interfere with, say, semen quality. In our Rochester young men study that I talked about, where we measured AGD and sperm count in young men, we also gave them a food frequency questionnaire, and we also asked about their, their exercise and their lifestyle habits and so on. And we published, I think, about 8 papers showing a number of factors in diet and lifestyle that affect semen quality. So they definitely do. In the trend analyses that I showed you, we can't do that, because in order to do that, we would have to have that information for each of the 185 studies, and we don't have that. So, that's maybe a weakness of those studies. You can't do that in a large meta-analysis.
Okay, thank you. This is from Darlene. Shanna, I work on issues related to the land spreading of sewage wastes. These are spread on croplands, injected into aquifers, on recreational lands, wetlands, etc. 80 K plus toxins and viruses. We need, Darlene, part 2, legislation to stop this. It is in compost and fertilizers. The public is not informed. This is a major cause of animal and human problems. Sorry, read that. Shouldn't have read the Darlene part 2 in there. Let me know if you want me to read the whole thing over.
That's fine.
Yeah, well, that's not really a question, I guess. It just points out another important source of exposure. And obviously we need legislation to control that. I totally support that. But I can't really, I have not something I've studied, so I can't really comment beyond that.
Okay, thank you, Shanna. Now a question from Greg Wingard. Have you looked at distribution of chemicals and exposures by chemical categories, such as plastics, consumer goods, versus pharmaceuticals?
So we don't, okay, let me see. Yes and no. I will say yes and no. Okay. We ask our subjects about their use of personal care products, their, whether they eat organic, whatever you can determine by questionnaire. But we find that really the best measure of exposure is urinary metabolites. So if we want to know what the exposure is in a woman at a certain time, you have to look in her urine or for the persistent compounds in her blood. However, your question goes to another issue, which is, where are these things coming from? And we need to know that in order to remove them, And there's been a lot of work showed that foods are a major source of a number of these exposures. And they enter, phthalates and the bisphenols enter the food through processing, through packaging, and sometimes through cooking, unfortunately, in plastic. tin cans, through canned foods in tin cans convey the exposure to bisphenols. Pizza boxes might convey exposure to PFOAs. So, you have to look at the particular chemical and see where it is to find, what the particular route, where it's coming from. But really, there's much too little information, I think, on that question. And I personally am very interested in finding out more about where these things are coming from. As far as pharmaceuticals, that's a whole other huge question and very important, I think. There's the question of hormones that are excreted directly, in urine, into the water supply, that are not completely removed. And then there's hormonally active pharmaceuticals. For example, I've done a lot of work recently on acetaminophen or Tylenol, which actually has a lot of properties in common with phthalates structurally, chemically. So I think looking at the hormonal action of our commonly used pharmaceuticals is a really important research question.
Okay, great. Next question is from Richard Honor. A missing element in your work may be a deep investigation of endometrial microbiomics, because some microbes produce hormone mimics or other metabolites that may influence any of the many functions that may lead to pregnancy or not.
I don't know anything about the endometrial microbiome, and I probably should. And it's really interesting. That's the first I've heard of it. And I don't see the name of the person who asked this question on the chat.
This is Richard Honor.
It's not on my chat.
Oh, this is not in the chat. This is in the Q&A box.
Oh, okay. Oh, I see. I don't see it either. I just see two questions in the...
It's anonymous.
Oh, anonymous. Oh, great. But there's no name. Oh, Richard. Okay, Richard, good. So, Richard, I would actually like to have a reference. If you could send me a reference to shannaswan.com, that would be great, because that would be interesting. I don't know anything about this.
Okay, great. And the next question is from Fran Solomon. In addition to being anti-androgens, do phthalates also mimic estrogen?
Good question. So not to my knowledge directly, although they can affect the testosterone estrogen balance, which is regulated through feedback mechanisms. So, but I'm not, I don't study that in the laboratory, so I don't know more than that.
Okay, thank you. We have a question in the chat from Annie Jarabek. I was intrigued by your emphasizing the low dose, e.g. drop in swimming pool. I had the exact same challenges with perchlorate. It is my sense that hormonal disruption is difficult. By definition, hormones act at low concentrations. But then when we try to approach hormone disruption from chemical assessment perspective, the exposures are too low. Thoughts on how to rectify this scale misperception?
Thank you, Annie. I think I appreciate, and agree that hormones act at very low concentrations. I think we've shown that they cause harm at low concentrations because we measure them at low concentrations and we see their harm, right? So it's certainly possible to do this in animal studies. However, we're just going to have to do, mega animal studies so that we can expose at low doses and demonstrate this. And we have to not assume monotonic dose response. And this is really critical because many of these things do not, just like hormones, do not act monotonically.
If I could just unmute, I agree, but what I was trying to get at is I can't tell you how many times I had to say that thyroid hormones are a hormone. So yes, perchlorate is affecting at a very low concentration, but there was this pushback. I mean, I even said at one point, they said, well, you're trying to regulate, or you're trying to do your assessment on a precursor of a potentially adverse effect. And I didn't even, we had difficulty saying, but every baby in this country that's born gets its heel pricked because thyroid hormone is important.
Yeah.
Why should not we then be able to do a chemical assessment based on thyroid hormone perturbation?
Right.
And it always came back to the fact that too low, I had in quotes, they just kept saying it can't possibly be happening because those exposures are too low, let alone hormesis or non-monotonic. I mean, just the fact that hormones are operative at low levels and anything that disrupts them is going to be at a low concentration, I think is challenging enough. And we demonstrated it as well. We've got plenty of data on perchlorate, but it just didn't get a lot of traction. And I just wondered what your thoughts were.
My thoughts are that that's political, political and economic, actually. And I think that that's a fight we're just going to have to take on. And the fact of the matter is they do act at low doses, and we do have low dose effects, so we just have to keep showing it and keep arguing for it. I agree.
Well, I would offer to add perchlorate in your mix, because maybe, if we can keep emphasizing, yes, by definition, hormones act at picomolar range.
Right.
Why is it a surprise?
I know. I mean, somehow people don't get that you can have different adverse effects by different mechanisms at high and low doses. I think that's a large part of it. Like studies are designed, you have a high dose, there's an adverse effect, and if there's another mechanism causing another adverse effect at low doses, you'll totally miss it, right? But we just have to redesign the regulatory structure to examine those.
Right. I think the more mechanistic we can get, the better, so that we can actually make these arguments key event by key event.
Definitely.
Mm-hmm. Okay, this is a question from Heather. She says, wonderful talk. And in your giving of this presentation around the US, maybe the world, have you learned of any efforts to identify phthalates in products? We are currently working to ID phthalates in outdoor products in an EPA-funded study.
Heather, where do you work? I would like to connect with you, because yes, we've identified phthalates in lots of products. I mean, first of all, personal care products. We've identified them in, they're in shampoos, they're in nail polish, they're in lipstick, they hold scent and color and fragrance. They're in foods. They've been demonstrated in foods. They're just, I can't even, there's many demonstrations of phthalates in everyday products. However, what I would like to see is, and I'm actually think I'm going to be able to do this study under private funding, because I can't get it funded nationally, is a study where we look at a product at the time it's grown, maybe even examine the soil and so on that it's grown in, and see what chemicals, phthalates, and so on it contains at the time of its picking, and then at the time of its processing, and then at the time when it's in the supermarket, and then at the time it's on the plate. And I think we don't know very well where endocrine disruptors or phthalates and others are introduced along that pathway. Where are the intrusion points, if you will, for these chemicals along that pathway? Until we know that, we can't stop that intrusion.
So this is Heather. So I'm at Zero Waste Washington here in Seattle. We're statewide. And we are working on, this is the second phase of looking at phthalates in products that are used outdoors, because it's actually a stormwater water quality funded study for EPA.
Mhm.
And we studied, we assessed 213 products in the first round. 46, I think, of them had phthalates in them, including brake pads.
Hmm.
So that means we're dusting the freeways with our brake pads. You know, it's
Okay.
already a problem for Sam and Coho with the tires, and copper from before in the brake pads, but the tire chemicals. Anyway, so we had seen that there was a ton of work that had been done on interior use products, things like personal care products and flooring, like you mentioned, but very little on things that are used outdoors. So that's why we're doing this study. And what is really interesting is that you know, those colorful plastics they use for crosswalks. They make like these artistic crosswalks,
Yeah.
plastic that you're melting onto the
Oh.
asphalt. That had phthalates in it if it was colored, but if it was white, it did not. So the brightly colored ones did. So we found quite a few very interesting things, and we're about to do another round of testing, which is why I asked the question, because we'd like to sync up with anyone else who's actually currently doing assessments of phthalates in products, which I think is kind of a limited number of people doing that effort of currently looking. So we'd like to be in sync with them. And we're using the 9 phthalates that Ecology currently uses here in Washington State for Children's Children's New Products Act. So they're 9 phthalates. So, and this is all products that we're acquiring. These are the products you would acquire to use as a consumer or as a you know, commercial or agency. So these are the products ready to go into use at that point.
So Heather, what about PVC hoses, garden hoses? Have you looked at that?
We did not look at those, but we could the second round. In fact, that's a good idea. We did not. We looked at a ton of paints. We looked at a ton of paints, and they did not have phthalates in them.
No, I wouldn't expect they would. No.
Well, in the past they have, but they did not. And in fact, we talked to one chemist. He said, "Oh yeah, we took those out several years ago." So the paint industry has gotten ahead of the curve and got the phthalates out.
But the real risk, the most risky thing is when the phthalate is heated, right? When the product is heated, because microwaving is the worst, of course, microwaving in plastic, but the nice example that I like to give people is phthalates in medical tubing, right? We did a study in Mt Sinai where they counted the number of lines coming into a newborn in the NICU, and that infant's phthalate levels were directly proportional to the number of lines going into them.
Yeah, that's terrible.
So any tubing, it could be for in blood bags, it could be dialysis. They're all introducing phthalates into our bodies. No bueno.
House plumbing is being put together with what we call PEX tubing now.
Sorry? Say it again?
PEX tubing is being used for plumbing in buildings and houses, residential especially. Plastic PEX tubing for
I'm writing that down.
Hot water and cold water. The tubing used for the hot water, if the water, once you have it sit overnight, you open the faucet up, you take a drink out of the glass without letting the water run, you'll know you're getting a big dose of phthalates right there.
Wow. So how do you spell that tubing?
P, capital E, capital X.
Oh.
PEX. Home Depot, Lowe's,
wow.
You name it. They have flex tubes used for plumbing, specifically between the hot water heater and the house plumbing, that has PEX tubing on the inside of it. It's metal on the outside. But on the inside, it's plastic tubing.
Oh my gosh.
It contaminates every drop of water that comes from the hot water heater. Now,
That's
what do we use hot water for in the house?
So since I think they want to move on with other questions, but if anyone does have products that they want us to test, we're probably gonna be testing them this summer or in the fall. So give us the list so we can get them tested.
Wow.
Yeah.
Cool.
Yeah, I've been wondering for a while with the large number of people with sleep apnea. Have we looked at CPAP machines, whether or not there's any exposure to phthalates?
I'm sorry, looked at what?
For people with sleep apnea.
Yeah.
They wear these CPAP, they have a CPAP machine and all these tubes.
Oh.
So they're wearing these tubes at night, every night.
Oh my gosh.
and there's water that's warmed in a reservoir that actually keeps, sort of a warm stream of air going into your nose. And from what my understanding is that sleep apnea is quite common nowadays. It's gone up quite a bit over the last 10 years or so, and the number of people using these machines is
Tom, I'm a former sleep disorders therapist.
Oh.
And yes, you are right. But the increase in sleep disorders has a lot to do with diet, weight,
right,
environmental exposure. I mean, you name it. Thin people can have the sleep apnea, but it's usually those above 10, 20% overweight. But if you're in a particular toxic environment, you're going to have it. And definitely the CPAPs have, oh gosh, when did they? Kind of came in the 1980s, and that's often what the doctor orders for you.
So I'm going to interrupt because we're actually jumping in front of some audience Q&A that's still waiting, and then we can come back to this conversation.
Okay.
But that would be a good one to look at.
Yeah, thank you. Scary.
Yeah, we have one more question from Greg Wingard. Part of the reason I asked is about sources relating to dosage consideration. Example, food sources, lower dose rates, longer exposure duration. Pharmaceuticals, potentially higher dose rates, shorter exposure durations. So how does dose rate and duration impact outcomes?
Well, the home exposure is low dose continually. I mean, right? They're coming into our bodies. We're repeating our, usual habits, and we're getting exposed continually. So the half-life of phthalates is 4 to 6 hours, but if they're coming in all the time, we're getting them all the time. So I think that scenario is low dose, continual exposure. Pharmaceuticals, depending on what they are, can be also a pretty higher dose, maybe. I don't know how to compare actually a dose of, like the anti-androgenicity of a day's supply of Tylenol with a day's hit of DHP. I don't know how to compare that. But in our studies, and I've done several of them in Sweden and the United States, over 50% of pregnant women take a lot of Tylenol. They take it and they take a lot of it. One of the categories for women asked how much do they take since they became pregnant till the time they got into the study was up to 100. And some women had as many as 100 pills. So, I mean, I think for a number of these pharmaceuticals, we're getting also a pretty constant level of exposure. Through the pharmaceuticals that we're getting through our water supply, obviously will be a continuous. So I'm not sure it's that different. It is different if it's a pharmaceutical that you take occasionally at a high dose. I don't know about that, but the only pharmaceutical that I've studied in any extent is the acetaminophen or Tylenol.
Great, thank you. I have a question from Patty Martin in the chat. What role, if any, do these chemicals have on sexual orientation, etc.? Feminization of the male brain can occur when testosterone doesn't kick in at the right time during gestation, and feminization of the male genitalia is an issue. What role do EDCs play in all of this? I am asking this because if this is related and could be explained to the general public, maybe there would be more tolerance if there is an environmental cause rather than what is perceived as a personal choice.
Well, Patty, you jump right into the most difficult and controversial area in this whole, can of worms, if you will. And in Countdown, we have a chapter called Gender Blurring. And what I want to say a few things. One is that I'd like to separate out different issues which might seem to be overlapping. One is disorders of sexual development. That's physiologic. That's, for example, can be caused in animals by environmental chemicals, say atrazine. Tyrone Hayes produces frogs that have ovaries and testes in the same animal. That's definitely a disorder of sexual development. There's no question that chemicals can do that. Okay, so that I think we can just put aside. Whether there's more or less of those in recent years, I don't think anyone knows, because that's not been tracked historically. The next question is homosexuality. So you can also produce animals in the laboratory that behave, that prefer same-sex mating. And so there is probably some environmental chemical component to that. There is also undoubtedly a genetic component to homosexuality. Homosexuality has been constant in its rate historically for a very long time, and it's also present in non-human species. So I think, yes, there may be an additional component from environmental chemicals, but that's certainly not what's causing this. Okay. When we come to gender identity, then we have a whole different set of problems, because gender identity is how you feel about your body. And we cannot ask an animal, how do they feel about their, their genetic, their organs, their genitals, and so on. So it's a question of sense of self and how you identify. So I don't think we know whether these chemicals are playing a role in problems of gender identity. And I also don't know whether they've increased, because we have no historical background data on that. So I think, this is a question I've discussed with people on the LGBTQ spectrum. I've been on a webinar with people on the spectrum. I've shared these thoughts, and I'm learning. I think we're all learning this. I think we don't know this yet.
Okay. Lisa, excuse me. I was going to say thank you for that response. The reason that that I asked that is we just come out of 4 years of total intolerance, and it seems if there were an environmental cause that could be explained to the general public, maybe that would, I'm not going to say eliminate, but potentially reduce some of that intolerance that has been just really antagonized over the last 4 years.
I appreciate the desire to make this less loaded. I don't think that if we could identify, for example, environmental chemicals that were related to gender identity, I don't think that would make a lot of people happy, because usually the way we talk about changes like decreased sperm count or decreased fertility, we're talking about this being a bad thing, right? I mean, I don't think anybody's very happy that sperm count is going down or fertility is going down. So if you wanted to argue that environmental chemicals were related to an increase in gender dysphoria, I think you would get a lot of pushback from people who say, I don't want that to be medicalized. I don't want that to be stigmatized. I don't want that to be thought of as a bad thing. I think we have to be really careful here, and keep an open mind. And by the way, it's not necessarily true that all the effects of environmental endocrine disruptors are negative. And let me just give you one example. Endocrine disruptors lower testosterone, definitely. We've seen that, we know that, we can measure that. However, there's also there is a global decline in testosterone. That's true. Whether that's a bad thing, I'm not going to say that's a bad thing. I mean, maybe that's a good thing. Maybe, maybe it's making us less violent. Maybe it's, as Steven Pinker claims in Angels of a Better Nature, by the way, that, humanity is becoming less violent, and that would correlate with decreased testosterone. So I think we just have to be careful and not keep our value judgments out of this area.
Great. So I just put a message in the chat. It's possible the Q&A may no longer work for you. Panelists were finding it didn't work for them during the talks today. So just go ahead and raise your hand if you have a question or want to talk. And that way we'll keep from talking over each other.
Patty, would you like to officially welcome folks to our after party now that everybody has been promoted and is in the room?
I didn't realize we'd reached the after party yet, but welcome everyone. And it would be really nice to see some faces on there. So hello, Lisa. I know Greg's on there someplace. Jean Mendoza, a couple of our board members, Barbara and Doris. So, and Dr. Carpenter, I didn't get a chance to really thank you after you presented. That was amazing. Lots of very good information. So to all the help we had gotten from the University of Washington Superfund Research people, Lisa and Tom and BJ, in helping us get this together, and to everybody that attended and to our speakers in particular for agreeing to do this. Thank you very much. And so now the after party begins. And so it's an open forum with some controls, right, about raising your hand and questions to our panelists. Some exchange.
So I started it just a few minutes early, Patty, because I knew that Dr. Swan was going to have to leave us. And since we seem to be wrapping up, I wanted to just invite everybody in while we still have her for another 10 minutes, but also to point out to everybody that I believe all of our panelists are here now. So this is really just meant to be a time to meet each other, maybe have some questions between panelists if there are some, or questions for all of the panelists that you met today. So thank you for joining us.
This is no time to go silent, people. Okay, this is your time. This is your opportunity to talk.
I might say that any of you that have any questions around plastics and your water, you might think about the sources at your locality. In other words, your residence. How is that water being moved from point A to point B? And specifically, how is it being moved from the water main to your house? You may find out there's a lot more plastic involved. In fact, the city of Portland is now has the practice of lining their older lines with plastic. These are the main lines.
Yeah.
So be aware of what's around you. Check it out.
Thank you. I just see Greg has his hand up.
Put my hand up.
Greg, do you want to unmute?
Yeah, I've got 2 mutes, so I get a little confused. I just wanted to say great presentation on endocrine disruptors. Very much enjoyed that. And great thing about these seminars is the ability to get a lot of information about frontline research that's happening and policy considerations, as well as practical things like how to measure impacts at Superfund sites in different ways to actually get better outcomes and get a better focus of how to get to those outcomes.
I have my hand up.
Okay, Darlene, go ahead.
I forgot my question to the speakers, but Heather, you're still on. Oh, the plastic pipes. Okay, John. So whole house filters, carbon filters, would those help? That's my question to you, John, and to Heather. Are you looking at and maybe Shanna too, are you looking at the chemicals in rubber hoses, garden hoses? Those are supposed to be the safest. I'd like to know if they are, but in the ones that are not, there's often lead in them as well.
Well, I can quickly answer that. We only have funding to look at phthalates. That's expensive enough as it is. If there was extra funding from somewhere, we would actually love to co-assess for other chemicals. But that's a good idea. We'll look at rubber as well as we'll look at a variety of hoses. That's easy for us to do. I should note that one thing that we also found in that first round was the wrapping, those ads that you put on a bus that wrap the entire bus and it's all one big advertisement, that had phthalates in it too.
So to answer your question about whole house filter, very few of them remove phthalates. They're designed to remove debris, basically. You're also in a situation whenever you're dealing with any hose of any type, if you leave it in the sun and it gets hot, then it releases anything and everything that's in the, not only brass fittings at the end, which can contain lead, but in the tubing itself, which could be rubber, poly, PEX, and whatever else. Temperature rising above 40 degrees is going to release any of that into the water that flows through. So basically, the safer way to do is go to the stream and scoop it up with your hand. Sorry.
Okay, I see Fran Solomon has her hand up.
Okay, a comment and a question. So first, Dr. Swan, thank you for your excellent presentation. I've been reading your book, really enjoying it. I teach classes about endocrine disruptor chemicals, so I will be incorporating some of the latest findings from your research into my upcoming classes. So thank you for speaking today. And Heather, I have a question for you, Heather Trim. I am intrigued by your study of phthalates in outdoor products. When do you anticipate a report might be out, and might it be possible for me to get on a list to get a copy of it? Oh, you're muted.
I can send you privately the first phase, and Sean, I can send it to you as well if you'd like. Because we're not publishing it, because we decided, since we got the funding to do phase 2, that we would make it a better report with the second phase of data. And also we're looking at the leachability of those products in terms of getting into stormwater. So that kind of gets at your question about like what happens to the phthalates. By the way, a lot of people said, well, what about off-gassing? We said, yeah, we're just looking at the products as they are put in place, like when they're on the road. We're not looking at off-gassing. That's a whole nother question, right? So let me know and I can send you we're not publishing it yet, is the bottom line.
Okay, I will email you. Thank you, and it's good to see you.
There is a comment in the chat from Jean Mendoza. It says, Heather, to conserve water, farmers now use micro drip irrigation that requires plastic piping that is changed out every year. Thanks, Jean.
Well, not only that, you know, there's this whole huge, I mean, we're also working on plastics generally in terms of usage, and the ag community does use a ton of plastic for what they call plastic mulch. And when we did a bill a couple of years ago in Washington, because the ag lobby is so dominant, we had to exempt the ag mulch, which is essentially plastic film, from the requirements that it has to be truly compostable. And so I think I'm going to add to my list right now, because I hadn't thought of it lately, but I'm going to add the ag mulch film as well. It is really disgusting because in a lot of Europe, they've been using it for decades, and they just plow it under. Little teeny bits of that material are getting plowed under. I have no idea if it has phthalates in it or not.
Okay, Lisa Arkin has her hand up.
Thank you very much. What an inspiring day. But my question, or my musing is, I'd asked the question earlier about fire, wildfire debris in urban and suburban areas. And at the time I asked the question, I was thinking about heavy metals and asbestos and things like that. But now I'm wondering, does it make any sense to try to measure phthalates in contaminated soils from fire residue where buildings and sites are burned? And then how would that be measured?
Can I say that? Yeah. So I would just say, I think that's a great question. And I wanted to thank you, Fran, by the way, for reading the book and using it for your class. But as far as phthalates in fire residue, I think California would be a great place to look at that, right? I am going to be talking to people from Cal EPA, and maybe I'll make a note to talk to them about that. But I don't do that. I measure phthalates in people. I don't measure phthalates in products. So I can't really speak to that, but I would guess that they're going to be there. Microplastics for sure, right? Yeah.
And it's easy to test. So the phthalates is commonly tested in soil samples, water samples, and air samples. What we had to push the envelope on was sampling in products, because it overwhelms the lab equipment. So we actually could only go down to 100 part per mil on our lab method detection limit, because otherwise we'd blow the equipment out. There's so much, in other words, there's so much. Yeah. Yep.
I see Annie Jarabek has her hand up.
Yeah, I'd just like to answer this. So my office within ORD is in charge of the wildfire initiative for EPA, and I will be happy to ask. He would be down the hall, but we're still working remote. I'll send Jason Sachs an email and ask whether or not they've identified phthalates. But we're finding all kinds of chemicals from PVC pipe in the residues. And it's been a problem. So, but I can't say for sure whether phthalates have been looked for.
Well,
but
phthalates are an intimate part of PVC piping. So they're probably, yeah.
Thank you. And this is for the fires in Southern Oregon, specifically, that ripped right through 2 cities. So that's why the debris is of concern, because it was mostly older trailer or mobile park homes for low-income families, and a lot of industrial sites like car repair and brake lining repair, a lot of that kind of working class neighborhoods. And people have said that their PVC pipes melted in the fire, yet they're still getting water through them.
Yeah, just so that you know, we're finding that even though houses that were unaffected by the fire, they're the ones getting the exposures because it's coming into their pipes. So just if you have the opportunity to tell people and make them aware, they're actually more at risk because they were, not hit by the fire, but they're actually more at risk for post-fire exposures.
I'd just like to thank everybody and thank you for having me. I'm going to have to hop off, but it's been really, really interesting, and I love your questions. And I hope that I can, those who want to follow up with me, you can find me on shannaswan.com. And thank you. Okay.
And thank you, Shanna.
Thank you, Shanna.
Thank
you.
Yeah,
Thank you so
much, Shanna.
Bye-bye.
Wouldn't
Darlene
the,
has her hand up. Doris, I see you, but I think Darlene's had her hand up for a while.
Wouldn't talking about fires, Lisa, wouldn't a lot of that come from the fire extinguisher by the fire companies, their hoses maybe, although I think they use rubber, but maybe in the chemicals they use to put out the fires? It's a question for Lisa.
Which Lisa?
Lisa Arkin, I'm sorry.
Thanks. Possibly, sorry. But these fires ripped through the community so fast, they were already burned and gone on.
Oh, okay.
There wasn't even a lot of firefighting of that sort, but I think eventually there was to finally put it out. Yeah, good thought.
Okay, Doris had her hand up.
This was a question I wanted to ask Dr. Carpenter earlier, and actually was probably answered in what he was saying, but so I would assume that the omega-3s are really concentrated in the fatty part of the fish, which also has the highest concentration of toxics. Is that true?
Well, anything that's fat soluble is going to be in the fat. So that certainly includes most of the persistent organics. And for phthalates, I actually don't know whether they're water soluble, so they're probably not concentrated in the fat. But they may go into the fat to some degree as well. But they are water soluble. You measure them in urine. So they probably are not extensively concentrated in lipid layers.
But even generally for all toxics, is it more located in the same place where you get the beneficial parts of the fish, the omega-3?
Well, remember that the perfluorinated compounds bind to proteins, so they are not in fat either. They bind to serum albumin, they bind to proteins in muscle and organs.
Okay.
So these nasty chemicals, they have all sorts of ranges of being lipophilic or being hydrophilic. And you really have to know the characteristics of each individual compound. And then, of course, what we see with things like the PCBs is that those that have fewer chlorines are more water soluble. Those that have higher chlorines are less water soluble. So there's a significant water solubility, but only of PCB congeners that don't have a lot of chlorines on them.
I see Tom has something to say.
Yeah, just a comment. I mean, mercury is one of the major fish contaminants, and it's not in the fat at all.
That's right. Just like the perfluorinated compounds binds to sulfhydryl groups in muscle.
Yeah. So you can't get rid of mercury, by cutting off the fat.
Other questions, Patty?
So I'll direct mine towards Dr. Carpenter as well. While you were talking about the benefits of omega-3s, I texted my son regarding that. He's like, wouldn't it just be better to eat algae? So I have to have a comeback to that. I did tell him I preferred to have the algae already processed by a fish, but would it be as good as eating the algae directly?
Well, the algae don't bioconcentrate the contaminants like the fish do. So yes, the answer is that would be better. It's very interesting because while in the past, until very recently, there's been just this wide perception that the omega-3s were just God's gift to mankind and cure everything. There have been a very a series of papers in the New England Journal, for example, arguing that there is no significant effect of omega-3s in preventing cardiovascular disease, which has been the party line for a long time, that was very valuable. Clear evidence that they don't prevent cancer, they don't prevent diabetes. So I must say, I was very surprised when our studies showed this very positive effect on cognition in older people. There had been some from the psychiatry community that have been arguing that they were beneficial against mental illness and neurodegenerative diseases, but it's never been very convincing. And yet our results are pretty strong in that regard.
And a follow-up to that, could that be that the benefit is because the omega-3s are anti-inflammatory?
Well, they are anti-inflammatory, but they also are significant components of neuronal membranes. So I think the anti-inflammatory effect certainly would be positive, but the effects on the membranes also are probably very important.
So David, there's also been some data on, with infants, early development in terms of its.
Yes, certainly. I think I mentioned that premature infants that are not breastfed clearly benefit cognitively by supplements with omega-3s. Whether a normal term infant or even a preterm infant that's breastfed benefits, there's not any convincing evidence that that is the case. Because breast milk normally contains a significant amount of omega-3s.
Doris? Doris, do you want to unmute yourself?
Sure. So I have another question, which was brought up with the PCBs. And so EPA constantly says that the kind of PCBs that are in the sediment do not volatilize that are in the Portland Harbor. And I'm wondering how true that is.
That's totally false. The PCBs in sediments are in equilibrium with PCBs in the water column. And again, it is the PCBs in the water column are going to selectively be those that are more water soluble. Those are going to be the lower chlorinated congeners. So the higher chlorinated congeners, they'll pretty well stay there in the sediments. But the lower chlorinated congeners will dissolve in the water column, and then they will volatilize off of the water column into the air. So the result is that the PCB profile in sediments changes over time with depletion of the lower chlorinated congeners and concentration of the more highly chlorinated congeners.
Thank you.
BJ has her hand up.
Yeah, I can also maybe refer this to James if he wants to comment, but I think it might be a question of timing, Doris, because EPA Region 10, same as in Portland Harbor, does acknowledge the volatilization of PCBs from the sediments at the Duwamish site here in Seattle. And James might have some more information on the current state of that, but I know it's a consideration in managing the impacts of the cleanup activities themselves.
Unmuting myself, and I just want first to say, when we started this so many years ago, Darlene, John, and others that were part of this, I don't think we ever would have expected it to go where it is right now. And kudos to all of you for keeping this going, Patty and everybody else, because this is an important endeavor as far as all of us are concerned. When we talk about PCBs in the Duwamish, it is the driver. That is the driver that actually, hopefully, will help us get to the point of being able to clean up the river itself. Right now, we are at a point, because of an explanation of significant difference and a cancer risk on PAHs, which I asked the question about. And I'm sorry I couldn't be here for the whole day. You might have already covered all of this. But right now we're looking at a 7 times plus reduction in the river for approximately maybe 5 acres. It's not a lot, but in Portland Harbor, it's well over 30 acres. And I just want to hear some of our experts talk about that maybe again for me, but it has an effect on fish. It has an effect on wildlife, in particularly in clams. So I would like to hear some kind of explanation on this reduction in what's the best way to say it, in in contamination levels?
Well, certainly getting the PCBs out of sediments in bodies of water is a very important first step. Now, the problem is that even when there's extensive dredging, that you're never going to get all of the contaminated sediments out. So the problem is that, and again, you know, most of my knowledge comes from the Hudson River, where we've had extensive dredging on several occasions. And the PCB levels in the fish are going down, but they're certainly at this point still not down to levels that will allow FDA to say that one should eat them. So it's a little discouraging because, you know, fish eat sediments, and if there's any contaminated sediment there, they're going to get it in their bodies, and then it gets in the food chain. But they're not going to go away by themselves. So the only thing that one can do is get them out of the sediments as best you can.
So, Mr. Carpenter, if you are, if you really do follow the Hudson River, then you know that as the process went through, that communities actually wanted and asked for more cleanup. But since EPA already had an agreed order, they couldn't do anything more. And that happened because most of those communities were in support of the responsible party, which was GE. And as we move forward here in Seattle, as Portland moves forward in Portland, how do we make the argument that it is better to do more than less?
Well, I think the way that we provide the evidence for that argument is clear documentation of the adverse health effects in people that live by the rivers or by the harbors. That's something that I've been doing for a number of years here in New York, where we've looked at rates of hospitalization for various diseases if they live by a PCB contaminated identified hazardous waste site. One of those is 200 miles of the Hudson River. And we've shown specifically there that the river's attractive. So the people that live along the river have higher incomes, they're better educated, they exercise more, they smoke less, and yet they're hospitalized more frequently for hypertension, for diabetes, for cardiovascular disease, for asthma, for respiratory infections. Diseases, all of which we can relate to exposure to PCBs. Now, our studies have not, we haven't been able to monitor blood levels in most of those people. On the other hand, I've studied two populations where we do have blood levels. Residents of Anniston, Alabama, by the Monsanto plants. And I would say it's really Monsanto that's the responsible party for all of the PCBs in the US. And then the Mohawk Native American tribe in the St. Lawrence River, where the responsible parties, in addition to Monsanto, are General Motors, Alcoa, and Reynolds Metals, because there they use PCBs as hydraulic fluids. There we can take measurements of blood levels of PCBs, demonstrate it, reduce testosterone level in both adolescents and adult men, elevated diabetes, elevated hypertension, reduced thyroid function, reduced IQ in both adolescents and adults, correlated with their serum PCB levels. So I think the evidence is pretty overwhelming that this is a very nasty kind of chemical that causes a host of different diseases. And the reason that one group of chemicals can cause so many diseases is, again, this nuclear receptor where you get gene induction that affects all sorts of different organ systems. So I think we have a very strong case that you live by a contaminated site, you're going to be exposed. That exposure can be from eating the fish, but it also can simply be from breathing the air or drinking the water if it's not treated water, because the lower chlorinated concentrates are going to be in the air and in the water.
And I'm sorry to interrupt Arlene and everybody else, but I do have to respond. In the Hudson, you might have higher income people that are being influenced by this, but in Portland Harbor and in Seattle, here at the Duwamish, it is low income people that are being.
And if you live by a contaminated site, your income doesn't really matter. It's been valuable for us to make the point because along the Hudson, the traditional risk factors don't seem to protect. Sorry. So they had elevated disease, even though they lived a healthier lifestyle.
Of course, and I understand that, but what we hold on to here is an environmental justice argument, because the cities and municipalities around us have those things as part of who they are as a government, and that seems to be the best opportunity we have.
I would certainly understand that point. That's absolutely true. A lot of poor people live near contaminated sites because it's cheaper there, and they have limited opportunities to live elsewhere.
And I would never want to hold up Darlene.
Well, I think before we get to you, Darlene, we have one question, comment from Diana in the chat. She says she can address the BAP from one perspective.
We can hold if people wanted to go on. It's just, I know, James, I think you were asking about the reduction or the reduced cancer risk for benzoate-pyrene. Is that what you were asking?
Yes.
Would you like me to address that now, or do we want to move on to something else?
Yeah.
A thumbs up from BJ. So this is actually something that Lisa, Tom, and BJ and I have been talking about. So I can talk about the way Oregon State has addressed it. And then I don't know if University of Washington, if you want to sort of talk about how you've addressed it. We opted to look at the impacts of that change. So we didn't go after the decision by IRIS that's reducing the cancer risk for benzoate-pyrene. We sort of left that to the side and we said, but what happens when you reduce the cancer risk? How does that affect the other PAHs in the area? So there are 6 other carcinogenic PAHs, and all of their toxicities are actually based on a mathematical relationship to the toxicity of benzoate-pyrene. So when you reduce benzoate-pyrene, you are reducing the level of those other 6 what are called CPAHs or carcinogenic PAHs. And so our center has looked at the toxicities of those individual CPAHs and are finding that the scaling to benzoate-pyrene tends to underestimate the carcinogenic potential of those other carcinogenic PAHs. So we've put out information trying to say that irrespective of the levels of benzoate-pyrene, scaling these other PAHs to benzoate-pyrene is not appropriate to begin with. So there's kind of those 2 areas. So that's where OSU has gone, just to say, like, we need to consider the use of benzoate-pyrene as a standard may no longer be appropriate. And then I don't want to talk for University of Washington, but I think you've been looking more into the decision-making behind the reduction in benzoate-pyrene levels.
Yeah, thank you, Diana. Tom, do you want to speak to the science behind the change?
Sure. And I think James knows this, but just to sort of give you the background, DRCC asked if we could take a look at the IRIS update for benzopyrene. So I took a lot of time and looked at the documents that were supportive of the IRIS document. And I felt from my experience, I was part of the National Academy of Science reassessment of methyl mercury in 2000. And one of the things that I thought was very important that when we decided that there should be a change in the iris for methyl mercury, it wasn't because of the one study that we found to do the critical study to do the calculations. It was because by the time we reviewed that study, there were just the weight of evidence with other studies out was just convincing, and you really couldn't make a good argument not to do it. When I looked at the benzopyrene iris, all that I could find is 2 studies that they're using to make the calculations that don't agree with previous studies by a factor of 5 or 10. And there's no study since then to support a weight of evidence that these changes should be made at this point in terms of risk management. So I asked EPA to basically rethink what they're doing. I think the data that is available at this point in time to make these changes, these risk management changes that will change the cleanup standards is inappropriate. Yeah, Annie.
I have a question because I'm unfamiliar with this, but are you saying that they're being, because of the toxic equivalency factor approach, they're all going down? So I missed most of your talk, but I would think that Oregon State has been developing data that could probably replace the TEF approach on a more mechanistic basis, as I tried to illustrate. So that would be your best argument, I would think, is to just show that they may not be interacting per the assumption of the TEF approach, which I think a lot of people, myself included, question the validity of at this point.
Yeah, no, the changes in cleanup are based on a new slope factor for cancer from oral exposure, and based on the studies that were I think published maybe 20 years ago. It's the slope factor changes by a factor of 5 to 10, and which then is driving them to reduce cleanup at these different sites by a factor of 5 or 10. So instead of cleaning up to 25 parts per billion, they're going to say they're going to clean up to 1,500 parts per billion, which I feel is probably not appropriate at this time.
And just to point out to what Annie was saying, I mean, it's true. I think we all do kind of agree that the TEF approach is not going to work really well here. And so we do have research at our center that suggests that, and I'm trying to do kind of complicated stuff in my head and it's not working, but like if you set benzoate pyrene at 1, and then you say that carcinogenic PAH2 is at 0.5, well, some of our data suggests that it's actually higher than benzoate pyrene. So 1, yes, you're reducing the risk level for benzoate pyrene, as Tom was saying, to 5 to 10-fold. You're also reducing all those other CPHs by 5 to 10-fold, but we're arguing that they weren't high enough to begin with. So they were already too low, and now we're taking them lower. Sorry, that makes sense.
I would just add that it's always dangerous to treat the unit risk as a scalar, because there's a lot of nonlinearities in the actual biology underlying that. So, I mean, if I could get away from the linearized multi-stage, that would be worth a Nobel Prize also.
Right. And we're happy. I think BJ or Lisa put one of our infographics in the chat. We did include citations for some of our papers where they actually have taken these CPHs and tested them in animal models and compared them, right? Like if you do the mathematical model that Annie's talking about, what's the number that spits out? But if you actually test it, what's the number that you get? And we're finding that those, perhaps not unsurprisingly, do not match. So I'm happy to share those papers as well.
Thank you, all of you. Darlene, you've been very patient.
Well, I was just going to make a comment following up what James was referring to and Dr. Carpenter was responding to. So I've been working on a hazardous waste cleanup in Port Angeles, Washington, also a 5-mile stretch. but a different shape than the Duwamish. And these are legacy chemicals from pulp and paper mills for over 100 years. We're down to 1 mill now, thankfully. And the oversight is not coming from, the oversight of the cleanups is from the state of Washington, not EPA at this point. So we have PAHs, dioxins, metals, phthalates, you name it, it's there. And ecology knows that. And the test, you know, I can't question the test, but they're not about to clean up much because they equate cleanup with cost effectiveness. And cost effectiveness is partly cost effectiveness for the polluter. So where the state is at is, well, we'll clean up this, we'll clean up that, and the rest and most, nature will take its course, or we'll bring in clean fill on land and for the soils and clean sediments over the in the sediments, and hopefully they will diminish to a point where when we go back and look at them in a few years, they'll be below a certain level of concern. Many of us are pushing back on that right now, but that's the philosophy and the way the Washington State Department of Ecology works. If it is a couple $1,000s more, or $10,000 or $15,000 more, why spend it if you could do less with less money? And
Okay, Laura, you've had your hand up.
Hi. I'm going back to the PCB thing in the Portland Harbor Superfund site. I hope that's okay. It was in relation to something someone said earlier. Dr. Carpenter, blood sampling is a way for testing PCBs. And I wonder, we tried, I think a couple of years ago with Multnomah County Health and the Oregon Health Authority to try to do a health study, and that was a dead end, a confusing dead end. And I guess just sort of an open question. You begin with the blood samples. How does a health study go forward? Maybe that's just too big and not for this discussion, but I don't know. I'm putting that out there. If anybody knows.
I would happy to answer that, and BJ can probably follow up and be much more talkative about it. Anyway, we've done several studies in the Duwamish Valley that have proven where before it was anecdotal evidence that there are multiple health issues in the area, but then we did I'm sorry, I'm just going up on the two studies. BJ? Because they were not done in blood tests and that type of way.
I'm sorry, James, what studies are you asking me to address?
The DRCC health studies.
Oh, so there were two. One was looking at the health status of the Duwamish the Duwamish Valley communities relative to other neighborhoods throughout Seattle. That's called the Duwamish Valley Cumulative Health Impacts Analysis, and I'll post a link to it, showing that the highest cumulative health impacts in the Seattle area are in the Duwamish Valley. And then the other one was a health impact assessment of EPA's specific proposed cleanup plan for the Duwamish before that decision was finalized. So I can post links to both of those.
But let me comment on health studies, because the problem with getting PCB analysis of blood is that it's very expensive. And if you do a good analysis, you're going to be talking about at least $1,000 per blood sample. So in a large population, it gets to be very expensive. There are some less expensive tests, but they're very insensitive, and they don't give you information about the congeners that are important. If you have a fish eating population, then the blood test will be quite accurate, because the PCBs in the fish are going to be the higher chlorinated ones that are very persistent and persistent in the human body. If it's an issue where their exposure is by inhalation, then it's the lower chlorinated congeners. They can be detected on a blood study, but they're not so persistent because they're more rapidly metabolized in people. And therefore, you have to look very carefully at the distribution of congeners. I think there's enough information now so that you can do a health study by comparing the health status of a community that you know to be living near a contaminated site without having to do blood PCB analyses. It makes the study much less expensive. And I think on the basis of all the evidence we have from other work at other sites, we know that PCB exposure is going to occur. And therefore, looking at disease profiles will give you satisfactory answers.
I think part of the challenge in the Portland Harbor is that there's a lot of gentrification going on. And so old timers are dying off. A lot of anecdotal evidence of people getting really sick who worked on the river, who lived near the river, but they're now dying off. And so you have newbies coming in, and they're pretty clueless. And when they learn about how toxic the river is, they're horrified and they're pissed often.
Yeah,
but how to study this turnover, in population.
I would advise you to really take a look at how our studies were done, because even though it wasn't inexpensive, as David might say, we had a grant to be able to do this, but it was incredibly informative, not only to the county and the city, which proved a point that needed to be proved. And I'm sure you're trying to prove the same point. But it is important to make sure that you have the evidence from their own Department of Health. And that's where we went, to Seattle-King County Department of Health. And when we started the work, the first answers that we got is that we know we have a problem here, but nobody's ever asked the question. Mm. And that's the point. I would like to ask David one more question. I've seen a change in reports from the Hudson Valley of people who, or let me say, municipalities and that were very in support of General Electric at the very beginning of the process, and now wish to see more cleanup, but can't see that done because EPA already had the agreed order. Is there any change in that at all, or is it just status quo as far as EPA is concerned?
I think there is really very little change. Part of the problem was that there was a settlement with General Electric. General Electric did what EP demanded, and therefore EPA thinks they can't demand more. It's very interesting. The health department did a study of the health of the workers that lived near the GE plants along the Hudson. And then they took as a control area the county just above that, which was above the plants. And what they found is the PCB levels were higher in the control county than they were in the exposed county. And then it turns out that the GE for years had been using PCB oils for dust control in Warren County, the control county. They were giving contaminated fill for the people in their backyards when there were new houses. There were all sorts of contamination that was no longer local. So that's, and then of course, the health department released a study saying that there were higher rates of cancer in Warren County than almost any other county in New York State, totally ignoring the fact that Warren County was highly contaminated with PCBs. So, you know, it's pretty much the status quo and unsatisfactory to everybody.
Thank you for your perspective. Doris, I know you had your hand up a while ago.
So my comment is Darlene's comment earlier. And so we get from EPA a lot on the Willamette that dilution is the solution. So basically the Willamette River is a very dynamic river. It's got prop wash, it's got storms, it's got, it's a tidal river. So there are constantly sands coming in and covering up some of the pollution, but those sands that are moving further downriver are just polluting the Columbia and eventually the ocean. So it's polluting, you know, and it may be that those standards are less, but it's not less polluted areas being now more polluted. So pollution for this, the solution is not a solution anyway, and it's promoted oftentimes here at on the Willamette Superfund.
BJ, a comment?
Yeah, this was really just a follow-up on the previous discussion about the health studies. Just to clarify, neither of these were drawing blood or testing humans for contaminants, but the cumulative health impacts assessment or analysis was looking at economic, social, and environmental indicators, because many of the social and some of those other health indicators make communities more vulnerable to the environmental exposures. And then I also wanted to let Laura know, because of your comment about gentrification, that is specifically one of the things that, that we prioritize looking at in the health impact assessment of the proposed cleanup plan. We're looking at some of the unintended health impacts of cleanup, one of those being green, or in this case, clean gentrification, and then how to mitigate for those impacts as the cleanup went forward. So if that's something that that you're interested in for Portland Harbor and the Willamette, there might be some good material in there.
Thanks, BJ. Darlene?
Would doing, instead of looking at health impacts, would looking at deaths in the area and causes of death help with cleanups?
Well, that certainly is another monitor, but there's so many factors, socioeconomic status and so forth, so many factors that that influence death. What my group has done is looking at hospitalization, because that's a good indicator of rates. In New York, we have a very good system where any person that goes into a hospital or an emergency room, that hospital must report to the state health department every disease that person has, up to 15 different diseases. So that gives us something a little more sensitive, because we know which diseases rather than just death. But obviously death is an indicator of exposure, no question about that.
Well, I asked because a couple decades ago, we've been working on the site for 30 years, but a medical doctor, also epidemiologist, worked with an epidemiologist at the Washington State Department of Health. So they agreed to look at potential causes of death and where they were happening, the high rates. And no surprise, they were where the worst mill sites were over time. And I don't think it's been so long ago that they could pinpoint anything to a particular health problem. It was more general, if that makes sense, but they could definitely pinpoint where the higher numbers of deaths were coming from, age-related, over so many years. They tracked it, went back into the records, the state records, the local records, and tracked it.
Well, having worked for the New York State Department of Health for many, many years, I'm very suspicious of some of their conclusions. In New York, they did this study on rates of cancer. Now, that's not deaths, but diagnosis of cancer. They found 5 counties that had the highest rates of cancer, and then they almost wrote the same report for each of them. There's too much smoking, you're too fat, you don't exercise, and it's all your own fault that you have cancer. Hardly looked at any environmental factor at all.
Yeah. Name of the game.
If you find environmental factors in exposure, then governments have to do something about it. So it's much easier to blame the victim than to go in depth and demonstrate the exposures that may be the major cause of the elevations in disease.
Thank you. Patty, I see your hand, but Greg has had his hand up. So Greg?
Yeah, I had a question for Briana and Diana about the work they're doing and in terms of kind of practical outcomes. So you're doing a look at methodology, and essentially for that methodology to impact, it needs to either be incorporated into policy or needs to be cited by people like us that are advocates for cleanup levels and such. And I was just wondering if you could address some of the what you think might be likely or preferred outcomes of the work you're doing in terms of incorporating it into policy or into actions.
Briana, do you want to take a stab at that?
You can go ahead.
All right, so you have a really good question, Greg. So I'll try and address it to the best of my ability. So because we are funded by the National Institutes of Environmental Health Sciences, our Superfund Center, like all of them, we all have what's called the Research Translation Core. So for Oregon State, that is me. And that is part of our goal, right, is to figure out how can we take these methodologies that we are developing and put them into practice beyond the realm of research, right? Because research is different than regulatory. And so that is part of our goal. It's called tech transfer, but basically working with EPA and other regulators. And that can be holding workshops, it can be publishing, it can be informal conversations. But ultimately there actually is a practice for us to try and get these protocols and methodologies sort of standardized so that they can be used by regulatory agencies if they want to. It's a longer process, but through our work, we're routinely engaging with regulatory agencies. So we have external advisory stakeholder boards. Like I said, we're holding these work groups and workshops when we can. We've had some work with that before. I mean, so I think, Annie, you were mentioning the adverse outcome pathways. That's something our center has also published on and worked very closely with regulators to try and get that moving forward. So that's our hope that as we have success, and hopefully we have success, I'm going to think positive here, with these methodologies, that we can then take the science and then move it beyond just the research realm into that. Does that answer your question?
Yes, in part. And I think the other part of it is like how we can engage, because a lot of us are in a position of advocacy, which in your position might be a bit harder because of your source of funding, review boards that you have to answer to, et cetera, where some of us are freer to pursue policy agendas as kind of we see fit. And so I was just wondering how that interface might work.
Right, so you're right. Because we are federally funded and working at a university, we do not advocate. So everything that we do has to be strictly based on science. And we cannot advocate, one way or another as that may affect policy. But there are some pretty standard methodology, and say standards for standardizing, essentially. And I can't quote them to you right now. I can look into that if that's something you're interested in. But it does come down to creating laboratory standards so that the work that we're doing can be replicated by other researchers. And so that should a regulatory agency choose to do that methodology, it is well documented. And this can come down to literally how long you're shaking a tube, what temperature you're heating things up to. So it really more is pushing a lot of paper on my end, I think, is what it's going to come down to.
But that does not include you helping with a health study along the Willamette that is not a blood health study, but a health study that would start to prove the issues as we've done here in the Duwamish Valley.
Correct. We can partner with people. So I've partnered with NGOs, advocacy groups, environmental groups. Absolutely. We can do those partnerships. I just always like to try and set the expectations, right? That we cannot advocate based on the results of science or of the study. But yes, we can absolutely partner with people.
Great. Thank you all. Patty, had her hand up.
So my question's for Annie, because I know she's got to leave by 4:30, right? Okay. And I don't know whether this is really, well, I guess it's relevant just because you look at population size when you do risk assessment. And statistically, you need to be a population of 100,000 to be considered statistically significant, which makes rural communities, areas that have fewer people, that are typically low income and minority, not significant, so they're ripe for abuse. And since the EPA is going to have a focus on environmental justice, I was wondering how that might factor into how you look at risk and how you think about those of us that are, being abused.
So I think you're referring to how cancer unit risk is expressed, which is one in effect, but that doesn't mean that that's how we define a population. So for community-based assessments, we would define a community as a community wishes to be defined. And as I mentioned in my talk, defining that boundary is an important part of the problem formulation. Are you going to do it based on geography, some sort of topology? There may be mountains on one side that creates a boundary. It's up to the stakeholder community to define how you want to be described. It could be based on certain other demographic issues, but community-based assessment is just that. The community gets to help define the community. It has nothing to do with the way that cancer unit risk is expressed is often just based on extrapolation from animals. And that 1 in a million is just a convenient scaling function. It doesn't mean it came from a population of 1 million people.
Right. I guess I'm just thinking about how years ago when we were, the focus of the disposal of hazardous waste as fertilizer, and any of the cancer statistics that came out were based, or actually we were told that they couldn't correlate it because we were a population that was less than 100,000. And so it wasn't statistically significant when you saw the rates of cancer that we had, which we had a higher incident. If you could extrapolate it, it would be a higher incidence of renal cell carcinoma and breast cancers. And so we were told that that wasn't significant. And so I guess that's where I was going.
I'm unfamiliar with that, but it's probably, actually you heard when I was asking Shanna about how to get hormones on the same scale as chemical assessment. And she said we'd have to do a 1 million mouse study. It has to do, if there's a low signal, you need more of a population to be able to see it statistically. That's the problem. But it doesn't mean that we would not be doing community-based assessments. It just depends. Maybe you wouldn't look at cancer. You might look at some other outcome measure that has a higher penetrance in the population.
Okay, thank you.
You can look at something, for example, more acute, lots of intervening factors and a long duration for cancer to manifest, for example.
Great, thank you. Tom, do you have your hand up? Oh, you're on mute.
There we go. So I was just going to go back to Greg's question to Diana. And I think that they've already produced data that could be used by advocates to stop this change in the cleanup standards process that's going on right now. I guess the question is, how do you do that? I mean, they've already indicated that this, potency factor, is not a good way to go, that there's actually data that would indicate, that would not give you a good estimate of risk. I think it's out there, and so far I think it's being ignored. So I think.
So is Superfund in charge of this? Yeah. I mean, I know it's the IRIS assessment, but it sounds to me as though, remember when I went back to who's the enabling legislation for your given problem? Right. If it's Superfund, then it's the Office of Land and Emergency Management. So OLM is who you need to look up in terms of a DC office. I'm pretty sure that the folks at OSU know Kathleen Raphael. She's a science advisor to OLM, as is Stephen Foster. I'm a science advisor in ORD. They're science advisors in OLM. That would be somebody that I would think to call up and query.
I will also say with Portland Harbor, so we put together that fact sheet. We sent out the articles. The biggest thing I noticed is that people actually did cite our research when they were doing the community response to the revisions, but they didn't actually cite it properly. They just said OSU research, and they didn't put the title of the article. They didn't specifically say what that was. And again, we don't advocate, but I can explain the science, or I can state this is what our science does or does not say. And so when the final decision came down, there actually was a line in there that said, we saw people cite the OSU thing, but we don't know what that means, so we cannot respond to it. So I would say if you are choosing to make responses as a community member, citing that research is going to be very, very useful. And again, I can send you citations, but being as clear and precise to those specific points, that means then that there will have to be a response, and you'll be able to see the thinking behind if they're supporting or not supporting those points.
So maybe Annie, if you could maybe just send us information on what you just said so we remember it. Is that okay?
Sure.
Thank you.
So Diana, do I have that right? It's under Superfund, or you just mentioned water. So which office is it?
I would actually have to look. So with Portland Harbor, it was in water and sediment. And I'm not sure what Duwamish is. So we've been working with EPA Region 10. Obviously, I think they were handling the record of decision, and they're the ones that responded.
Record of decision makes me think it's Superfund, but we need to clarify that.
And it should be, because Portland Harbor is Superfund site.
And so is Duwamish. And one of the things that I want you to understand, it was responsible parties that pressed the issue. In other words, they went to the site manager and said, this is what IRIS says, this is what you have to do. And so that's what she did. And that then started the, explanation of significant differences. And that's what started the whole issue here. And probably the same thing in Portland Harbor. I'm even though I'm not understanding that, if somebody could tell me that it was the responsible parties that pushed that.
You're right, James.
I'm sorry, but I'm going to get off. It's 7:30 in New York and I'm being called for dinner. Good interchange of discussion and I thoroughly enjoyed it. Thank you.
David, thank you so much.
I need to leave also. That all this noise is my kitten going ballistic. I need
Thank you, David.
Okay.
Thank you, Annie.
I enjoyed this also.
Thank you all.
Thank you so
Okay.
much.
Thank you all. And I think we should close now. It's a good time to end.
Yeah.
Diana and Briana, thank you so much.
Absolutely.
Thanks for having us.
We'll be in touch for your data, for sure.
Annie, do you want to say any closing words?
Did you say that to me?
Yes.
Who did you say?
You're the
Oh, I
boss.
was just going to say thank you to everyone who attended and to our speakers that still remain. Thank you. And all the help that we've had in putting this together. It's been a great afternoon.
Yeah.
And morning.
Important.
Tom, any
It's been a
last
good day.
words?
Yeah, no, I also want to thank everyone for all their hard work putting this together. And I thank the speakers that are still here. Diana, I hope it's okay that I pointed that out, that you're already doing great work that can be used for regulatory issues.
Oh, absolutely. Yeah, like I said, we have a lot of those papers and we're happy to work with people to sort of translate the science speak into like how actual people talk because they're very different.
Yeah. So thanks everyone. Thanks everyone for coming.
Thank you.
Yeah.
Good to see
Thank
you,
everybody.
everyone.
Good to see you,
Yeah,
James,
wonderful.
BJ,
Greg, do you have a
Tom.
camera?
Have a good evening.